Hi everyone, and welcome to this chapter of Full Stack with Swift. In this chapter, we're going to look at all the modern concepts that are available in Swift as a programming language. If you've already watched an introduction, you probably know that this course generally, not just this chapter, but this course generally is not for absolute beginners. So I expect you to already know another programming language. It doesn't really matter what it is. It can be Python, Rust, it can be TypeScript, JavaScript, whatever. As long as you know the basics of programming languages, such as what functions and variables are, then you're good to go. If you don't have that experience from before, this course generally might be a little bit difficult for you to follow through with. I will do my best to explain everything, but since I don't really want to explain all the basics, I think it is best that you perhaps have a look at some guides on getting started with another programming language such as Python, and then get started with this course. However, if you haven't worked with any other programming language from before, and you're also very talented as well, which I assume everybody is, you might be able to follow along with this course without problem. So what we're gonna do now is to go ahead and set up a playground, basically a workspace with many playgrounds in it. And playgrounds are Swift's concept of being able to immediately see what your changes are doing, and it will allow you to basically run your code automatically as soon as you make any changes to your code. So it is a very powerful way of testing code, or even creating some projects in it. You can create a whole project with a playground and see the results graphically even on the screen. So it's very powerful. For those of you who are familiar, for instance, with Flutter and Dart, you already know that you can see your changes displayed on the screen immediately, and playgrounds are no different. They're very similar actually to how Dart and Flutter work, but it's a little bit actually simpler, I would say, because we're writing pure code and just seeing pure text displayed on the screen as a result of, for instance, calling a function. So in order to continue with this chapter, you probably need a Macintosh. However, what we're going to do, we're just going to use Swift Foundation SDK in here, or a library. So you can actually follow through as well on Linux, such as if you have, for instance, Visual Studio Code already set up, and you've installed Swift, you should be able to follow through. The only difference will be that those of you who have a Macintosh and Xcode installed, you will be able to create a simple playground and see your changes immediately. For those of you who are following this on Linux and Visual Studio Code, for instance, you need to run the code manually. So you will need to just type your code and then call Swift compiler from your terminal or a console in order to run those codes. So it shouldn't be that different. So you should be able to follow along even on a Linux machine. So without further ado, let's just go ahead and create our workspace. Now, I'll explain what a workspace really is. A workspace is a collection of projects, you could say, a collection of files and projects. It's really just one file that explains the structure of a project to Xcode. If you're running things on Linux, you don't have to create a workspace. You probably can't, because Xcode does that. And unfortunately, this Xcode, basically Xcode application creates like a proprietary format for all of its files, kind of. So not the text files, but like the workspace and project files. They are proprietary XML format, which is puzzling why in this day and age it has to use XML really. But that's a different subject. So if you're following through with the course at home with Linux, then you don't have to create this workspace. But if you're at home with a Macintosh, you need to go ahead and create this workspace together with me. So I'm going to bring up my Xcode just enough in here so that we can see what we're doing. I'm going to go to new, and let's just say workspace. Then in here, let's just say Swift crash course YouTube. Okay, in here. And let's just say save this workspace. As you can see, it's just an empty workspace at the moment, so it doesn't have any contents. What we're going to do then, let's just increase the size of this so it takes the entire screen. And then we're going to go ahead in File, New, and then we're going to go into File, and in here type Playground. in the search field and add a new blank playground. Okay, so the first concept that we're going to talk about in here is going to be called variables. So let's just say variables. And I can see that our workspace was actually just created in here without any folder. So we might be able to remedy that before we create our playground. Let me just go ahead and open a Finder window in here. So let's just go ahead in here. You don't see actually what I'm doing, but right here is the folder. Then I'm going to create a folder in here. Let's say Swift Crash Course YouTube, and place this, and then we can close our Xcode, place the workspace in there, and let's just double click on the workspace to open our Xcode. So now all the playgrounds that we're going to create are going to be created inside that folder. Okay, so let's go ahead and create our variables for playground from scratch. So file, new file. Okay, and then in here we're going to say playground, and you can actually find playground a little bit lower in here, I think. Somewhere in here you can see in the playground section. So let's say blank playground, and let's call it variables. Okay, because we're going to talk about variables now. So this is the default thing that you can see in here, and basically this is your view. You might see a whiter screen in here simply because, well, maybe you haven't changed your themes in Xcode, and that's something that you can figure out on your own, how to change themes in Xcode. We're not going to talk about that, okay? Let's clear this, and instead of importing UIKit, we're going to just import Foundation. And if you're watching this course at home, or wherever you're watching this on Linux, for instance, and if you don't have a Mac OS, you need to also do the same thing. Just import Foundation. Just create a simple Swift file. You don't have to create a playground. Just create a plain text.swift file and then import Foundation library in here. Okay. Very good. So now we've imported Foundation, and Foundation includes all the basic, as its name indicates, it includes all the basics of what Swift contains, really, like how strings work, how integers work, all the default operations between these different variables, and even optionals, etc. So importing Foundations is one of the most important things you can do basically in your Swift file as you're getting to learn Swift. Okay, so let's go ahead and talk about variables. In Swift, there are two different syntaxes or keywords for creating variables. One is using a let, and the other is creating a variable using var. So let and var. The difference between these is very confusing for some people in that they think that let creates immutability and var creates mutability. However, the only thing different between these two is that a let variable cannot be assigned to again, whereas a var can be assigned to again. There are some other small differences between them. We will actually look at those things when we're working with classes, for instance, or structures, how they differ from each other. But for now, just know that let cannot be assigned to again and var can be assigned to again, but also keep in mind that there are some other small differences between them, which we'll explain, okay? So let's go ahead in here and say let my name, and then we say equal to lambda, for instance, and then we say let your name is foo, okay? After you've done these and created these two variables, you cannot assign to them again simply because they're let variables. So let's say my name is your name, and if we go down here at the bottom of the screen, you can see my mouse, and I'm going to hold on this button. So I'm just going to press my trackpad and then say automatically run. And this will just ensure that this playground will be automatically executed anytime we change anything in it. Okay. You can see the error. It says that cannot assign the value. My name is a let constant. So that's how you know that you cannot assign to it again. After creating a let constant, you just need to leave it. You don't have to, you can't basically assign a new value to it. Okay, so that's how let works. Now let's go ahead and create a variable. So for now, we're just going to create a simple array, and I already assume that you know what arrays are, but we're going to talk about collections a little bit later. Just know that in Swift, you create an array with this syntax with square brackets. Okay, so let's say var names is, we're going to say my name and your name. Okay, so we just created an array in here. And you can then see the results to the right hand side. You can see this array contains van.dot and foo. Okay. Now you can go ahead then and say, since this is a variable, then it can be mutated even internally if it contains, for instance, a structure. So we say names, and then we can call an append function on it, and we say bar, and then we can also add baz to it, as you can see in here. So by the end of this, then our array called names contains van.dot, foo, bar, and baz. However, if you change this to a let, you will see that we'll get some errors in here saying that this is a let constant, cannot use mutating member on immutable value names. Now, this goes a little bit deeper in how let and var are different from each other. But in order to understand that, we need to understand what structures are, because arrays in Swift by default are structures if you're not using old Objective-C arrays, for instance. So just know that by creating a variable array, you can append to it and you can remove stuff from it, for instance, as we'll see later. However, if this is let, you cannot mutate even the internal values inside it. So you can see there are two mutability concepts in Swift. One is that you can actually mutate this array. For instance, you can say names is completely equal to another variable, like blah, okay? So you can see all of a sudden it became blah, blah, bar, baz, you see? So this is mutating the variable itself. It is actually assigning a complete new array to names as a variable. And these two statements are mutating what is inside this variable. So doing a let in here prevents both assigning a new value to names and also mutating names. However, having a var, you can assign a new variable to names, and you can also mutate names internally. Okay, so this is another difference between let and var. So it is also very, very important to understand these two differences, mutation of the variable internally and assigning a new value to the variable to mutate it. So a lot of developers struggle with that, especially in the beginning. So I completely understand if it is a little bit difficult to start with, but the earlier you learn this concept, the better, because otherwise I think Swift can become quite difficult for you to understand going forward. So spend some time and experiment with let and var, but we will have quite a lot of examples in this chapter, so you don't have to do it on your own. Okay. So now, if you change a variable, like if you've created a variable and you assign a new value to it, it won't change the object that it originally was assigned to. Now I'll explain what that actually means. So let's say let foo, let's create another space in here. Let's say foo is foo, and then we say var foo2 is equal to foo, like this. Okay. You can see now this variable of foo2 contains the value inside foo. All right, and you can see both of them contain the string foo. Now, if you go ahead and set the value of foo2 to, for instance, foo2 like this, you can see that foo and foo2 still contain the values that you'd expect. Foo contains foo, and foo2 contains the new value. So by assigning a new value to foo2, which was previously equal to foo, you're not overwriting the value that was inside foo, simply because this is referring to this. And the reasoning behind this is that we're working with something called value types. Now, I will explain more value types later, but all you need to know for now is that by assigning the value of foo to foo2, we're simply copying this value over to foo2. So this value is being completely copied, and you're creating a new instance of it inside foo2. So now we have two foos inside memory by this point. So we're not getting a reference. So it's not a reference type that we're talking about. Swift has value types and reference types. For those of you who are not familiar with this concept from before, don't worry about it. I'll explain it more in details. But for those of you who are familiar with this concept, just know that structures, which are basically a Swift string is a type of structure. Structures are basically value types. And then we also have classes, which are reference types. And we will explain all of these later in the future. But just know that by assigning a value that was assigned to a variable with let, assigning it to a variable like this with var, and then changing the value of that variable, and assigning a new value to that variable. You're not changing the value that was assigned to that variable initially. I know that, I mean, this sentence is a little bit complicated, but I think you get my point in here, what I'm trying to say. Okay. Now we can have a look at another example of this and how that looks. So let's go ahead and say let's more names, and let's create an array in here, and then we say foo, and then bar. Okay. Then let's say we create a copy of it. We say a copy is more names, and simply because this is a let variable, and also that we're working with a Swift array, which is a structure, then we should know that structures are value types, and assigning the value of a structure to another let variable in here creates a copy of this entire array for us. Okay, so now that we have, let's make this a copy variable basically. Let's now go and add some value to this copied variable and say append, and we say baz. All right, and then we say let's get the value of more names and then the copy. You can see more names in here still contains foo and bar, which were the original values. However, the copied variable now contains baz, as you can see in here. So adding baz to this copy did not change the values that were inside more names. And this again goes back to how Swift is working with value types in here. It is copying over the contents of more names into this copy variable, and changing this variable's internal data does not affect the original data which it was assigned to in the beginning. Okay, so hopefully that makes sense by now. Now, one thing that can be a little bit confusing for developers is when they're working with let and var, but with old Objective-C classes. All right, and this can be a little bit strange to start with. Like, a lot of developers who are not so familiar with Swift would say that let creates immutable variables, so you cannot change them internally. However, if you're working with a let variable, with a let constant, for instance, in Swift, however, that its internal value is an instance of a class, that class can mutate internally without this let variable getting in the way. Let's have a look at an example. For those of you who are familiar with Objective-C, you know that there is a class inside Swift which is called NSMutableArray. Now, if you just want to learn Swift, you don't at all need to know about this. It is simply for those of you who are a little bit curious about let and var. Okay, I'm just going to demonstrate this to you, but please, if you're not completely understanding this example, it is completely fine. Chances are, if you're working with Swift and you're learning Swift UI, and even if you're working with UIKit, for instance, to create your UI applications for iOS, macOS, whatever, chances are you may not really be using this thing that I'm going to show you at all, or maybe you'll use it once or twice in your entire career. And more and more Swift gets modern, less and less we're going to use these classes. So, but for those of you who are Mac developers, for instance, you probably actually work with NSMutableArray perhaps often. Okay, especially if you have an old code base. So let's create a constant in here where we say let old array, and we create an NSMutableArray in here. Okay. And then in here, we say that the value is an array, okay? And then we say the array contains the values of foo and bar, like this, okay? Then you can see in here that Swift Playground says old array is foo and bar, right? And you see, oh, this is let, so we cannot change its internal values, because if you, for instance, have a look at this one, an array again, okay, which is created with let, if you say more names, and you say append, and you say hello, you will see that you will get an error in here. It will tell you that you cannot append to this variable because it's created with a let statement or a let syntax, okay? However, in here, since we're creating a let old array that is equal to a class instance, which is not a structure. And again, I completely understand that we haven't talked about classes and structures yet, but just know that this is not, this is basically, as its name indicates, it is mutable internally. It can be changed, whether it is assigned to a let or a var, it doesn't make any difference. It is a class, whereas this is a structure. Okay, and structures are value types and classes are reference types. Okay, so just know that for now, that this is indeed mutable, even if it is assigned to a let variable. Okay, so now all of a sudden you can say old array, and then you can say add, and let's say Baz. All right, and now you can see Swift Playgrounds runs this code and tells you that indeed your let constant, what you thought was constant, has changed internally. All right, now you can go ahead and create a new variable, and we say new array is old array. And if you say new array, add QUX in here, CUX, okay? And then we say old array, and we say new array. Now you can see the results in here. Since new array got the value of old array, you add a new value to this new array, and you'd expect probably for new array only to change, not for old array to be affected. However, you can see the result that both old array and new array are actually referring to the exact same array. So this can cause a lot of confusion for developers who are, for instance, new to Swift, thinking that, oh, I just created a let immutable variable, no one can change this. However, you can see that it got changed. And even worse, you can, if you pass this value, for instance, to a function, that function itself can also change this variable. So it is quite dangerous just by using let. It's not that we're completely getting rid of mutability in Swift. So a lot of things can go wrong, especially if you're using reference types such as NSMutable array. But don't worry about it. I mean, if this is a little bit alien at the moment, I will explain this a lot more in details later, okay? As I mentioned, be very careful when you're working with mutable types in Swift and when you're passing them, for instance, to functions, because those functions can actually change your mutable types even if they say they don't. Okay, so let's have a look at this. Let's say we create another array in here. Let's copy this, and I'm gonna say let some names, and then we say foo and bar. Okay, so that's fine. Let's create a function, and I completely understand we haven't talked about functions yet, but this is the syntax of what functions look like in Swift. So we say func change the array, and then we have an argument called array, and in here we say NSArray. Okay, now I'll explain to you what NSArray is. NSArray is the NSMutable array is the mutable variant of NSArray. And if you actually go to the source code for NSMutable array, let's say NSMutable array, you can see that its subclass is NSArray. So anywhere you have an NSMutable array, anywhere your function or call expects an NSArray, you can actually pass an instance of NSMutable array to it, because it will just work. It will be downgraded to NSArray, okay? So let's say that we look at this function, and this function just looks like it is working with an immutable array in here. However, internally, it can say, let's just say copy is array as NSMutable array. So this is a syntax in Swift that you shouldn't really use that often, but code can actually do that without getting bugged by Swift, really. Okay, so you can see in here we're saying we're creating a copy. Array like this. We're basically creating a variable that is called copy. However, it's not really copying the instance, it's just named copy. So maybe we could just call it array2 or something, or just copy, but just know that it is really not copying the value inside this array. It is just assigning it to this variable, but it is setting its data type, it's promoting its data type to a mutable data type. It's assuming that it is mutable, okay? This is really bad code. You should never write stuff like this, okay? But I'm just demonstrating that it is possible to write code like this, and you should kind of guard yourself against code like this. And then in here, we say copy.addBaz, okay? Now, if you call this function, change the array, with your mutable array, everything will just work as expected, some names. And then you can say some names and have a look at the data. Now, when this code is run, you can see in this scope, some names after being passed to change the array has actually been internally mutated. You can see foo, bar, and baz. So this baz, that this function added to this array, is actually present outside that function as well, simply because we're working again with reference types, meaning that there's one copy of this in the memory, and this function is actually changing the original copy. Okay, so that was really it. That's what I wanted to explain in this particular section of the video with variables and constants. So just know that you have let and you have var. Let it, if working with value types such as structures of Swift arrays or strings or integers, it prevents immutability of that value internally, meaning that you can't change this van to, for instance, say my name, and then you can say is equal to, actually my name, make uppercase. You can't do stuff like this. So you cannot like change the value that is assigned to this, and you can't reassign a value to my name after it has been created. Okay, so the reassigning, that you cannot reassign a value to a let constant, applies to both reference types and value types. So it doesn't matter if the value inside this let constant is a string or it's an instance of a class. As long as it's let, you can't assign a new value to it. For instance, let's say here is, you can see it is a some names. It is an instance of a class, which is a reference type. However, the fact that you cannot reassign a value to this still holds true, whether it is holding an instance of a class or an instance of a structure. So let's say some names is blah in here. Now we should get an error in here saying that you cannot reassign another value to this after you have created it. So this reassigning to a let constant applies both to reference types and value types. However, the internal mutability of a let constant only applies, the prevention of internal mutability of a let constant only applies to value types such as structures. If you've assigned a class to a let constant, the class might internally change without Swift actually complaining at all. Okay, so I completely understand it's a little bit complicated, and I personally believe that some other programming languages have implemented this a little bit more beautifully and a little more like fluid, such as Rust. And I have some courses actually about Rust as well, so you can watch my Rust crash course, for instance, on YouTube, and learn about mutability in Rust as well. But I believe that Rust has implemented mutability a little bit nicer than Swift, because Swift can cause some confusion in how it handles mutable values. But for now, just know these simple rules, and then we can move on to the next section of this video. All right, now that we've talked enough about variables, let's move on to another concept which is very, very important to learn in any programming language that you're learning at the moment, and those are, or that is, operators. So operators are small functions that are a little bit special in how they're declared, and Swift treats them as such. It treats them a little bit more special than other functions. So let's have a look at what operators are. But before doing that, let's create a simple playground for operators. So let's say file new, and we say file if we can find it. Oh, we can't, because we can't create a file inside this. So let's be in here inside our editor, and I'm going to say Command N. And then I'm going to go ahead and create a playground in here. Let's say blank playground. And then we're going to say operators. But be very careful, because by default, Swift Playgrounds, or Xcode actually, tries to create this playground inside another playground. And that is horrible. It is really awful. Please just use the main folder to create your playground, and also add it to the main Xcode workspace structure as well in here. So let's say create. Now we have operators, and let's do the same thing in here. Let's say import foundation. Okay. After doing this, let's start talking about operators. So let's create two constants in here. Let's say my age, and we say 22, and we say let your age is 20. Okay. Now let's work with our first two operators, and those are the greater than and less than operators. If you have two integers like this, and I kind of expect you to already know what an integer is from other programming language, perhaps that you already know, then we say if my age, then once you have two integers, you can use this particular operator that you can see it says greater than. So the left side should be greater than the right side, your age, and this is an if statement, okay, which I kind of already, actually I kind of expect you to already know what if statements are. So you can see now we're using an if statement and then putting our left hand side and right hand side variables in here and using an operator which is having this kind of syntax. So what this operator is doing is comparing the value to the left with the value to the right, and it returns the value of true if the value to the left is indeed greater than the value to the right, okay? And here then we can say I'm older than you, okay? And then we say else if my age is less than your age. So this is another operator that works between integers, for instance, that says I will return true if the value to the left is less than the value to the right. Then in here we say I'm younger than you, and else, oh hey, we are the same age, okay? So if I'm not older than you and I'm not younger than you, then we should be the same age, logically, all right? You can see nothing is happening in this playground because we don't have automatic running, so I'm just gonna hold my trackpad on this button and then I'm gonna say automatically run. And then you can see that our code is gonna run in here, and the value, basically we got into this branch of our if statement, I'm older than you. Simply because this operator indicated to Swift that the value to the left is indeed larger than the value to the right, returned the value of true, and then Swift fell into this if statement. So that's, these two are the first operators that we're seeing in Swift basically. However, I mean, there are some other very special operators such as the equal operator that we're seeing in here, but we shouldn't really go ahead in explaining that. We're simply assigning a value to a variable in here with that operator, okay? Now, there are other operators such as plus, for instance. Let's say let my mother's age is my age plus 30. So this is an operator that is operating between two integers again from the left hand side and the right hand side. So it simply takes the value to the left and adds the value to the right to it and then returns that result to us, okay? So that's another operator that we're seeing in here, the plus operator. You can also, of course, use, for instance, the multiplication operator, and we can say let double my age is my age, and you say times 2. And as you can see, this is an operator that is sitting between two integers. Again, it takes the integer to the left and multiplies it by the integer to the right and returns the value, and which then gets assigned to this variable. You can say it's 44. If you remember, the age was set to 22 times 2 is 44. So you've probably now seen a few operators in here, and you're wondering, okay, how many different types of operators are there? There are 3 different types of operators in Swift. I mean, I'm not counting these operators. I'm just talking about 3 different types of operators, okay? The first one is called a unary prefix. The second one is called a unary postfix. And the third one is called a binary infix. Okay, so when we're talking about unary, as you remember, let's actually write them down. Let's just say one is unary prefix. The second one is unary postfix. And then the third one is binary infix. Okay. Wherever you're seeing unary, just know that this thing is working with only one value. Again, working with one value, and binary is working with 2 values. Okay, so you can now imagine that this operator, the multiplication operator that is working with 2 values, is indeed a binary infix. It is binary because it's working with 2 values, the left and the right hand side, and it is an infix operator because it's sitting in between. So infix in between, okay, it's sitting in between 2 other values. So all the operators that we've seen so far, the greater than, less than, basically addition and multiplication, are binary infix operators. We haven't seen unary prefix and unary postfix, so let's have a look at unary prefix. As you'd expect, unary works only with one value. So let's say let foo is true. So this is just assigning the value of true to foo. However, if you want to change the value of this true to false and you want to flip it, basically, you use this operator in here, which is the apostrophe operator, which is a unary prefix operator that takes the value to its right hand side and basically negates it. Okay, so you can see in here true became false, simply like that. So this is a unary prefix. It's prefix because it's before the value that comes right after it. Okay. Then we have a unary postfix. So a unary postfix operator is a little bit special. I mean, in all my years of working with Swift, I've been working with Swift since summer of 2014. It is very, very seldom that you create your own postfix operator, a unary postfix. There are some unary postfix operators already built into Swift, but and you use them perhaps quite a lot. However, creating your own postfix, unary postfix operator is something that you do very, very seldom. Okay, let's have a look at a unary postfix operator. Let's say name. And I'm just going to create an optional value. Now, I know we haven't talked about optionals, but just for the purpose of demonstrating what a unary postfix operator is, let's go ahead and write the syntax. Let's say optional, and then we say random. Okay. Now, if you want to grab the value that is inside this variable and unwrap it, we say let unary postfix is equal to name, and then we put this apostrophe after this name. Now, just know for now that what we did in here is that we put an optional value into a variable called name, and optional simply means that this name can either contain no values or it can contain a value. That's what optionality in Swift means, but I've prepared a completely separate playground for optionals, which we're going to talk about a little bit later. However, this you can see now, it goes ahead into this optional value and grabs the internal value and assigns it to this. Okay. So let's say if we in here say type of name, and then we can type of unary postfix. Now they have two different types. You can see the type of this variable is an optional string, and the type of this variable is indeed a string. So this unary postfix operator went inside this optional and grabbed its value out and forced it out and assigned it to the variable to the left hand side, basically using the assignment operator. So this is a unary postfix operator. It comes after a variable and it works only with one variable. So it doesn't have a variable here and a variable there. It is only working with the variable to its left hand side. Okay, prefix, unary prefix works with the value after it. Postfix works with the value before it. Okay, so that's the second example, basically, for unary postfix. Now, for the last type of operator, which is the most common type, and we call them binary infix, simply because they work with two values, hence the name binary, and also infix simply because they sit in between the values that they work on. Okay, so let's say result is 1 plus 2, and this is a simple example of a binary infix operator. You can see it's working with two values and sits in between them. Okay. And another example is, let's say let names is equal to foo, and then we say plus empty space plus bar, and this is another infix binary operator that is sitting between two strings. You can see you may be a little bit confusing. You can say, oh, but if this is sitting between these two strings, what is this sitting in between? Is it a prefix operator? Well, it is not. What is happening here is that Swift is executing this code from the left hand side because there is no parenthesis. Then it says, okay, foo plus empty space becomes foo plus, like empty space like this, and then takes this plus and uses it in between the result of the previous statement and bar. Okay, so that's what is happening inside this code, basically. Okay, so that was an example of a binary infix operator. And as I mentioned, most operators that you use in Swift are going to be binary infix. There are quite a lot of actually other operators as well, but we don't use them so often. Okay, depends again also on your code base. Now, there is another category of operators, which is called a ternary operator. Okay, and ternary is something that is a kind of a hot topic in any programming language that supports ternary, simply because it can be misused and it can cause your code to look very, very difficult to read actually. So what I suggest, what I think is a good idea is always check with your teammates who are working with your colleagues basically in your team, and ask them if they're comfortable with ternary, and if they are, what are the boundaries that they feel comfortable using ternary operators within. Ternary can become very complicated, especially if you're nesting them, if you're using a ternary inside a ternary, and it's just good to check with people what they're comfortable with. Okay, but let's just have a look at a ternary operator. Let's say age is 30. Now, let's say that you want to display a message to the user saying that let's message, and then you want to say if the age is over or equal to 18, then this message should say you are an adult. However, if the age is less than 18, then you should say you are not yet an adult. How do you do this? Well, what you could do is to say let's message is a string, okay? And then you could say if age is more than or equal to 18, then message is you are an adult. Otherwise, message is you are not yet an adult. So this works actually very well, and you can type the message out. You can see now it says you are an adult simply because the age is 30, or if you were 16, it would say you are not an adult yet, or you're not yet an adult. However, there's another way of writing the same exact code. So let's just comment this out, okay? And that is using the ternary operator. So in here, you can see we've defined our variable first, and then we're going using an if statement and an else statement, and then assigning values to that variable, okay? However, you can also say let's message is, then you would put your condition in here. You say condition, okay? And then the format is, then you put a question mark, then you say value if condition is met, and then, so let's put this to the next line, and then a colon in here, and value if the condition is not met. So this is the format of a ternary operator. First, you put your condition in here. So what is the condition? So if the age is more than or equal to 18, so let's just write it. Age should be more than or equal to 18. Then we say that the value should be you are an adult. Then the value if the condition is not met is you are not yet an adult. And that is exactly how you write a ternary operator. So you say, you take your variable that you want to actually calculate the value of, then you say it's equal to, then you put the condition of your ternary operator, and then a question mark. After a question mark follows the value that you want to assign to your variable, should the condition be met, and then a colon, and the value that you want to assign to a variable should the condition not have been met. Okay, and you can see now the message is you are an adult. And if you change this value again to 17, you can see the value will be changed to you're not yet an adult. Okay, so I hope that you now got an idea of some operators in Swift. We've had a look at different types of operators: unary prefix, unary postfix, we have binary infix, and we've also looked at a fourth category of operators, which are ternary operators. And again, just be a little bit careful with ternary operators, because not a lot of developers are actually very comfortable using these. I personally like ternary, especially like in these cases where it's less code, is understandable, is compact, is not so much logic. However, some developers just write them all in one line like this, and that can be a little bit difficult to read. I actually agree. My habits in Swift is to manually break my code down into smaller bits and pieces like this, into different lines as well. And unfortunately, unlike some other programming languages like Rust and Dart, there is no internal analyzer as such. There are no formatter. So Swift code, you need to format it by hand, unfortunately. And it has been 8 years since Swift's come out, and there is still no internal formatter for Swift. Of course, you can select your code and then indent your code with Control I in Xcode, but you cannot have Xcode format your code for you as you type. So that is a little bit of an unfortunate problem that we have to deal with, but it is what it is, and we can just get used to it. So if you want to make your code a little bit more readable, I suggest that you format it a little bit by hand, so kind of handcrafted as well. Okay. That was really it for the operators. So in the next section, we're gonna look at if and else statements. So see you there. Now that we're done with operators, let's go ahead and create a new playground for if and else. So right here, I'm gonna press Command and N on Macintosh, and let's say playground in here. Oops, if I can spell it, and a blank playground, and let's just call it if else. And please just ensure that you're not creating it inside an existing playground. You can see in here it's called operators, and we should change that to be inside our main folder, basically. Okay. And then we say it shouldn't be inside the operators group either. It should be inside the group of our workspace. So create. Now we can collapse the other ones, and in here, just like normal, we say foundation. Not like normal, actually, like usual, I meant to say. So let's talk about if and else statements. We've already seen a few examples of if and else, and if you've already done programming in another programming language, you should already be familiar with what if and else statements are. So it's just a conditional, basically. Okay, let's add a few values in here. So I'm just going to copy and paste some values and place them in here. So some seed values that we can work with. Okay, let's create a simple if statement and an if and else statement. So we say if my name is equal Vandot. So in here, so like this. And so this is using a lowercase v, as you can see in here. Okay, then we say your name is, and then we're going to add our variable within a string, and this is how you do it in Swift. You say backslash and then parentheses, and then you say my name in here. Okay, then in here we can say else with no conditions in front of it, and then we say oops, I guessed it wrong, like this. And then let's do an automatic run for our playground, and we should now come to the oops part because we guessed the name incorrectly with a lowercase v, as you can see in here. So this is a simple if statement. So you compare something with something else, and then you can have an else block or not. You can actually just have an if statement as well, so you don't have to have an else block in Swift. Okay, now you're not limited only to one else statement. You can have else if as well. Okay, so let's just say if my name is equal Vandot with the proper spelling as well, with a capital V. Then we say now I guessed it correctly. Okay, and then we say else if my name is Foo. Now you can see that we have another branch. So we have an if, and then if that case is not met, then the program will fall into this statement. So it's very important to understand that it's not that Swift is executing both of these concurrently. It's executing the first one first. If that condition is met, then Swift goes in here and ignores everything, all the other statements inside the if statements. So all the other else ifs and the last else statement if it is available. So it's just branching basically. Okay, so if my name is Foo, we say are you Foo? And this doesn't really matter what you type in here. I'm just trying to demonstrate how if and else if basically statements work in Swift. And then we can have a final else statement in here and says, okay, I give up. Okay, and you can see that Swift has gone into this branch because name was correctly set to Vandot, and we're comparing it with Vandot. Sorry, it wasn't set to Vandot. I mean, it was set in here, but we're actually comparing it correctly with the correct value in here. Okay. And some people write their if statements a little bit more in like what I call a flipped way. In here, you can see we're saying if my name is equal to Vandot. And so if you're reading it like you would read an English sentence, I would say if my name is equal to Vandot. However, some people actually do it in the opposite way, like this. They would say if Vandot is equal to my name. So this is another way of writing it, an uncommon way of doing this. And a lot of old and a little bit old school developers would do stuff like this. It is not so common in all my years of working as a software engineer. I've seen one or two people preferring this. However, me and my colleagues have been able to convince them otherwise, that we shouldn't do this, and most modern source codes don't do this. However, you may be an exception in maybe you're working at a company where this is the prevalent way of doing if statements, in that you actually put the value that you are testing last, and then you compare with the value that you're expecting first. As I said, this is a little bit uncommon in my experience, but maybe at the company that you and your teammates have decided that this is the way to do it. It is completely equal to this. It is the same thing as this code. I mean, what it achieves is the same. However, the syntax is a little bit different. Okay, so it is up to you and your teammates to decide which way to do. However, if you're new to Swift, I beg you to please don't do this. It is this way that you should learn how to write your if statements. So please don't flip these values. However, if you're a seasoned developer and you know exactly what you're doing, and you and your teammates have decided that in your code base, all your if statements should be written like this, or in just a few exception cases, you write your code like this, as long as you've checked with your teammates and everything is fine, then you go ahead and do it. But if you're learning Swift just now, this is the way to write an if statement. Okay, and this is the way that almost everyone writes their if statements, seasoned or not seasoned. Good. So that was simple. These are some simple if statements, basically comparing a value with another value. But what if you are having a little bit more complicated logic in here? So let's say that you want to make sure that your name is Vandad and that your age is also 30. So you can see the age is defined in here as 20. Let's just go ahead and compare it with 30 instead. Let's say if my name is Vandad, and in here, if you want to compare also the age, you can say and my age is 30, for instance. Okay, then we say name is Vandad and age is 30. Then we say else if my age is 20, then we say I only guess the age right. And then an else statement in here, we can say I don't know what I'm doing. Okay, so as you'd expect, now we're going to go into this line of code. So what happened in here is that Swift started executing this code from left to right, and it said, okay, from left, the name is truly Vandad, and it started comparing the age, and it says age is indeed 20, is not 30, so I'm not going to go into this if statement. So it ignores this if. Then it looks at the code that follows this if statement and says, oh, it's an else. Otherwise, if the age is 20, is the age 20? Yes, it is. Then it falls into this statement and then ignores the rest of the else. So you need to think of if statements as in branches. They get executed separately, not concurrently, and they're basically in a serial order from the first statement. If it fails, goes to the next statement, then goes to the next statement. If any of these statements succeed in trapping the logic, so this one trapped and said, okay, if the age is 20 it is indeed, then the code goes in here. If any of these else statements or if statements do that, the entire rest of this code is then ignored. So this didn't fall into, we didn't fall into this. We did fall into this, and then the rest is completely ignored, regardless of how many else's you have in here. You can say else if, blah, blah, and then another else after that, but all of those will be ignored, okay? Now, just like we have the AND operator in here, the logical AND operator, we also have the OR operator, okay? But you need to be careful with it because you can actually make the code do things that you didn't want it to do. So let me just explain something in here. So let's write an example. Let's say if my age is 20, not 200, or my name is Fu, then we say either age is 20, name is Fu, or both. So what happened in here is that you can see we say, you may be reading this saying either the age is 20 or the name is Fu, but what Swift does really in here says either the name, the age is 20 or the name is Fu, or both of these. So even if both of these are true, then this code is executed. And the reason behind that is that if your age is 20, then the code actually comes here just by default. It doesn't even execute the rest. Okay, so that is the reason that if age is 20, your name might indeed be Fu, and that is what you've written in here, but the code has already fallen into this simply because the first part of the condition was met. So Swift doesn't even execute this part. It says, oh, age is 20, of course, let's go in here. Okay, simply because Swift looks at the statement after and says, oh, it's an or, so I don't have to execute it, simply because I already know that my age is 20, so it falls here. Okay, so it can be either this part, this one, or both. And a mistake some developers make is they think that they can add another else block in here, and that else block will be executed as well. And that is not the case, because as I've explained it before, if statements are serial and they get executed one at a time, if any of them traps the execution of the program, meaning that it actually results to the compiler understanding that, oh, this branch of code should be executed, then the rest will be ignored. So if in here you type else if my name is Vandad, even if your condition is met, which in this case is because my name is truly Vandad, or my age is 20, which it was set up here, if you remember. My name and my age were Vandad and 20 respectively. This code will not be executed. So let's say it's too late to get in this clause. You can see that it won't be executed. It won't be displayed in here. Only this branch is executed simply because my age was 20. Okay, and I can change it actually to foo, and you can see it still gets here first because my age is 20, and the operator after that is a logical or, meaning that, oh, if this or both, and it's since this one is true, it doesn't even have to execute this. Okay, so as I mentioned, or and logical operators, they can get quite complicated, in that if you're working with these operators and also parentheses, then you could create kind of confusing code as well. And if you actually don't use parentheses, sometimes your logic could be completely incorrect. Let me just show you an example. Let's write a code in here and we say if my name is Vandad, and then we go to the next line and we say and my age is 22. Okay, then we go to the next line and your name is Fu, and remember my name is Vandad and my age is 20, your name is Fu and your age is 19. Okay, then in here we're saying your name is Fu, and we know that that is true in fact, or your age is 19. Okay, so we say, and what is this code actually doing? So we say my name is Vandad and I'm 22 and your name is Fu, or you are 19. Do you see what happened in here? So what happened was that, and you can see that this message actually is printed here in our playground, meaning that the code did fall into this execution branch. So what happened, you can say that my name is Vandad and my age is 22, but you can say, well, your age is not 22. How did this code come here? And the reason is because we're mixing ands and ors. And you can see what Swift reads in here. It says, okay, if your name is Vandad and your age is 22 and your name is Fu, is this true? Then looks at all these ands. It says, yeah, your name is Vandad, but your age is not 22. Then it looks at the rest of the code and says, do I have any other logic to follow? And it says, yes, actually, you've written in here either these or that your age should be 19. And it looks at your age, said, yes, actually, your age is 19. So you can see how this could be confusing. For you reading this, you may think, oh, your name should be Vandad and your age should be 22 and your name should be Fu, or your age should be 19. So you may think that this part is executed separately and this part is separate. But since there's no parentheses between these, Swift reads it from left to right, and then there's no precedence between the ands and ors, so they have the same precedence. So it says, okay, this entire thing is the same precedence, and I just execute it from left to right. And this or at the end basically traps the execution branch and ensures that the code falls into the if statement. Okay, so writing code like this could be a little bit confusing. What you might have wanted to write is this instead. You probably wanted to say if, and then parentheses, okay? And then this is your own logic. So you want to basically check your name and age. So let's put it inside parentheses. So we say my name is Vandad. And let's go to the next line. And my age should be 22. So you're basically saying and. So you say my name is Vandad and my age should be 22. Then you go to the next line and you say and another parenthesis, your name is Fu, or your age is 19, like this. Okay, so what is happening in here is and I can see our playground has some problem. So what this really equates to, I mean, if you want to read it in English, you could say my name is Vandad and I'm 22, and your name is Fu, or you are 19. So do you see how this is different? So it says your name, my name is Vandad and I am 22. So this condition should be met, and so should this, because we are using an and, meaning that not only this condition should be met, but also this condition. Then it says, okay, well, this condition is met because your name is Vandad and your age is 20. Actually, oops, we have 20 in here. So that's interesting. So so we wrote 22. That's fine. I mean, let's let it actually be like this. So it says my name is Vandad and my age is 22. So it says, oh, this is not met. Okay, so as soon as this is not met and this is an and statement, it says, oh, I don't have to execute any of this now, because I know that the left hand side of the and operator, the logical operator, is not true. So I'm not even going to execute this. Okay, then if we put an else block in here, then we can say let's say that didn't work so well. Okay, so if you put parentheses between these, you can see that the logic becomes a little bit clearer. So we can change this actually, and we say, let's say or. Okay, and now all of a sudden you can see that this block of code is executed simply because either this should be true, or this, or both of them. And since this part is not true, it comes here and says your name is Fu indeed, and your age is 19. Do you remember age was 19 and name was Fu? Then it executes this code simply because one of these branches is true. Either this, or both. And we know that this is true, so it executes this code. So usually you don't write code actually like this. Thankfully in Swift, usually your code should make more sense inside your if statements, and you shouldn't have too many branches like this with ands and ors and parentheses. But sometimes if you have very complicated code, if you're working with low-level logic, for instance, at your service layer, you might write code like this. So you should be ready to kind of be able to handle and read this type of code. But I completely understand that it is a little bit complicated to look at it if you're just looking at it like this. And usually code like this is prefixed with some comment explaining why we're doing things the way we're doing them. Okay, so that was it for our if and else playground. In the next section, we're going to talk about functions, so we can create a separate playground basically for functions. After working with if and else statements, we can go ahead now and work with functions. We've seen a few examples of functions in Swift before, and hopefully you already know what functions are, so we don't have to go too much into details with functions. But let's go ahead and explore some possibilities that we have with functions in Swift. So Command N in Xcode, or if you're in Visual Studio Code, I think also Command N or Control N on Linux. And we are going to just search for playground in here. Playground, and let's say blank playground in here, and let's call it functions, and then let's create it inside the main group and inside the main folder. Okay, and I think it would be perhaps a little bit better if we change the size in here. So I'm going to go to themes, in Midnight, which I'm using, I'm going to select all of these, and then let's just change the font size perhaps to, let's just say 36 perhaps, or even, yeah, 36 I think is good enough. So we see the code a little bit better, okay? So with functions in Swift, you have the same possibilities as you have in many other programming languages, such as Python and Dart and TypeScript, JavaScript. Pretty much all the modern programming languages have some kind of same syntax and functionality for functions. So let's have a look at a few examples. So let's say we import Foundation. I'm going to get rid of that part to the left, our Explorer. So we can create functions in Swift with the func syntax or a keyword, and then the name of the function, and it should be camel case, meaning that the first word of the function name should all be lowercase, and all the subsequent words inside the function name should have their first letter as uppercase and all the other letters as lowercase. So here is an example of a function that takes no arguments and it has no return value. So let's say no arguments and no return value. You can see all the first word has all its letters as lowercase, and all the other words have their first letters as uppercase that follow the first word. Okay. Then we put parentheses in here, and we can put our arguments in between the parentheses, but this function doesn't have any arguments. Then we do curly brackets, and then inside the curly brackets is the body of your function. And here we're just gonna say I don't know what I'm doing. Okay. And the way that we write these things in Playground is a little bit special, because in Swift Playgrounds, whatever you type as a string will actually be printed inside the Playground's preview. However, this is not how you would actually write Swift code. So you would probably just issue a print statement, okay? But in Playgrounds, this does make sense. So let's just do automatically run in here, so our code gets executed automatically without us having to do anything. And you can see nothing is being printed here, simply because we're not calling or invoking our function. Now, the process of invoking a function is just to tell Swift that you want the code inside this function to be executed. And the way to do that is just you use the function name, no arguments, and then with the parentheses and any arguments that the function expects within the parentheses. Now, thankfully, this function doesn't have any arguments, so we don't have to pass any arguments within the parentheses either. And you can see the value is then printed to our Playground console in here. Okay. Now, we can also have functions that have arguments. So let's create a function that takes any integer value and adds the value of 2 to it. But this particular function is not going to have any return value again. So we're just going to have a look at how to pass arguments to a function. So let's say func plus 2. So like this. And then we take a value, and you can see this is how you specify an argument to a function in Swift. You just type the name of the argument, and then you type the data type. And also there's another way of doing this. I will explain it later. You can have two labels for a variable, one an external label and an internal label, which is something quite unique to Swift. You can have it in some other languages, but not in all. So here's an example of a function that internally creates a new variable. Let's call it new value, and then takes that value and adds a 2 to it with a with a binary infix operator, as we've seen before. But you can see that it doesn't return anything. Okay, and we can say plus 2, and then we can pass the value of 30 in here, and you can see new value will be equal to 32 within this function. All right, so that's how you can basically pass a variable to a function using an argument. Now you can have functions that return values as well. So they do some calculation and then they return a value. And the way to do that is to use this particular syntax, as I'll show you now. Let's say new plus 2, and then we take a value of type integer and we return a value in here. And then we can just say we return a value of basically plus 2. And the return statements in these simple functions that just have one line of code is optional. This is something that Swift has taken from Rust. However, Rust takes it to an entirely new level, in that Rust allows even for you to type some more code in here, and then the last statement inside the function that doesn't have a semicolon will be returned. However, Swift doesn't have that ability. So because semicolons are optional in Swift. So If you don't want to have a return value in here, if you don't want to type the return syntax in here or a keyword, you're more than welcome to do that. Most modern code actually omits return. So if you see a statement like this function is set to return this statement implicitly. All right. And the way to call it is that you can say new +2, and then you pass the value of 30, and you can see the value of 32 will be returned from this function. Okay. Now, you can also have functions with multiple arguments. So let's say func custom add. So we have a new add function in here, okay? And we take two variables. So let's say value1 int and value2 int, all right? And then we return also an int. So what we return is value1 plus value2, all right? So we take two arguments, value1 namely and value2. We add them and we just return them as part of our function declaration. All right. Then we can assign the return value of this custom add to a variable. So let's say let custom added is equal to execute the function of custom add. And for value1, we pass the value of 10. And for the second value, we pass the value of 20. And you can see the result is value of 30. So this function is being executed and its return value is being assigned to this variable to the left-hand side of the assignment operator. Okay. Now you can also have functions that do not have this outside label as it is called. So at the moment, this function has two arguments and they only have one label. This label is used externally, as you can see, at the call site, and also internally inside the function. However, functions can also determine how these labels are created. Every argument can have two labels, external and internal. Okay, so you can see that then internally inside this function, this label is not available. So if you type external, there is nothing available, but if you type internal, then it is available to you. Okay, so let's go back in here and have a look at an example of a function that doesn't have any external labels. All right, so for its arguments. So let's say func custom minus, all right, and it has two arguments, and let's just call them left-hand side and then right-hand side, and we return an integer as well, okay? Oops, and then we say left-hand side minus right-hand side. Now, if you call this function just the way it is, then you can write like this: custom subtracted, and then we say is equal to custom minus, and then let's say the value of 20 and the value of 10 in here, okay? And you can see then easily that at the call site, we have to pass these argument names, LHS and RHS. However, if you don't want to do that, if you don't want to pass an argument name, you can just say custom minus, and then you want to say 20 and 10 like that. Then you have to make sure that Swift gets the external name as underscore like this. So underscore simply means that the call site where you're calling this function from shouldn't have argument names. So you can see now you have to remove LHS and RHS, and then your code will work as expected. Okay, so that's how you can basically ignore external argument names, and just keep in mind that the first part of the argument's name can be its external name, and then if you put a space and then another basically word or sentence, hopefully not a sentence but a few words, it will be the internal name of that argument. Okay, and if you don't have that, the only name you have in here will be available externally and internally. All right, good. So if you're in pure Swift, you can see in here we're at the moment calling this function like custom minus. But if you're in pure Swift, meaning that you're not inside a playground, if you call a function that has a return value, so let's say custom add, and then you say value1 is 20, value 2 is 30. In a playground, you just get the return value, and the return value of this function will be displayed here. However, if you're in pure Swift, meaning that you're not inside a playground, then doing this will actually give you a warning telling you that you're calling a function without consuming its result. The reason we're not seeing that warning in a playground is that playgrounds consume the result of all functions implicitly and type them out here in the preview. But inside pure Swift code, when you're writing like iOS code or macOS code or watchOS, whatever, you're basically, you don't have a playground in those codes. It's pure Swift code. So you need to consume these values, meaning that you have to assign them to something. Okay, like that. And then you need to also consume this somehow. So even if you type code like this, Swift will complain saying that, hey, you're assigning this to added, but you're not using added anywhere. So what's the point of doing this function call? All right. So if you want to write a function in Swift that does produce a value, however, the person or the call site where you're calling that function doesn't necessarily have to consume that value, you can mark that function as discardable result. And I'll show you how to do that. So let's go ahead and create a my custom add function in here. So we say my custom add. Okay, and then we have two arguments in here that are externally not named, but internally they're called LHS as in left hand side. And then we have RHS in here. Okay, and we return integer as well, and we say LHS plus RHS. So if you want this function to be able to produce integer, but the call site, the caller of this function, doesn't have to consume that integer, you need to mark this function as discardable result. Doing this in a playground doesn't make any difference at all, because as I mentioned, playgrounds consume the result of all functions implicitly. However, if you're in pure Swift, this will make a lot of sense. And to be honest with you, we could actually have a look at this. I mean, now I'm improvising a little bit. I'm just going off the script, but let me just create a simple iOS project in here. And let's say my app. And then we're just gonna save it on desktop. It's fine. I don't really care where it is saved at the moment. So let's just save it. And let me just show you how this looks inside a, for instance, Swift UI application. So if you go into our app in here and say, what should we do in here? Let's say, perhaps we have a window group in here. Let's go to content view. And now we have a Swift UI application though. So it would have been better if we actually created a, let's just create a file in here, a Swift file. Let's say my service. Okay. And in here, let's just say that we have a, what should we do? Let's say struct person. Okay. And then we create a function in here, just like we're learning now. We say get age. And this is not really how we write normal code anyways, but this is for the purpose of demonstration. And then we have another function that's called do something. And then we say let age is get age. So we call that function. Now, if we leave this code like this, let me just actually change this to, yeah, that's fine. If you try to compile this code, you can see that now we're getting initialization of immutable value age was not used or something, was never used, okay? And even if you write your code like this, you will get a warning saying result of call to get age is unused. So this is the warning that I was just talking about. Inside a playground, you don't get these warnings, but inside a pure Swift code, you get these warnings. So the way to fix that is to prefix this with discardable result and then compile your code. You can see then it's working as expected. However, if you assign this to a variable, you will get the warning anyways, because you're assigning it to a variable that you're not using later. So this discardable result doesn't fix this issue. However, it fixes the issue of you calling this function without assigning its variable to any values. Without assigning its value to any variables. Okay. Good. You didn't have to create this project. I mean, this was just a test. Okay. So that I can demonstrate what I meant in this case. Now that we have that, we can just type my custom add, and then we can just say the value of 20 and 30 in here without having to worry about consuming the result of this function. Now you may be thinking, but why would you write a function like that? Well, some functions, for instance, in service layers inside an application may do some complicated work, and they may produce a Boolean value indicating whether it was successful or not. However, it's not always that you actually care about that Boolean value, and you can call that function without caring about its result. In that case, you can prefix the function declaration with a discardable result, as I showed you right here. Okay. Now, functions can also contain their own functions. So this is something that not many programming languages support. Dart, for instance, supports it, and you can also have something like that in Rust as well. So let's have a look at that. So we say func, do something complicated with a value, and you can see width is the external argument label and value is the internal argument label in here. Okay, and this function we can see returns an integer. Let's break this parameter down like this, and then in here we say we have another function inside this that actually does the logic. Okay, so we say main logic with a value, and returns an int. And in here, we just say value plus 2, okay? So we're not really doing anything complicated. We're just plussing the value with 2. However, this function, do something complicated, contains another function that does the actual logic. And this function then can call this function internally, but no one else in the entire application can call this function. This function is only available to this function because it is written inside it, okay? Then what we can do is say return the main logic. We call that function, we say value plus 3. Then in here, we can go ahead and say do something complicated with the value of 30. So what happens is that the value of 30 goes in here. Then 30 will be plus 3, 33, and then we'll go into main logic. So 33 plus 2 will be 35, as you can see, printed out here, okay? Now, arguments in Swift for functions can also have default values. So you can have, for instance, a function that says func get full name, as you can see in here. Okay, we say first name is the name of the argument internally and externally, and it has the default value of foo. And then we can say last name is a string, and it has the default value of bar. Okay, and this function returns a string, which is like this. We put the first name in here and a space and last name. All right, so we're basically calculating a full name using this syntax. Now you can call this function now in so many different ways. Actually, you can call it in 3 different ways, I would say. One is without arguments. So because both the arguments that are required for this function have default values. So you don't have to pass any arguments to it. And you can also mix and match. You can, for instance, pass. Actually, I think you can call it in 4 different ways. Yes. So you can also call it only with the first name if you want to. So you can say Baz. You can see now the result will be Baz bar. So the last name is picked from the default value and the first name is overwritten by the value at call site. And you can also say get full name. And then we say only pass the last name. Let's say foo. So now the value will be foo, right? And then you can also call it with both parameters. So you can say first name, and we say Baz, and last name, we can say Cox like this. All right. So you can see now the result will be Baz and Cox in here. All right. So these were just some examples of how you can create functions in Swift. Now, we will actually look more at functions and how to create more complex functions perhaps, but this is like the basic structure of how to create functions in Swift. And there are some functions, of course, that are a lot more complicated than what we have in here, but the complication is usually inside the function itself. The function header or the function signature is usually one form of these things that we've written in here with some arguments that perhaps have internal or external names, or some arguments that have no external names but internal names, discardable result, and pretty much that's it really. So that's about functions for now. In the next section of this video, we're going to have a look at closures, which are kind of special functions. So see you there. Now that we've finished talking about functions, let's go ahead and talk about a special kind of function, which is with local variables, and it is called closure. So before we do that, let's create its own playground. So I'm going to go here and say Command N and type playground in here, if I can spell it. And in blank playground, I'm going to create closures in here and ensure again that it is created in your workspace and not inside another playground. Then I'm going to press the create button, and let's say in here that import foundation. Okay. Now, closures are available in many other programming languages such as Python. They're also available in Dart, for instance, and in I would say Rust as well, and of course JavaScript and TypeScript. So most modern programming languages have closures. And what closures really are, they're special types of functions that are created in line so that you can actually pass them to another function, for instance, and they can hold a function. So you could pretty much say that they're function references kind of, but not really. But I think the easiest way to explain closures is to demonstrate how they look like, how the syntax looks like, and I think after that it will be a lot more it will be a lot easier to understand what basically they do. So let's go ahead and create a closure in here, which is supposed to add two integers together and return a result. So if you were to do that using a function, you would probably do add, and then you would say like left-hand side integer, right-hand side integer. And you could perhaps also remove the external label of these arguments so that you don't have to actually write LHS, RHS when you're calling this function. Then you would say that this function returns an integer. Then you could say left-hand side plus right-hand side is that function. However, if you want to assign this to a variable, for instance, call add, then you could say, let's actually comment this out. Then you could say let add. Then as you would do with any other variable, as you could do actually with any other variable, you don't have to do that, but you need to tell Swift what type of data type this function is accepting. So you could say let add, and then you would say colon, and instead of, for instance, saying this is an integer equal to 1 or this is a string equal to foo, you could say in here that this is actually a function, right? And then you say, okay, it accepts an integer, and actually it accepts two integers, and it returns an integer. Okay, so this is you defining the data type of this variable or a closure. Okay, and then you could say it's equal to. So now you've defined the data type. Now you actually create the function. Then inside the creation of the function, you just create curly brackets as you would do any other function. And in here, then you get your data. You say left-hand side is an integer, right-hand side is an integer. Okay, and you return an integer. And then you say in like this. So let's actually break this down, bring it to the next line like this. Okay, so this is where you're defining the data type for add, and this is where you're actually assigning it to a valid function. All right, and let's change our playground to automatically run in here, and then you can see Swift is telling you that you're not returning anything in here. So let's just say LHS plus RHS. Okay, and these values that we have in here, they're just internal argument names, so they're not actually being used externally. Okay, now that we have add, you can see it tells you that add is actually a variable that points to a function which requires two arguments and returns also an integer. So you could call add just like you would call the add function. So if you say add 20 and 30, you can see that you're pretty much just calling that function that is beneath this add variable, you could say. Okay, so you get the result of 30. So now that you know how to create one of these functions, closures, you can see you can create it inline like that. You can actually pass any one of these functions like these, which you create inline, to another function. And that's where the power of closures really come to play. So let's create quite a useless function that we call custom add, but it's just there for the purpose of demonstration of closures. So this custom function, what it does, it takes two integer variables, and then it uses another function that you give it. So you pass a function to this function, and that function that is passed to this function will do the actual addition. And our function that we will create now will just call that function. All right, so it will just demonstrate how you can pass a function to another function and how you can create a function on the go or on the fly. So let's create this custom add function in here. We call it custom add like this, okay? And this custom add, so it takes two values. We call them LHS, left-hand side, all right? And then we say RHS, another integer. And as the second parameter, we want actually a function that does the addition for us. So this custom add itself doesn't really do the addition. It will delegate the addition task to the given function. So just like you would define any other variable, like here, you basically type the external argument name, internal argument name, or just one argument name that is used externally and internally. And then you would define its data type. This is very similar. You see defining a data type with a column. We did the same thing in here. So we want basically a function that takes an integer or two integers and returns an integer. So let's go ahead and define it here. We say the external label for this argument is using. So we can say custom add, kind of like this, custom add 10, 20 using, like this, okay? So the external name of this argument is using, and internally it's called function, all right? And then we say this function requires two integers and it returns an integer. All right, so this is just like defining any other variable inside or argument inside your function signature. You just say external external argument name, internal argument name, its data type, and its data type is pretty much just a function with two integers as arguments and returns an integer. Okay. After doing that, we close the arguments list with the closing parentheses, and now we have to define the return value of our function. So this custom add function at the moment, you can see it's not returning anything because the parenthesis ends here, but we don't have any of these pointers in here. So let's say that our function also returns an integer, okay? Then inside the function itself, inside this custom add function, we need to return an integer, but it is this function that does the calculation. So let's just call it just like you would call any other function. So we just say function, LHS and RHS. And again, this is just a label. It doesn't have to be called function. You can just call it f if you want to, or you can just call it l, h, whatever you want to. But I really suggest that you don't name your variables with f or h or l. It's just better just to call them something that means something as well, okay? And in this case, function I think is quite a good name for it, but you might disagree. So we have function now, and you can see it is being called by custom add, and its result is being returned from custom add. And you can call the custom add function as I'll show you now. So let's say custom add, you can see we have 3 parameters. Okay, I'll break them down here. Now, the left-hand side, you can see it doesn't have any external labels. So let's just say 20, and then we say 30. Now this using is going to be very interesting because usually when you come here, Swift is going to be able to substitute this for you using a trailing closure syntax. Okay, so if I go here and press enter, you can see all of a sudden the using label was just completely removed. Now, if you go ahead in here and you just want to see, okay, but what is happening in here? What you could do is instead go ahead and create a function in here, because this should be a function. You see, it's telling you it needs to have 2 arguments and a return value of integer. You could create a function yourself and then say left-hand side int, right-hand side int, and it should return an int. And then in here, and also please don't forget the in syntax, because it needs to know, Swift needs to know where this function actually starts, its body, okay? Then in here, you say left-hand side plus right-hand side. So after doing this, you can see now the value of 50 being printed to the Playground console. All right. So that's what you could do manually. However, what Swift does is that if it sees an argument at the end of a function, you can see, an argument at the end of the list of arguments of a function. So here we have left-hand side and right-hand side, and then we have a closure that has to be passed to this function, but this closure is not like the first argument, it is the last argument. And Swift does something called a trailing closure syntax. What it does is that, and we can actually do it by hand. We can go in here, you can see it removes this argument name first of all, then it puts an ending parenthesis here, and then removes this column. Then you can see this should pretty much do the same thing in here. So, and then it of course removes this parenthesis in here as well. So now you can see the parenthesis ends here, and then there's no using argument name, and then there is a trailing closure right after the function is finished. So we can actually put this, maybe here actually it's good, yeah. And we can clean this up as well a little bit like this. So this is the trailing closure syntax in Swift, meaning that if there is a closure at the end of a function, then it doesn't necessarily have to have all the bells and whistles around argument names and etc. Okay, it can just omit right in the argument name, close the parenthesis right after the argument before it, and then creates the closure right after this function call, and it will be passed into this argument. Okay. So now you saw that we created a closure, which is this one, and we passed it to another function, which is then being used to calculate the value of 20 plus 30. Okay. Now, Swift also has a very handy functionality where it can infer data types based on the function signature. Now, I'll explain this a little bit now. You can see in here, this function custom add already has defined that the closure being passed to the function argument has to have the data type of integer, and it has to have the data type of integer for both of its arguments and also integer for its return value. Now, in here, then you could say, okay, but if this function already knows that it should be integer and integer, maybe I could just remove these. Well, you kind of would be right. You can just go in here and say left-hand side, right-hand side, and then in. And if it runs your code again, you should basically see 50 again. You can see in here. So we could maybe change this to 30 just to see that everything's working as expected. There we go. We got the value of 60. So you can remove these data types, right? So if let's actually copy this code and bring it a little bit down here and remove the data types like this, and we can remove the return value as well. So that's the first step of cleaning up the code that you can do. All right. Now, a lot of developers would call this actually clean up. They would say, oh yeah, you should remove these data types. They're not so good, etc. However, I've worked on a lot of big projects that have been written purely in Swift. And once your code base gets very, very large, that you have maybe thousands of source files, and then every of those source files has hundreds of lines of code on average perhaps written in them, I've noticed that, I mean, after doing a lot of benchmarking on the compilation and asking Xcode to tell me exactly where things are taking time or the most time during the compilation, it's been where the compiler has been trying to figure out data types. So the less information you give to the compiler, the more time it takes for the compiler to compile your code. So here you can see we have a lot of information for the compiler. We're telling it that this closure has 2 arguments, integers, and it's returning an integer. So the compiler doesn't have to figure it out on its own. So it says, okay, then I just calculate this and return the data. However, here the compiler has to ensure that, yeah, okay, so the function, it has to go back to the custom add function and say, okay, this shouldn't have 2 integer arguments and it should return an int. Then it comes here and checks that, because we haven't even told it what return value we have. Then it says, okay, there's some data here, some data in here, and they have to be plus together. Can 2 integers be plus together? Okay, so it has to figure out all of this on its own. So it has to basically look up the plus function or infix binary operator to ensure that that actually exists between 2 integers. So you can imagine all of this basically puts strain on the compiler. And of course, if you have thousands and thousands of these functions where the compiler has to figure out things on its own, then of course your compilation is going to be drastically slower. Now that we're talking about stripping information from the compiler, there's also one more step that you can take in order to make your code more compact and more difficult for the compiler to guess. But on smaller code bases, this doesn't really make any difference, to be honest. So let's actually copy and paste this code right here. What you can do in this case is that you can completely remove this information from here. And in Swift, you can tell it that you have 2 arguments in here by prefixing every argument with its index and dollar. So you can say $0 plus $1. So dollar in here will mean basically an argument at an index of 0, which is this guy, and an argument at the index of 1, which is this guy. And then you're just plussing them together and returning the value. So some developers will then be like custom add 20, 30, and then we'll do it like this. So it is completely up to you and your teammates how you like to format your Swift code, because unfortunately there is no real official linter and official code formatter for Swift, as I mentioned before. So there are some community guidelines how to format code, but you can actually see code written like this sometimes. And to be honest with you, for me at least, this is readable. I have nothing against it. But if it was me writing this code, I would probably write it a lot more like this, just because of the experience I've had with ensuring that the compiler can compile my code faster on larger code bases. But writing code like this is also completely fine, dependent on the context. All right, good. Now that we've done that, let's have a look at passing some sort of special closures to functions. Before we do that, let me just write some code in here as like a preparations. Let's just define an array in here and say, and I'm also aware that we haven't worked with arrays yet, but if you've worked with another programming language, you already probably know what arrays are. So it's just like a homogeneous, actually they can be heterogeneous as well, but it's just like a series of data, okay? Let's just leave it at that. Let's just say ages are 30, 20, 19, and 40. So now we have 4 integers placed inside this array. Okay, now you can see in here, we can start sorting this array. Let's say that we want to sort things ascending and descending. So we say sorted, okay? And you can see it has an argument in here. There's a function called sorted using. Actually, let's just say sorted by. Let's say sorted by. This is a little bit better. And you can see it expects a function. So it says, give me a function that takes 2 integers, and then it can throw, and we haven't talked about throws yet, and it should return a boolean. Okay, so let's go ahead and see how we can implement this function. So we say LHS integer, RHS integer, and it should return a boolean. Okay, and then actually it throws as well, but we don't have to write that. And then we say in. All right, so in here, let's just return true for now, and let's see what happens. Okay, so if you return true in here, let's see the data that is being returned in here. It says 14, 19, 20, 30, so it really didn't do anything. So, but if we say in here, LHS should be more than RHS. Okay, and this is, of course, it's going to return a Boolean value. All right, now you can see what happened is that the result is that the return from ages.sorted is an array that is sorted descending. So as long as left hand side is more than right hand side, if you're basically doing this comparison with greater than, then you're sorting the array descending. And you can read the documentation for sorted by as well to understand how it actually works. Okay, it says when you want to sort a sequence of elements that don't conform to the blah blah, let's see. And that returns true when the first element should be ordered before the second. So it says return true when the first element should be ordered before the second. And what we're saying is that if left hand side is more than the right hand side, then it should be sorted before. And that's why we're getting descending. And if you change this to less than, then you should expect your array to be sorted ascending. Okay. So what I'm trying to do in here is that we have a lot of code in here. You can see that takes left hand side and right hand side, returns a Boolean. However, there, as you may guess, this particular operator, which is a binary infix operator, already takes a left hand side and a right hand side and returns a Boolean. So if we were to implement this operator ourselves, we would probably write it like this, right? Function less than, and we say left hand side integer, right hand side integer, and it returns a Boolean. And we say left hand side less than right hand side. However, please don't do this because this actually goes into something called an infinite loop. It will go into an infinite recursion of itself because this function will just call itself. All right, so what I'm trying to say in here is that if you look at this function signature, you can see it is exactly the same as this function signature. So, and since this is a function name in itself, why don't we just pass it to this? So instead of writing all of this, why don't we just do this, right? Because it is the same thing. It is the exact substitute of this. So let's remove that and remove this code as well. And you can see actually you can do that. So by passing a function or an operator, a binary infix operator to this argument, you're substituting pretty much all this code that we wrote in here. So a lot of newcomers to Swift will write code like this, but a lot of seasoned developers know that this binary infix operator already is a substitute for that closure. So you can do the same thing for more than. So this is going to sort descending and this is going to sort ascending. So you can see here descending sort and ascending sort. Okay. So that was one example, or rather 2 examples of passing operators to closures. Okay. Now let's move on to the next example. And for that, I'm going to go here to our custom add function and I'm going to copy it right here. And let's paste it down here. And let's call it custom add 2. And if you remember, I mentioned that we have this syntax called basically trailing closures in Swift, meaning that if there is a closure at the end of the function signature as its list of arguments, then Swift helps you out by allowing you to remove the argument label and allowing you to trail basically the closure at the end of the function call, as we saw in here. So you don't have to type using in here, okay, which is something that we otherwise would have to do. All right, like this, using this and then parentheses. So since that function, since this argument is at the end, then we don't have to do all of that work. However, if you make a mistake of putting this argument, for instance, at the first place or in the middle, not at the end, then let's see actually what happened in here with a comma. Then calling this function, you will have to do something like you have to do mental gymnastics like this, custom to, and now you have to pass your closure like this. All right, and then you say LHS and RHS, and then you say LHS plus RHS, and then you have to go in here and say 20 and 30, for instance. Okay, so I don't know about you, but this code looks a lot dirtier to me than it should be, because it has a lot of labels and it is like it is a function or a closure before these values being sent here. So to me, this doesn't look very clean, to be honest with you. And you can, of course, make this a little bit shorter as well. You can remove that code that you've written in here, and you can say $0 plus $1, and then do it like this, and then go 20, 30. So it becomes a little bit more readable if you do this. However, it's still not as clean as it can be. So you can also put perhaps the value of 10 in here just to demonstrate that this is actually working as expected. So now this should be 60, okay? So that's why I really suggest that you take advantage of trailing closure syntax in Swift and add your closures if you have a closure argument at the absolute end of your argument list, okay? Now, we've seen how we can pass operators like this to a closure parameter of a function. But as you'd expect, since since operators are normal functions, you can also pass normal functions to closures. So let's have a look at an example. Let's create a function in here. It's called add 10 to, and then we get a value of integer, and we return an integer, and we just add 10 to this value. All right, and then we can have another function in here called add 20 to, and then we just add 20 to whatever integer parameter that is passed to our function. Now we can then have a function in here called do addition. All right, and then it takes a value, and we externally call it on, and we say do addition on value. All right, int. And then we want to have a function that basically takes this value and does some addition with it and returns an integer, okay? So we say using a function, using function, and this function should take an integer as its only argument, and it should return an integer, okay? So that's, so it shouldn't take two integers basically, simply because we want to pass one of these functions, which has only one integer as its input, to this closure in here, okay? And our function should return an integer. Then what it's going to internally do is going to invoke that function with this value and return its result as the result of our function. We could have written return in here, but it is not necessary in modern Swift, okay? Now let's go ahead and invoke this. Let's say do addition, and then we say on the value of 20. And in here, using, you could imagine that, well, you could create a trailing closure in here, you can see, and we say value, and we could say value plus 30, okay? So what is going to happen in here is this value of 20 is going to be passed here to this closure, and it's going to be 20 plus 30. So let's see if Swift Playground is going to be able to recover, and you can see 20 plus 30 is 50. Now, instead of doing this, instead of passing this basically inline closure to this using argument, you can, as you'd guessed, pass a reference to any of these functions that has the same, both these functions have the same header or definition as this closure. They take an integer as their argument and they return an integer. So let's say that we say add 10 to, like this. And you can see now is this function internally going to be passed to this. So this function is going to be add 10 to, and it's going to be invoked with the value of 20. 20 plus 10 is going to be 30, which is then printed right to our playground console. Then let's copy this and go here, and then we say add, do addition again on 20, but add 22, which is our other function up here, okay? And then we have the value of 40 printed to the screen. Now, this function is a little bit strange, as you can see. I mean, not strange actually. They don't have external argument names. So if you change that, and so that the value is actually the external argument name, then you have to change the signature passed here as well. So then we should say add 10 to with value, and add 22 with value. So just make sure that your function signatures are basically the right signature according to how you've defined those functions in here. Okay, very good. I think this suffices for closures. Really, closures are, as I've mentioned, kind of inline arguments usually that you pass to another function. You can define closures by assigning a function to a variable, and then you can pass that variable around to other functions as well. So really, when a Swift developer is talking about closures, they're just talking about functions that are inline. So they don't have the func keyword before them. So any function that doesn't have the func keyword behind it is in fact a closure in Swift. You could pretty much just say that, okay? Good. We're done now with closures, and we can now move on to talking about a little bit more fun stuff in Swift, namely structures. See you there. So we're now done with closures, or at least for now. Let's go ahead and start talking about structures. I think from this point on in the course, we're going to actually have a little bit more fun, since we've talked about the absolute basics of Swift up to this point. And you can imagine that the basics are not so fun. I think for me, at least personally, the fun part comes in when we have enumeration, structures, classes, protocols, extensions, generics, all that. So let's get started with that. I'm going to go in here and let's do Command N in Xcode, and let's create a blank playground, and we're going to call it structures. Okay, structures. Again, a warning, please create this not inside another playground. Just change both the group and the folder to the root of your, or to your workspace basically. Okay, and then we say create. So we have structures, and let's import foundation as usual. I'm gonna get rid of the Explorer to the left hand side. So structures in Swift are a way of grouping data together and giving some sort of a name. Structures in Swift are value types, and meaning that when you assign an instance of a structure to another variable, then the data inside that structure gets copied over. So you don't actually get you don't get the same reference using two variables. I know I mean, this could be a little bit difficult to understand for especially those who are not familiar with value types from another programming language, but don't worry about it. I'll explain it all soon. So let's just first of all go ahead and create our first structure, which we're going to call person. Okay, struct person. And in here, when you create a structure, you can then go and instantiate it. So you can create an instance of this person, such as let foo is person. Okay, and you can see then you do this syntax in here with parentheses. And inside this parenthesis, you would eventually pass any arguments that the constructor of this structure requires. At the moment, the structure doesn't have any values inside it, so it doesn't contain any properties. So that's important to understand the term property. It doesn't have any property. And we could go ahead and create properties. And the way to do that is using the let or var or keywords in here. So you could say we have a constant in here called name, and its data type should be string. And all of a sudden you see your playground is going to give you an error in here. If you have automatic running as well, especially, it tells you that you are missing an argument called name. Let's just ask it to fix it for us. And we say name, okay, it's a string, and we say foo in here, okay? Just like having the name property in here, you can create another property, for instance, called age. And we could say this is an integer. Now you see playground will give you another error in here saying that you're missing the age argument, and we can ask it to fix it. And it says age, okay, then we say 20 in here, okay? Now you can see we've created an instance of person with two properties, name and age. All right. Now you can access these properties using something called a dot notation. So if you go in here and say foo.name and foo.age, just like that, Swift Playground is going to be able to print and consume the results of these and print them to the console, as you can see in here. However, if you're writing pure Swift code, this will make no sense. You're basically saying foo's name, but you're not doing anything with it. But since Swift Playground implicitly consumes the result of all variables and all return data, it is being printed in here. But in Swift, it is more likely that you would say let name and age is foo's name, and then plus foo.age inside like a string or something. Okay, so I'm not going to write all of that, but you get my point. So you have to consume it in another way if you're not using Swift Playgrounds. But just know that you can drill down inside a structure using this notation, which is called a dot notation. You just put the name of the variable that points to structure and you say dot, and then you get the properties out. Okay. Now, you can also have custom constructors for your structures. As you can see in here, we didn't actually have a constructor. The constructor for structures is always created by the compiler itself, and this is one of the reasons a lot of people prefer to use structures in Swift rather than classes, simply because you don't have to create constructors for them. Constructors are implicitly created by the compiler. So if you add another property in here, there will be a new constructor, so which will replace the old one that had only name and age with the new arguments in it as well, or the new property in it as well. Okay, so that's one of the properties of Swift structures, that they have implicit constructors. You don't have to create yourself. Now, if you do want to create a custom initializer or constructor for your structures, you can also do that. I'm going to show you how. So let's create a structure in here, and we say Commodore computer. Okay. For those of you who are old schoolers and have worked with Commodore, this is one of my favorite computers. It was actually my first personal computer, a Commodore 64. Okay, so we create a Commodore computer and we say let name. Okay, and your name is, the name is supposed to be something that you designate. It could be like my lovely Commodore or whatever. And then we have another property in here called manufacturer. I always have difficulty writing it and spelling it. And we say this is a string. Now, in this case, if someone wanted to go ahead and create an instance of Commodore computer, they would probably go, let's say Commodore 64 is equal to Commodore computer, and they would say name, and then they would say my Commodore, and the manufacturer is always going to be a Commodore. Okay, so a Commodore 64 has a manufacturer of Commodore, and also Commodore 128 is going to have my Commodore 128. Okay, so both of these instances have the manufacturer as Commodore. Then you could ask yourself, okay, if you have a Commodore computer who always has its manufacturer equal to Commodore, why should the call site, meaning this part, pass this value over and over again? So you could create a constructor that always sets this value for you to Commodore. Let's go ahead and have a look at how you could do that. So let's go ahead and say we have an initializer. You can see in here. Okay, so you just type init, not func init, except you just type init. Init implicitly becomes a function. Then since it is a function, then you have your argument list and then your function body. Then as you can expect in here, you just want the call site to pass the name to you. So you just say name string, but you omit the manufacturer from the init initialization. So you say self name is name. All right, and you need to prefix this name with self, simply because if you say name is equal to name, it just thinks, you see, it highlights the name. It says name is name. It's the same thing. You're not actually referring to the name inside the structure. So you have to say self.name. So Swift understands you're referring to this name being assigned the value of this argument. Okay, and then you say self.manufacturer is Commodore. So you yourself take it upon yourself to assign a value to this property. Okay, then you can go ahead and say let C64 is Commodore computer, and you can see the only argument that the call site has to pass to you is the name. So you say C64. Then you can say C64 name and C64 dot manufacturer, and the values will be exactly as you'd expect them. So it'll be C64, and the manufacturer will be Commodore as you've set it inside the initializer or the constructor of this structure. Okay. Now, there are other ways of actually doing that. So what you could have done in here, instead of having a custom initializer in here or a constructor, you could have commented this out and you said a manufacturer equal to Commodore, like this. Okay, so this would have achieved the exact same result. So you don't have to have a custom initializer if you want to assign values to your properties that don't change pretty much. Okay, so just keep that in mind, please. So there's another way of doing that. Okay, now we've looked at that. Let's have a look at another type of properties that you can create inside your structure, and those are called computed properties. I'm going to show you the syntax for them. Now for that, let's go ahead and create a new structure. So we say struct, and we call it person2. Unfortunately, we've already consumed person in here, so we can't have another structure called person unless we go ahead and comment this out, but we're not going to do that. Let's just create a person2. But please, if you're working with production level applications, please don't do this. Please don't call your structures or classes 2 or 3 or 4 unless your business logic requires you to do that. Okay, which in all my years of software development, I've never had the requirement of calling something 2 or 3. So just keep that in mind, please. This is just for the purpose of demonstration in this playground. Okay, so let's go ahead and create a person structure in here with a first name and last name. So I'm just going to say first name is a string, and then I'm going to copy this and go ahead and change first to last. So we have first name and last name. Now, let's say that your requirement in here to create a property for your person2 structure called full name. So this full name should always be equal to the first name and the last name with a space in between it. So what you could do is to go ahead and create an initializer for your person2, and you could say full name. And you can see in here, you can't just say full name is equal to first name and last name, because you will get actually an error in here. This syntax is invalid. So let's actually have a look at here. Cannot use instance member last name within property initializer, because at the point of you assigning this value to full name, first name and last name are not known. So even though this might make sense just looking at it, but Swift compiler doesn't work that way. So you could be tempted to go ahead and say, okay, I will create an initializer in here, and I say first name is a string, last name is a string, but I don't want you to pass me the full name. I can figure it out on my own. So you say self first name is first name, self last name is last name, and self full name is a string consisting of another string, which is the first name, which is passed in here as a parameter, and then we will have a space and then last name. So this actually is completely valid Swift code. There's nothing wrong with it, I would say. However, there is a better way of doing that, and that is called computed properties. So what you could do is to completely remove this initializer in here, and then change this let's to a var, and then make it a function. So this is a computed property when you have a variable inside, and then for the variable value, you actually have a function in here. Okay, and in here you could just say first name and space last name. So now you actually did what we wanted to do from the beginning when we said equal to. You see, we tried to do this, but that didn't work. All you have to do so this is what we tried to do at first, but in order to get this to work, you have to say first var, define the data type, remove the equal sign, make it a function, and then put the logic in here, and that will be valid Swift code. Okay, so you can now go ahead and create an instance of this structure. Let's say let foo bar is person2. We say first name is foo and last name is bar, like that. Then we say foo bar first name and foo bar last name, and then we can have access to a property called full name, just like you have access to first name and last name. You can see first name is foo, last name is bar, and full name property or computer property is set to foo space bar. Okay, and this is how computer properties work. All right, now structures, the way they're created is that they don't inherently allow mutation, right? So let's have a look at an example. Everything we've created so far has been immutable, meaning that we haven't been able to change the structure internally. We've just instantiated those structures and assigned some values to them. And after assigning values to them, we couldn't actually change those values. So we can't go in here and say C64 name is blah. So this is going to give you an error because this is not assignable. All right, you can see we got an error in here. Okay, so how do we make sure that we can create structures that are mutable so you can actually change them after you create an instance of them? So let me show you an example of creating a function that can mutate a structure. Okay, so let's create a car in here, car structure, and then we say current speed is in an integer. Let's just say current speed, then we can pass 10 or 20, meaning 10 kilometers an hour, for instance. Now, what if you want to have a function in here, func drive with a specific speed, okay? And then in here we could say driving. But what we want to do is to change the current speed of this car with the speed that is given inside the drive function. So if you say current speed is speed, you can see now you immediately get an error in here saying that you cannot do that. So it says cannot assign to property current speed because is a let constant. So you might say, okay, let's fix that. Let's change it to var. Then this will not work either because you can see now you get another error saying cannot assign to property self is immutable. So the suggestion that Xcode Playgrounds is giving you, it says mark the method as mutating. So let's fix that, and you can see the suggestion actually works. So this function is prefixed with the keyword of mutating, allowing the car instance to be changed. And the reason behind all of this mental gymnastics is that structures inherently are immutable, meaning that, and they're also they're also value types, meaning that once you create an instance of it, it's sitting in the stack and it shouldn't be changed. But if you create a mutating instance, then a mutating function, you're basically bending the rules of how structures are actually working, and it's completely valid Swift syntax as well. So it's nothing illegal. But I think actually in all my years of working with Swift, it is not so often you want to do something like this. But there are a lot of classes inside Swift itself that have mutating functions. But usually when it comes to structures, you don't want to mutate them. But sometimes you have valid reason to do that, okay? So let's go ahead and create an immutable car. You may be thinking, okay, but what does that mean? But this is a mutating function. I'm going to show you what I mean. Let's create an instance or a variable car called immutable car, and we're going to say it's an instance of car, and this current speed is 10. Then you can go ahead and say immutable car, and then you could say drive, and with the speed of 20. All right, you can see now you're going to get an error in here saying that, oops, you're calling a mutating member on an immutable value or variable. And it says immutable car is a let constant. So what happened here is that since immutable car is let, you can't actually call a function that changes the internal value of that let constant. And this is one of the very subtle differences between let and var in Swift. If you remember when we talked about variables at the absolute beginning of this course, I mentioned that there are some small differences between let and var, which we can't explain right now. And this is one of those differences. What Swift is doing in here is saying that, okay, you create a let constant in here, and you're saying that it is equal to an instance of a structure, but then you're going ahead and trying to change it by calling a mutating function on it. If this function wasn't mutating and we didn't have this code in here, you would be able to easily call it. You can see no problem. But if this function is marked as mutating, you're telling Swift that this function is internally going to change the data inside the structure. And since this is a let constant, it is not allowed to change either. So by changing, I mean, you're not either allowed to do this. So you can't do this, and you can't change it internally either. So both of these are invalid. Okay, so that's what let stands for in this case. So how do we do that? Let's just comment this out and go ahead and create now a mutable instance of car. How do we do that? Well, of course, there's a syntax for it, and that is var. It's a variable. It can change. So we say mutable car is a car with the current speed of 10, then you can go ahead and say that car, mutable car, like this, and drive with the speed of 30. And then you say mutable car, current speed, then you can see the current speed is gonna change to 30 in here, okay? So what we're gonna do then is to have a look at a little bit of copying values and seeing how that also affects our mutability. So let's just remove this code for now. And if we go ahead and create a let copy of this, so we say, let's just say copy is a mutable car. So what we're doing in here is we're taking the value inside mutable car, which is an instance of car, and we're assigning it to a new let constant called copy. Since structures, just remember that structures in Swift are value types, meaning that if you assign an instance of any structure to another variable, the internal data of that structure will be copied over to this variable, meaning that now you have duplicate cars. One is in the mutable car and another one is in copy, and they have absolutely no connection to each other. Let's demonstrate that. And we say mutable car in here, and we say drive it at the speed of 30. And then we say mutable car current speed, and then we say copy current speed. Now you probably think, oh, they should both be 30, but you can see that the mutable car, which was actually mutated using the drive function, it has the current speed of 30. However, the copy has the current speed of 10 at the point it was taken, or basically it took over a copy of mutable car. At this point, mutable car had the current speed of 10, as you can expect from the constructor or initializer. Okay, so remember, structures are value types. When you assign a value of a let constant, for instance, or a variable, where it is equal to an instance of a structure to another variable, then you're basically getting a copy of that structure. And you might be thinking, okay, is that because of let? Okay, let's test that. Let's change this to var and see what happens in here. You can see it didn't really change anything. By simply assigning an instance of a structure to another variable, whether it's var or let, you're making a copy of this and placing it in here. Okay, so that's a very, very important thing to understand about structures. So structures in Swift cannot subclass other structures. Okay, and subclassing is something that comes into play when we talk about classes, but I'm naming it in here. We haven't talked about it yet, but I'm naming it in here because, as I mentioned at the introduction to this course, I expect you to already know another programming language, and chances are you probably know JavaScript or Python or Dart, for instance, or Rust, and you are probably comfortable with subclassing, though Rust doesn't really have subclasses. It has the concept kind of like protocols, okay? But I just wanted to mention that Swift structures cannot have the functionality of subclassing, and I'm gonna explain that how subclassing pretty much works. But we're gonna go more into details about subclassing when we get to the definition of classes in Swift, and that is gonna come up soon. Okay. For now, let's create a struct, and we're gonna call it living thing. And in the init function, we're just gonna say I'm a living thing. All right. Now, you may be thinking, okay, a living thing could be an animal, for instance. So we create a structure and we say animal, and you would expect it to be able to subclass living thing like this. You would say an animal is indeed a living thing. But you can't do this. This is not a valid Swift syntax. You can see this is inheritance from non-protocol type living thing. So just keep it in mind, structures cannot inherit from each other in Swift. Okay? So let's comment this code out, and we just leave it there. Living thing is still a valid Swift syntax, so we could just leave it there. Okay. Now, in Swift, you can also have custom copying of structures. And as we saw, when you assign a value inside a variable to, like here, we had mutable car, and you assign it to a copy, let constant, the entire contents of this mutable car was copied over to this variable. But what if you want to have some sort of a custom logic while copying over something to a variable? Well, you have to create that logic yourself. Let me show you how. Let's say struct bike, we say manufacturer, okay? And we say string, and we say let current speed is integer, all right? Now, if you say in here, let bike1 is a bike, and we have a manufacturer of Harley Davidson in here, and we say, let's say the current speed is 20, so nothing illegal. And then we're going to create a bike2 in here. So we say let bike2, and then you say bike1. Now what you want to do in here, you say, well, I want to get bike1, but I want to change its but I want to change its speed when it is being assigned to this variable. You can't do that at the moment, right? Because even if you change this to var, and if you say bike2 current speed is 30, you can't do that simply because current speed inside the bike is specified as let. You can't change it. You then go say, okay, I have to change it to var then. Well, you'd be right. You can't change it to var and everything will just work fine. But remember, you had to do all of this work simply because you had this requirement in here to assign a bike to another bike and change its current speed. There is another way of doing this, and it's actually more preferred, I would say, to do it this way that I'm going to show you, is to create a function that allows you to do that. So you could go ahead in here and say, well, I have a function, and I'm just going to call it copy. It doesn't have to be called copied. You can say copied with, or whatever you want, okay? Then you can say copy, and then you say current speed. So you want to change the current speed, so take it in as an argument. And then your function could actually return an instance of bike itself. Then you say, okay, I create a bike. Its manufacturer is the self's manufacturer, because remember, this is an instance method, meaning that it is actually operating on an instance of bike itself. So it has access to self and the manufacturer. And its current speed is going to be the current speed that is coming from the argument itself in here. Okay. So now that you have that, you can go ahead at call site in here and say bike1 copy with the current speed of, let's say, 30. And then if you change this back to let, you can see it works as well. And bike2 current speed is now 30. And we could also say bike1 current speed, and you can see that should be 20. So this is one way of creating copies or custom copies of your structures. And to be honest with you, there's not much more to structures. I mean, you have to just get the concept of mutability in structures, and also having the ability to have arguments, having the ability to have properties in here. We talked about var properties as well that can mutate. And we also talked about computed properties, which can return a value by assigning a function pretty much to that property of the structure. So there's not so much more into structures, and I think we've talked enough about them. In the next section, we're going to go ahead and talk about enumerations. So let's create the enumerations playground now. So Command N, playground, and blank playground, and let's call it enumerations. And in here, I'm going to say it is created inside the main workspace. Let's change the group as well to the main workspace in here and press the create button. Okay. Going to get rid of the Explorer, and let's say import foundation. All right. Now let's talk then about enumerations. Enumerations are one of my favorite features of Swift and any other programming language that supports it. And I think actually almost all languages that I've worked with, except for assembly, of course, support enumerations or a form of enumerations. I mean, Objective-C does it, C does it, C++ does it, TypeScript does it, JavaScript does it, Python does it, Dart, Rust, all these languages I've worked with have the concept of enumerations. And that's very good. I mean, they do have enumerations, but to a certain degree, they differ from each other. So some have more advanced enumerations, such as Swift. I would say Swift enumerations are the most advanced I've seen. After that, Rust enumerations are the most advanced. And then we have also JavaScript and TypeScript, which are at the same level, kind of like Dart enumerations. But also Dart is less advanced in supporting different features of enumerations. What are enumerations? I mean, I've talked quite a bit now about enumerations, but what are they? Well, enumerations are categorization of similar values that are named, such as animals, cats, dogs, and rabbits. You could put them inside an enumeration. Now, if I, for instance, ask you and I said, let's create a structure in here, struct animal, and I said, define the type of animal in here, you would probably say, okay, type is a string. And I would say, okay, so can I create an animal and its type is a bike? Then you would say, okay, so what should we do? Should we go ahead and create an initializer in here that takes the type and it says if type is rabbit, or type is dog, or type is cat, then self type is type. Otherwise, you create a precondition failure of, oops, it didn't work, something like that. So this is valid syntax, and it is going to work, but it is not so obvious. I mean, a lot of cases, probably people don't even see your source code, so they have to kind of guess what type they have to pass in here. And that is the reason we have enumerations. Enumerations is a categorization of similar data together by a name. So let's have a look at how that actually works. Let's say an enum, animals, okay, and we can remove the structure from here. And this enumeration, let's also have our playground as automatically running. And this animals in here, then you can define your different types of animals, give them names. And the way to do that is by using a case syntax in here, or a case keyword. Then you say cat, I have a cat, I have a dog, and I have a rabbit. Now, when I say I have, I don't actually mean that these are properties. I mean, these are cases. This animals enumeration has these various cases. And you can also omit case for every one of these cases and remove it and just do it like this as well. This is also completely valid Swift syntax. So you don't have to prefix every case with the case keyword. But a lot of people do that, and it allows you to also go to the next line. I mean, you can also do this, but it looks a little bit strange, to be honest with you, if you do something like this. I haven't seen enumerations in Swift in all my years written like this. It's either written like this, or it is written like this, usually, okay? But it kind of depends on you and your team, how you want to define your enumerations. I think what would be really good is if you and your team decided on a convention of how you want your enumerations to be created. Either all of them have case before them, or you just have one case for all the cases, basically, okay? So you may be thinking then, okay, now that we have this, how do we create an instance of this animals? So we could say let cat is animals dot cat. As you can see in here, you have all these properties in here: cat, dog, rabbit, etc. Let's say cat, and then we can print it out here to the playground console, and you can see it just says cat. You can change this to dog, and you can see it says dog in here, though we have to change the variable name probably as well. Okay, so that's the simplest way of creating an instance of enumeration. Now you can compare enumerations with if statements. So if we go in here and we say if cat is equal to animals cat, then this is a cat. And we can say else if cat is animals dot dog, this is a dog. Otherwise, this is something else, okay? And of course you can continue here. You can say else if cat is animals dot rabbit. However, in here you can't say else if cat is equal to 3, and this just won't work because 3 is an integer and cat is an instance of animals, so you cannot compare. You can see it says there's no comparison operator between animals and integer. And you would be thinking then, oh, maybe I should go and create one. And you could do that. You could say func equality. So this is an binary infix operator. On the left-hand side, you have an animals. And on the right-hand side, you have an integer. And you return a Boolean. And you could say if, you could say you return left-hand side cat, left-hand side is equal to cat, and right-hand side equal to 3. Okay, so then this returns a Boolean. And now you can see your error will go away. So you could do something crazy like that in Swift, but please don't do it. I mean, I'm just showing you different ways of doing things. But this, I just want to tell you that this is not okay to compare an instance of an enum with an integer, for instance, okay? However, there's another way of doing this using its raw value, but we haven't talked about that yet. So let's just remove this and remove this entire if statement from here like that. Okay, so we just have an else. And you can see, as you'd expect, this statement is being executed simply because cat is in fact an instance of animals.cat. All right, or an instance of animals rather equal to cat. Okay. Now, If statements are a little bit strange in that you would have to write quite a lot of code, if and then else if, and then you have to compare them with animals, etc., etc. There's another way of doing this, and that is using a switch statement. And I'm going to show you how to do that. If you say switch on an instance of an enumeration, then in here you can get help actually from Xcode to complete it for you. You can see, and you just press the fix button and it will tell you that, okay, I know that cat is an instance of animals, and I know animals has cat and dog and rabbit. I will type it out all for you. So you can see that syntax is case and then the enum value, and then you can type some code in here. And you can say break, meaning that as soon as it hits that point, you just break out of this switch statement like this. Okay, so let's go ahead in here and say this is a cat, and this is a dog, and this is a rabbit. All right, so we've written our code and we expect this line to be executed. And if you go ahead in here and change the value of cat to a dog, then this case is going to be executed. You'll see soon. This is a dog, right? So let's change it back to cat again. So this is how you would do a switch statement. And then there's a syntax for switch statements where you don't have to specify all the cases. So if you don't want to specify the case of rabbit, you can also do that, just remove it, but you're going to get an error now, as you'll see soon. It'll say that you haven't covered all the valid cases. It says it must be exhaustive, meaning that you have to cover all the cases. But if you don't want to cover all the cases, there is a special syntax called default in here, and say this is something else, which is similar to our else statement. Right? So these two are pretty much the same. However, one is using a switch, the other one is using an if and else statement. Now, I probably should tell you that this is usually not a good idea, specifying a default clause, simply because in the future, I mean, let me actually demonstrate to you. Let's go ahead and in here say that you have a func and you want to say describe animal. And then you say animal is of type animals, okay? Then you go in here and you say describe animal. And let's change the switch to from a cat to an animal in here, which is passed to us. Then we say describe animal and we pass our cat to it, okay? In the case of cat, we're saying this is a cat. In the case of dog, we're saying that this is a dog. And in here, actually, we don't have to pass cat to it. We can say animals dot rabbit. Okay, if we do that, you can see it says this is something else. Now, what if we go ahead and add another case in here and we say case hedgehog? I think it's spelled like this. Now you can see our function is still saying this is something else. So for every case of our animals where it is not handled, it's neither cat or dog, it's saying this is something else. Well, this might work in this example, but usually in larger applications, when you add an enum case to your enumerations, you want everywhere where you have a switch statement to actually take care of that case. Okay, so let me show you how. If we remove this case from here, so we have cat, dog, and rabbit again, we go in here and we bring the case of rabbit, okay, and we say this is a rabbit, and we break, okay. And we can actually take this out. We don't have to have it inside a function anymore. We take it out, all right? And in here we say switch cat. So we have all the cases covered now, cat, dog, and rabbit. Now, if another programmer inside our team goes ahead and adds a case of hedgehog, you can see our if statement still works. And you might be thinking, well, the if statement still works, it must be good. But the switch doesn't work, so it's not good. However, in my opinion, where you go ahead and add a new case to an enumeration, you need to also always ensure that everywhere you're handling an instance of that enumeration, you're taking care of the new case as well. The if statement doesn't do that. It doesn't fail because it's simply doing comparison. However, switch is doing more than that. It's ensuring that if you're switching on an enumeration, that the enumeration cases must be exhaustive, meaning that you have to cover all the cases. So in my opinion, with my experience, it is almost always best to compare enumerations using switch, okay? Because it will tell you that, oh, you can't compile your code now because someone has gone and added a new case to the switch. You have to handle that. So let's handle hedgehog in here. And we say this is a hedgehog. Okay, and we break. So now you can see it is handled, and though this is still a cat, so this statement is being called, but at least we've handled the case of adding a hedgehog in here, okay? Now that we've taken care of that, let's talk about enumerations, a little bit more advanced enumeration concepts, and that is enumerations with associated values. Okay, enumerations in Swift have the ability to have associated values. Dart, for instance, for those of you who are Flutter developers, you probably think that Dart also has that, but unfortunately it doesn't. In Dart enumerations, you create an enum and you kind of make it a class almost by adding properties to it, and then you create enum cases that hard code the values of those properties, and that's not really the same thing as having enumerations with associated values like Swift and Rust have. Because as you'll see soon, enumerations in Swift can have associated values that are dynamically added at the time of creating an instance of that enumeration. Okay, let's for instance have a look at an enumeration called shortcuts or shortcut. Let's say in here you want to create 3 shortcuts. One is called, for instance, a case file or folder. Okay, another one is a www URL, and then a shortcut to a song. So let's say that you're creating an enumeration that can allow the user to do a shortcut to any one of these cases, either a song, for instance, on Spotify, or a website address, or a file or folder. Now, how do you go ahead and do that? How do you then say, okay, this, let's say, let www Apple is shortcut to www URL, but how do we specify that this is actually going to go to Apple? All right, then you would probably think that, okay, I'm going to add case www apple.com or something like that. Well, if you had to do that, then you would have to create a case for every website in the world, and that won't work. And that is the reason we have associated values for enumerations in Swift and Rust. So let's go ahead in here and you say, I want to add some values to these guys. Whoever is creating an instance of any of these cases has to pass some values to them. Then we say, for instance, here, the path is a URL. You see in here, okay? So then at the call site, when you're creating an instance of this www URL, you have to pass it a URL, okay? So we say, let's go to the path and we create a URL. And in here we say it's a string of HTTPS apple.com, and we force unwrap it. We haven't talked about this operator yet. Actually, I think we talked about it once. This is a unary suffix operator, which we've actually seen an example of before. Okay, when we're talking about optionals, but you see, we haven't gone into depth with optionals yet. So just accept that this is a URL for now. Okay, but we don't have to know exactly what this one does. I'm going to explain it soon when we go and talk about optionals. All right, so you can see now we actually passed a value to an instance of this enum case. And you can do the same thing for others, like file or folder. We could say it has a path to a URL and it has a name of string. Okay, and we could say a song has an artist of type string and a song name of type string. All right, so this is up to you. I mean, it's really up to your imagination what values you want to have associated with your enum cases. Okay, now you would be thinking, okay, now that we have this guy, how do we compare it with, like, if there is a case in your application where you get a copy of an enumeration or an instance of this enumeration, if you want to see whether this is a song or a URL or a file or folder, how do you do it? So you would probably say, oh, if www apple is equal to shortcut dot URL, and then let's say you pass this URL to it, boom, then do this. Okay, so you may be thinking, okay, I could do that, but no, you can't really do that. You can't do comparison between an enum instance with associated value and another enum instance with the same associated value, because as soon as you add associated values to enumerations in Swift, basically you need to define equality for this enumeration yourself. There is no equality by default anymore. In this case, when we had animals and there was no associated values, we could do this because Swift adds implicit equality operator, which is a binary infix operator, to enumerations with no associated values by default. But as soon as your enumerations have associated values, Swift doesn't know how to compare them anymore, because it's not the comparison of their cases anymore, but you actually have to define the comparison yourself. Maybe you want to only compare the names in the case of file or folder. Maybe you don't care about the path. Maybe in the case of a song, you don't care about the artist. You just want to basically compare the song names. So Swift can't deduce that equality operator for you. So you can't do that unless you go ahead and basically define equality operator, which is a little bit more advanced than what we're going to go into right now. So as you'd guess, you can rely on your friend switch statement. So we say switch ... apple in here, and we can actually ask Swift to complete this for us. You'll see now there'll be a little hint in here and it says fix, and you can see it will come up with all the cases for us. Okay. Now, I usually don't like the default format that is created in here, but we can use it for now. I'm just going to break them down into smaller parts in here, into smaller bits of pieces of code. Now, in here, we could say print the path, print the name, and then break. Okay. In here as well, we're going to say print the path and then break. And then in here, we're going to say take the artist to its own line, song name to its own line, and then print the artist, and then print the song name, and then break like that. All right. So now we can see that we're going to hit this point, and it says the path of this URL is actually apple.com. All right. And actually, I think in here, yeah, it was called path as well. But here, it doesn't have to be called the same, just so you know. This path, it doesn't have to be. So you could say let P. Okay. The important part is this one. Now, there is another way. You can also remove the argument names. So you can see in here, it says there's an argument name path, and then it's a let path. Let's copy this and make it cleaner. Let's copy this entire thing. So this is what Swift suggests that you do. But usually in codes, in code bases, or at least the ones I work with, no one does this. Okay, no one says here's the artist and then let artist. No one does that. What usually people do is go ahead and change and remove this external argument name in here and just leave the lets in here. Okay, so remove the path and remove the previous thing in here as well, and this, and you will see that this works exactly the same as the other one. All right, so that's another way of writing it. And what is also very, very common in Swift code bases is that people don't like this syntax of writing let before every argument name either. So you could copy this code now. Let's clean it up even more. Gonna paste it here and remove all these lets. Okay, so that let, this let as well, and also these lets from here. And what we're gonna do is to go ahead right after the case, type let. Right after the case, type let. Right after the case, type let. So this let is going to be applied to all of these arguments in here. And you can see it works exactly the same way as it did in the other two examples. Every example is going to become shorter and more compact than the one before it, basically. Okay. Really good. Now, there's another very compact way of unpacking values inside enumerations that have associated values. Now, there was two values in my sentence, but I think you get the point. And that is using an if statement. In very rare cases, if you want to only handle a specific enum case, for instance, in this case, you want to see if this ... apple is an actual URL, you could use a if caselet statement. You could say if caselet. And to be honest with you, in all my years of doing Swift, I still get this wrong almost every time. I sometimes type if let case, and sometimes if case something something, and then let. But the actual syntax is if case let. All right. And then you say the case is ... URL, which is your actual enum case. And then you say path is equal to your variable. Then you can print out the path. So you can see it's printed in here. So you can in here then say it could be anything else. It could be file or folder, and then you could say path and then name, all right, equal to your enum case like this. And you can see it is not executed simply because ... apple is not an instance of file or folder enum case in here. Let's change it back then to ... URL, and then we can grab the path out of this variable instance or shortcut instance in here. Okay. Now, while you're working with enums, you can also ignore values inside the enum cases. Let me show you how. Let's say we create an instance of shortcut. We say without you, is an instance of shortcut to a song by one of my favorite artists, Symphony X, and the song name is called Without You. So one of the really good songs of Symphony X. I highly recommend that you watch it. Listen to it if you want to. I don't actually think there is a music video to it, unfortunately. But there may be one of these lyrics music videos to it on YouTube. So now we have Without You, and we want to compare if it's a song by, for instance, only looking at its song name. So we say if case let, and is it a song? And we don't want, actually we don't care about its artist, so we can ignore the artist using an underscore in here, but we only care about the song name. And we say if that is equal to Without You in here, then we can grab the song name. Okay, so you can see it says Without You without actually using the artist in here. You could also say artist and then type the artist in here as well and grab that artist. You can say it's a Symphony X, but if you want to ignore the artist, you can just pass underscore in here. Okay, really good. Now you can also have case statements and switching case for enums with associated values that have similar data types. Okay, let me actually show you an example of it. Let's go ahead and create an enum of a vehicle. All right, and we say one is a car, and every car has a manufacturer of type string and a model of type string. And then we have bikes as well, with manufacturer as well, like this. But for bikes, we don't want a model, we want a year made integer. Okay, so this is an enumeration. Now, you may be thinking, okay, let's say that you have this business case of every time you access an instance of vehicle, you may want to grab its manufacturer. So how do you do that? Let's go ahead and say let car is vehicle. And how do we do that? Let's say vehicle.car. For its manufacturer, we say it's a Tesla. And for model, we say it's Model X. Then we say let bike is a vehicle bike. Okay. And its manufacturer is Harley Davidson. And its year made, let's say 1987 or something like that. Okay. Just making things up in here. Okay. Now, how do you grab the manufacturer out of these two? Like you have a car and you have a bike and you want to grab their manufacturers. You know both of them have a manufacturer, but how do you grab that? Well, you could go ahead and say, okay, I switch the car. I let Swift extract this information for me for all the cases. Then add this in here. Then you say, okay, I have the manufacturer. We learned that we can have a let statement in here and remove all of this in here. So we have the manufacturer. We don't care about the model. So underscore in here. Then you say manufacturer, and then you break. And you do the same thing for bike. Okay, you say case let, manufacturer is right there. And the year made, we ignore. And then in here you say manufacturer and break. Okay, so this is a switch on the car. All right, and you can see we grab the Tesla manufacturer out of that car. But what do we do with the bike? Oh yeah, we have to go ahead and do the same thing for bike. We go ahead in here and we say switch on the bike. And we say, in this case, since it's a bike, you see Harley Davidson is extracted. Then you may be smart and say, okay, sorry, and not you may be smart, you are smart, but you might try to be smart to say, okay, then I can create a function out of this. Then I will say func get manufacturer from vehicle. Okay, and vehicle of type vehicle, and it returns a string. And in here you could just say return manufacturer and return manufacturer. You could do that as well. Okay, so this is actually one step closer to making this a little bit more usable. And then you could call get manufacturer from car, and then gets manufacturer from bike as well. Okay, so you could do that as well. So you get Tesla, and then, oops, what happened to our bike? The manufacturer should be Harley Davidson. So car manufacturer, bike manufacturer. Oh, because we're switching on car. This is very, very bad. We should switch on the vehicle in here, okay, which is a local variable to the function. Then we get our Tesla, and we should now soon get Harley Davidson. So this is another step towards having a more reusable extraction of manufacturer from our vehicles. What you could do is to move this actually out and place it inside the enum itself. And instead of switching on a vehicle that is passed as a function, we can remove this and say we switch on self. All right. And then we go in here and then we can say car get manufacturer. Okay. And then we could say bike get manufacturer, right? So that's one more step actually towards having it a little bit more compact and having it make more sense. So it's a car get manufactured and bike get manufactured. Now both of them have the same function. However, what you could do is to have this as a computed property. Enums, just like structures, can have computed properties. So let's say var, and we change it to manufacturer, and we say it returns a string. And now all of a sudden, you don't have to call this as a function. You can actually say manufacturer, just like a property, right? Like this. Good. Now it's one step closer to having it very clean. There's one more thing that we can do to have it even better. And that you can see that these both cases, case-let car, case-let bike, they're pretty much doing the same comparison. They're extracting a manufacturer and ignoring the second value. Well, what if we could just remove this and remove this case and have a comma here instead? So we say in both cases, the case of car and bike, we're returning the manufacturer. And you can see that this is valid Swift code and it is doing the exact same thing, right? So if you have pattern matching in your enumerations like this, where two enum cases or more are having the same pattern matching by grabbing one value, and it doesn't necessarily have to be this, to be honest with you. It could, for instance, be in the case of bike, in here, model, and you can ignore this one and instead use the model in here. So actually you then have to call them the same thing. Let's say foo, and then you return foo. Okay, so pattern matching works basically just by matching the value types. Since both of these are strings and the other stuff is being ignored, then you can use this foo. But we actually broke the code because instead of the car manufacturer, we're returning the car model in here. But I just wanted to demonstrate to you, it doesn't necessarily have to be at the same place. So it doesn't necessarily have to be like the same first value of both cases. Okay, so this is a computer property on an enumeration, and it is returning, it's doing pattern matching on the both cases, and it doesn't have separate case statements in here. Okay, really good. That part's also done. Now, apart from enumerations with associated values, you can also have enumeration with raw values, and here's an example of that. So let's go ahead and say enum family member, and then in here you can actually say that we have a case of father, case mother, case brother, and we have a case sister. But what if you want these cases to, for father, for instance, to be called dad? So to have the value of dad. So you want to, for instance, have mother be equal to mom. Then you can say, okay, father is dad, mother is mom, brother is bro, and sister is sis. Okay, but we're going to get an error now simply because it says that this enumeration can't have values like raw values like this. What you need to do is to tell Swift that this enumeration has raw values of a specific data type like this. So you could say it is a string basically. All right, and now Swift is very happy. So what you could do then is to say family member dot father, and then you have a new property in here called raw value. Then you can grab that dad value out of father case, and it is a string. You could do the same thing with brother or mother and sister as well. Okay, so brother is going to say bro in here. Okay, now you can also have enumerations in Swift that have that you can extract other cases, because if you go into family member at the moment, you can see that you have brother blah blah in it, raw value, but you don't have you don't have the possibility of extracting all the cases inside this enumeration. But you can do that in Swift by conforming to a protocol called case iterable. We haven't talked about protocols yet. We're going to do that soon, but for now, just it's enough if you understand the syntax. So let's say enum favorite emoji, and we say it is a string. And also we're conforming to a protocol called case iterable. Okay, just learn it for now, that if you do this, Swift allows you to go through all the enum cases using a property, as you'll soon see. So let's say case blush is equal to blush in here. Okay, and we say case rocket is rocket in here. We then say case fire is fire, like this. All right. Then you can go ahead and say favorite emoji, and like that. And we say we have a new property in here all of a sudden called all cases. All right, you can see it says blush, rocket, and fire. So it gives you all those cases. Okay, and also you can grab their values. You can say favorite emoji dot all cases. Now we're going to use a function called map, and we're going to get their raw value. And please don't worry if this doesn't make sense. I'm just demonstrating what you can do, but we're going to talk about these things when we talk about collections later. All cases is now an array of your favorite emojis. Okay, so if you make an enumeration conform to this case IEEE protocol, I think it is actually a protocol, yes, then you can grab all the cases out of your enumeration using all cases property. Okay, now you have enumerations. You can also you can create instances of them using like favorite emoji.blush, favorite emoji.rocket. But if you have the value of an enumeration, how can you create an instance of it? So right now we have been able to say favorite emoji.blush.raw value, so we get the value. But if you have the value, can you reverse it into blush? So if you have an emoji like this, can you actually grab an instance of favorite emoji using the emoji itself? And yes, of course you can do that. And the syntax for it is if let blush is favorite emoji, and you can say using a raw value of your emoji in here. Then you say found the blush emoji, and then you can print it out to the console. Otherwise, this emoji doesn't exist, like this, else, if I can spell it right. Now, you can see it says found the blush emoji, and then it actually prints it out, which is blush. It's not the emoji itself, you see. It is actually the blush case of the emoji. The favorite emojis enumeration, favorite emoji you can see in here, okay? But don't worry too much about this because we're going to talk more about these in later chapters when we talk about optionals. At the moment, we haven't talked about optionals, so this might look a little bit strange to be thinking, what is if let? Well, it is strange because we haven't talked about them yet, but this is just an example. All right, let's copy this as well and do another example. Then we say, let's see, create, instead of blush in here, we're going to say snow, and we say snow exists, really? So let's pass snow in here and see what happens, because we haven't defined snow as one of the cases in here. You see, we don't have a snow emoji. So, and then we say, try to create an instance of favorite emoji with this snow. And if it is created, then type this, snow exists, really? Okay. And then we can in here say as expected, snow doesn't exist in our enum. So we expect actually to get in here because snow doesn't exist as one of the cases of our enumeration. Okay. Now we've looked at these, and don't worry about these two particular examples because they're using optionals, and we'll talk about optionals more in the future. Okay. Now let's talk about mutating members of enumerations. Now, just like structures, you can have mutating functions inside enumerations, and the way to do that is by prefixing the function with mutating, as you did with structures. So let's say enum height, and then we say we have cases of short, medium, and long, and then we have a mutating func in here, tating func, make long. All right, and by mutating an enumeration, you're pretty much just assigning a new value to self, because there's not much more you can mutate with an enumeration than actually mutating it itself. So in here, then you can say self is equal to height.long. All right, so you can basically assign back to your own self and change your self instance using a mutating func on an enumeration. Okay, so let's go ahead and say we have a variable, my height is equal to height medium, and then we say my height make long, and then we say my height. Let's see what it is. So once it is executed, first is medium, and then we made the height equal to long in here, as you can see. Okay, and if this was a let constant, then you wouldn't be able to do this. You will see now that make long can't be executed simply because it is trying to mutate self. All right. Good. Now we're done with that. Now, There's another concept in Swift enumerations, which is a little bit more advanced, but I wanted to just name it, and they're called recursive enumerations or indirect enumerations. And in all my years of working in Swift, I think I've used them once or twice. It is very uncommon that you see indirect enumerations, and that's why I've left them as the last concept to explain it here, but I think it's still a good idea to explain them. So let me show you what indirect or recursive enumerations are. In short, a recursive enumeration, as its name indicates, is an enumeration that refers to itself. So in here, you can see we had enumerations that just have short, medium, long, and even we had enumerations in here with associated values that were not referring to themselves. You can see in here, they just had associated values of URL, but no associated values of type shortcut again, okay? But let's go ahead and create a new enumeration in here, which has reference to itself. We say enum, int operation, and then we say we have an addition, let's say. So we're basically defining an addition between two integers. Okay, so it's just a case. It's not a function. We say case subtract, and then we subtractions between two integers as well. And then we can have a freehand. This is a special case that we're creating, which refers to int operation itself. All right. So what's happening in here now? You see, we'll get an error saying that you cannot refer to yourself unless you mark this enumeration as an indirect enum, as you can see in here. Okay, so you can now see that issue has disappeared, but what does this actually really mean? And what it means is that now you can have a freehand operation on this int operation. And I completely understand this is a little bit complicated, and you don't have to learn this, but let's just see how we can create a function now on this enumeration that calculates the results based on the cases. Let's say we have func calculate result, and we say the parameter is off operation, and we say int operation in here, okay, as optional, and we say that's equal to nil. And again, I completely understand we haven't talked about these yet either. And in here, we could then basically calculate the operations by doing a switch statement. I'm just gonna paste that in here so we don't have to type all of this, to be honest with you. Okay, so let's see what happened in here. We have the operation or self, unexpected non-void return value, and in here we should return an integer as well. Okay, so what's happening is that we're basically switching on this operation. Since it's optional, we're saying either the operation or self itself. And we're saying if it's an addition, then do addition. If it's a subtraction, do subtraction. If it's freehand, let's actually change this to freehand with a capital H, if I can spell. If it's freehand, then call this function recursively with that operation. And the result to this really is that you can go ahead now and say let freehand is int operation dot freehand, okay? And in here, then you can say do an addition of 2 and 4, and then you can say freehand, and you can say freehand dot calculate result, and then you can see the result being printed in here of 6. Again, please don't worry, this is very complicated. This is almost going to like advanced Swift, and as I said, in all my years of working with Swift, I've had to use, I think, once or twice indirect enumerations. And if you didn't learn this, it's completely fine. It was kind of expected, to be honest with you. And that's one of the reasons I'm kind of jumping over it and pasting code, because I don't think there's so much value in spending time learning about indirect or recursive enumerations. So just know that they exist, but you don't have to learn it. Okay, so let's close off the enumerations chapter with this indirect enumeration. And it's probably a better idea actually if you just remove this whole thing from here, so you don't have to be taunted by the thought of having indirect enumerations in Swift. So at least for me, it doesn't feel so good to end the chapter with something that we just jumped over. But I just wanted to explain that this exists so you know about it. Okay, good. Now we're done with enumerations. In the next section of this video, we're going to talk about classes. Now that we've talked enough about enumerations, let's go ahead and talk about the next concept, which we've actually named before, and you probably know them from other programming languages that you're already familiar with, and that concept is classes. So let's create a separate blank playground for this. So let's say playground in here, and we say blank playground, and let's call it classes. And just again, ensure that you're creating it inside your main folder or workspace. And then we say in here, create. And like we usually do, we just say we need to import foundation in this playground. And again, hold the trackpad in here and say automatically run. Okay. So we have structures in Swift, and we also have enumerations, but there's a third category of storage space, you could say, in memory, and that is called a class. And classes are like structures, but they're not value types, they're reference types. And also they allow for mutability without having to prefix things, for instance, with mutating syntax or keyword. So let's have a look at a simple class in here. So I'm just going to say class person, and let's say var name string, and then var age int. Okay. And so this is a simple class now. It has two variables. And let's see. Oh, we're getting an error in here, and simply because we have no initializers. And this is actually really good. We're getting this error because I actually didn't think of explaining this first. But now that it has appeared, let's talk about it. As you saw before, if you have a structure, like let's say in here we say class person, struct person. And let's actually put exactly the same code inside the structure and comment the class out. And you can see everything will just go fine with the structure. You don't need an initializer or a constructor for a structure by default. An implicit one will be created for you with all the member variables added to the argument list of the constructor. So if you say person, you can see name and age are already there. However, when it comes to classes, you always have to create constructors yourself. There is a refactoring feature in Xcode where you can ask Xcode to create the constructor for you. I'm not sure if it is available inside Playgrounds, and we can see that it isn't. Maybe there is a menu somewhere. Let's see, constructor or initializer, generate member-wise initializer, and that's the one. But it doesn't seem to really work in Playgrounds. So we need to just use this little hint in here and ask it to perhaps, oops, yes, it is not really allowing us to actually add an initializer. It's trying to add a default value to these properties, and that's not what we want to do. So a class's first difference to a structure is that it needs to have a constructor or an initializer. And we already know the syntax for it, and that is with init. And then in the parentheses, you would add your arguments in here, okay? So let's say we have a name, which is a string, and then age, which is an int. And again, not again, actually, we haven't talked about this before, but the ordering of these arguments, it doesn't necessarily have to be the ordering of your properties. So it can be anything in here. And you can actually ask for more stuff. Let's just say height int. I don't know what you want to do with that because we don't have a place at the moment to store it, but you can ask for more things than your class actually has as properties, because maybe some of those values are going to be used in other ways inside the constructor of your class. Okay, so let's take this back to having name and age in here. All right. And then inside the constructor, your job is to first and foremost ensure that your class's properties are all set before the constructor is finished. So you cannot return from a constructor or an initializer, as Swift calls it, without having initialized all your stored properties. Okay, so it says name needs to be stored. Name needs to basically have a value, and then we're going to go ahead and say self.name. Self.name is equal to name. Right? And then we also have to say self age is equal to age. All right, so that's the simple initializer, but we haven't really looked at mutability. Let's have a function in here and say increase age. All right, and then in here we say self age is, we're using this operator in here, which basically takes the left hand side and adds the right hand side to it. All right, so now we have a function in here. You can see it's increasing the age property by 1, and it doesn't have to be prefixed with mutating. Actually, I think if you type mutating in here, it will give you a syntax error. It's not valid on instance methods and classes. So you shouldn't actually prefix anything in your classes with mutating. All right. Then you can go ahead and create an instance of this class. Let's say let foo is a person with the name of foo and the age of 20. All right, then I'm going to break these into their own lines. Then we're going to say foo age. Have a look at the age, and then we say foo increase age, and then foo age. All right. So let's have a look at these values then. You can see first the age of foo is 20, and then after incrementing it using the increase age, then we get the age equal to 20. So nowhere in here did you actually have to create anything mutating. And you can see that the variable itself is actually created with a let. So that's the second difference. When you create a let constant equal to an instance of a class, you cannot assign a new value to this let constant because that is one of the natures of a let constant. After creation, it cannot be assigned a new value. So you cannot go ahead and say foo is equal to some other person in here. So that rule stays the same when it comes to let constants and classes. However, since now you're working with a let constant equal to an instance of a class, this class internally can change. As you can see, the age has changed without you having to change this to a var. So that's the second difference between classes and structures, in that classes allow for internal mutability without you having to create an actual var out of them. All right. And also their reference types. And we'll talk about that soon, actually. Okay. So let's have a look at what reference types actually mean. So in here, we say foo age. Let's bring this down, foo age. Maybe just type it again in here. And then we say bar is equal to foo. All right. And then we say bar increase age. Now you would probably expect bar to be copied and have actually a new copy of foo. However, since classes are reference types, the reference of this foo is placed inside this bar. So pretty much after line 30, bar and foo point to the same instance of person in memory. So bar gets a reference to this foo, and then by increasing the age of bar, then foo's age is also increased and bar's age is exactly the same. So they're basically pointing to the same memory and memory space or memory the allocated memory for this person instance. Okay, so keep that in mind. It's very, very important. Now you can also compare instances of classes by using the equal, so the triple equal syntax, which in all my years of working with Swift, I've never had to use. So it is very unlikely that you'll have to use it. However, if you want to see if two instances of a variable pointing to a class are pointed at the exact same memory space, then you would use this syntax. You would say if foo, if I can spell, is equal bar. Okay, I think I've placed actually my fingers on the wrong place on the keyboard, so that's why I'm typing everything incorrectly. So let's say foo and bar point to the same memory. Otherwise, we say foo, they don't point to the same memory. And then you can expect that you get this printed to the console simply because, yes, they are actually pointing to the same memory space. And if for those of you who are curious, you'd be probably thinking, okay, what happens if I just change it to this? And we should ideally get an error, as you can see in here. And that is simply because we haven't implemented equality on this class. So person doesn't conform to equality in here. And we'll talk more about equality perhaps a little bit later. But if you want to basically ensure your class instances are equitable, then you have to say equitable in here, and then you go ahead and define a static func equal like this. But we will probably talk about this a little bit later. Just know that this equal is not the same as equal. This basically tests if two variables hold values that internally are equal to each other based on some logic. However, this is some logic that Swift has implemented, and you don't implement this logic at all. What this one does is just make sure two variables are pointing to the same memory allocation. All right. And as I mentioned before, you probably don't use this so often. Now, classes, unlike structures, can also have inheritance, meaning that you can create a superclass with some logic, and then you can have some other subclasses that conform to that. Actually, not conform, but they subclass that superclass. All right, let's have a look at an example in here. So we say class vehicle. All right, so we have a simple class, and we say go vroom like this, and in here we say vroom vroom like this. All right, doesn't necessarily have to be anything scientific. Then we create a car class, which should subclass vehicle. Okay, so we say it subclasses that vehicle in here, and car doesn't have any implementation of its own. Then you can create an instance of car like this, and then you can say car go vroom. So you can see car, though it doesn't have an internal implementation of go vroom, it has inherited that function from its superclass, namely vehicle in this case. So keep that in mind. You can have inheritance using classes, which is something that you cannot do in structures. Okay. Now, classes can also have private setters. So you can actually have a variable that is marked as var, but can only be set privately. So you can see in here, these variables are just simple vars, meaning that they can be both internally changed and also externally changed. You can see in here, let's say foo has the age of 20. I can go in here and say food at age plus equal to 10. And with this syntax, I'm pretty much changing the age of foo. So if I then go to foo age, it should be 31 in here. So you can see it's a variable that can both be externally and internally changed. All right, so if you mark a property as var inside a class. However, you can also mark a property as var, however, allow that to be only internally within the class changed. Okay, so let's say class person2. So then we say private set var age int. So by using private set, we're saying that only can be set internally inside this class implementation and can be read from the outside. All right. And then we say we initialize it with an age of int. Then we say self age is age. All right. And then we have a function in here. We say increase age, and we say self age is equal plus equal 1. So we're basically saying pretty much the same logic as we had before, but you'll now see that you cannot change this age from outside this class implementation. So let's say Baz is equal to person2, and then we say 20 here, then we say Baz dot age. If you then try to change this externally, you will get an error simply because this property is not settable from outside. You can see it can't be mutated. All right. Now, if you remove this private set from here, you can mutate that age from the outside as well. All right. You can see it's working as expected. But if you have this syntax private set, then it can't be modified from outside the class implementation itself. However, you can use still this function, which then modifies that variable internally. So you can say Baz increase age and then Baz age. You can see now age should have been changed to 21 at this point. All right, so that's the syntax for private set in classes in Swift. Now, you can also, now that we're talking about classes, very important that we talk about initializers as well, because initializers are very, very special, I would say, in Swift, in that you can have convenience initializers and you can also have designated initializers. Now, designated initializers, their goal really is to ensure that they construct an instance of the class by, first of all, ensuring that all property values are set, and also that the internal structure or the internal validity of that class holds up. However, you can also have convenience initializers, meaning that the only thing they do is that they probably add some logic to the constructor or the initializer of that class, but they essentially, at the end of the day, delegate the initialization to a designated initializer. So it's as if you have, for instance, your mother in the kitchen or your father in the kitchen. There's a party and they're making food. And then you stand at the door of the kitchen as kind of like a delegate, and people come and make their, they basically make their order. They say, could I please have this? Then you can talk to them. You'd be like, let's say someone comes to the door. The kitchen says, could I please get a cup of tea? And then you can say, oh, does it have to be red tea or does it have to be a black tea? Then they say, oh, red tea. Then you go to your father and say, could you please make a blah, blah. So I actually forgot whether it was black or red that that person decided. But whichever they say, then you go to your father and ask, or your mother, and ask them to make it. So you're kind of like a delegate. You're making the job of your father or mother a little bit easier. And that's exactly what a convenience initializer does. It gets rid of some hassle, and then at the end of the day, it delegates the work to a designated initializer. So just the designated initializer is the person in the kitchen, and the convenience initializer is you at the door. Okay, but let's have a look at some examples of how this actually works in real life. So let's say class Tesla. All right, then we say let manufacturer is Tesla. Then we say let model is a string, and let year is int, so the year of production. All right, then we will initialize our Tesla in here. We create a designated initializer. You can see in here is designated. It doesn't have convenience written before it, and we'll talk about convenience soon. But any initializer that doesn't have the word convenience before it is a designated initializer. And classes can have multiple designated and multiple convenience initializers. All right, so here's a designated initializer, and we say here model is X. So let's say by default, anyone initializing Tesla without passing any values to us, they get a model X Tesla. And then we say year is 2023. So that's one designated initializer. The next one, we will say init. And in this designated initializer, we actually take the model as a string and the year as an integer. All right. So we say self model is a model and self.year is a year. All right. Like that. Now, another property of designated initializers is that they cannot delegate their work to another designated initializer. So in here, you can say self init model X and year is 2023. So we should get an error in here saying that a designated initializer cannot delegate its work to another one. Okay. You can see cannot delegate. So designated initializers should do all their work themselves. They cannot rely on another designated initializer. Okay. So that's for designated initializers. Now let's have a look at a convenience initializer. Now let's say that you want to create a convenience initializer that by default assumes that the year is 2023. So the caller to that initializer doesn't have to pass the year. All right. So then you say convenience initializer, init, and then the only property we want in here is the model. All right, and in here then you can say this function calls the self init with the model that is given in here, but the year is 2023 by default. So you can see a convenience initializer is delegating its work to a designated initializer in here. Okay, now you can go ahead then and create a subclass. You can say class Tesla model Y. All right, and it is subclassing Tesla, and in its init, then what you want to do, you want to create an initializer for model Y that by default calls the super initializer and sets the model to Y and sets the year to 2023. All right, or perhaps it could just call this convenience init in here as well. Let's have a look. So you create an initializer, and here you say, okay, I want an init. All right, however, you need to be careful because init is already implemented on the superclass right here. So if you're also creating an init in your subclass, you have to prefix it with override. So you're saying I'm creating also another version of this. Okay, and you can see it says you need to at the end of this initializer somehow call super init. So then we say, okay, then we call super init, and for model we say model Y and year is 2023. All right, let's see what happens in here. Okay, so now this should actually work as expected. This shouldn't give you any errors. All right, let's see what happens if we comment this out and just instead call one of our designated initializers. So, our convenience initializer, which is this guy right here. We just pass the model. Since the year is already set to 2023 in this convenience initializer, we could just try to call it and see what happens. So I'm just going to say model is Y. All right, and right here, since this is a designated initializer, inside a designated initializer, you cannot call a convenience initializer from your superclass. So this is another rule that you have to remember. So I think a good rule to remember is that designated initializers in subclasses, they can only call to designated initializers in their superclass. Inside any class, a designated initializer cannot delegate to any other initializer. Okay, convenience initializers can, inside subclasses and inside their own classes, call either No, basically not either, but they can call a designated initializer. Okay, it is a little bit special. I'm completely aware of that, but it's just some rules that Swift has set. And I think logically they make sense, but kind of they can make programming a little bit difficult sometimes when you're working with classes. So let's create an instance of this Model Y. So we say Tesla Model Y. And in here, you can see we don't have to pass any values to the initializer simply because we already have an init with no input values, basically, no arguments, okay? Then we say model Y, model Y dot model, and model Y dot year, and then model Y dot manufacturer, which comes from the superclass, which is always set to Tesla, all right? Now, one thing that I mentioned at the beginning of the section was that classes are reference types. They're not value types, unlike structures. And that should really make you aware of passing instances of your classes to functions. So let's have a look in here. Let's create a foobar, and we say it's an instance of person 2, all right, with the age of 20 in here. And then we say foobar.age. And then let's say that there is a function that is looking harmless. It's called do something, all right? And with person, and we just pass person2 instance to it. What this guy does internally is that person dot increase age. It calls increase age function on that person, all right? Foobar is at the moment having the age of 20. And then if you say do something with foobar and then say foobar.age, you can see the age will have been increased to 21. And simply is because the reason behind this is that classes are reference types, meaning that by calling this function and passing an instance of your variable to this function, you're not copying the values of foobar over as new instances, except you're actually passing your entire memory space, the memory allocated for your person2 instance into this function. So this function is completely free to do anything it wants with this person instance. So just be a little bit careful with that. Just know that classes are a little bit more special than structures. With structures, you get a little bit more safety, so to say. Now, another concept that we're going to talk about before we close off this section of the video is deinitializers. They're quite useful in some special cases, but some other cases you probably don't need them. So I would say probably 90% of the times you're working with classes, you don't need deinitializers unless you're working with some sort of notifications or RX, for instance, if you're working with reactive programming. So let's have a look at deinitializers. As their name indicates, they're kind of similar to initializers, but they do the opposite. Deinitializers are invoked automatically by Swift whenever your class instance is going out of memory. So it's kind of getting cleaned from the memory. So no one else is holding on to it, and it has to be removed from memory. So let's create a my class in here. Okay. Then in the init, we will just say initialized. And then we'll have a function here called do something, which is empty at the moment. All right. Then we create a new function in here called dinit, and you can see that it is purple in here, but it doesn't matter. I mean, the color doesn't really matter. It just matters that this is a reserved word. It's a keyword in Swift, meaning that you can't really use it anywhere else except if you do something like funky like that. But just know that it's a reserved word. It's similar to init, but it's just called when your class is going out of scope. And in here we can say deinitialized. All right. Now to test this, we should actually create a function in which we create an instance of this, because if you create an instance of your class in here, let's just say let my class is an instance of my class, and then my class do something, your deinitializer won't probably be invoked. You can see your initializer is invoked. Do something, I mean, in here we could actually say do something, just so that we see that that function is also invoked. However, deinitializer isn't invoked, and that's just the nature of playgrounds. So what you could do is to create a closure, my closure, and we say it is basically carrying out this logic inside the closure, and then we can call our closure. So at the end of this closure, this variable should go out of scope, meaning that its deinitializer should be called. So let's say my closure in here. All right. And then you can see your deinitializer. Oopsie daisy. What happened? My closure. All right. Cannot find my, did I spell it incorrectly? Like this. And now you can see that the initializer is in fact called and invoked simply because after my closure is called, this scope completely finishes, meaning that all variables inside this scope should also go out of scope. So dinit will be called on all class instances. All right, really good. We seem to now be done actually with classes. So let's just jump right ahead into the next concept, and that is protocols. So I'm going to go in here, and actually not there. We don't have to go there. I'm just going to press Command N in here, create a new playground. And we're going to say protocols. Again, ensure that it is inside your workspace and not inside another playground. Create, all right. And we get rid of this Explorer in here and we say foundation, like this, foundation. All right. Now, protocols, for those of you who are Rust developers, you probably already know what protocols are. And protocols are special kind of objects, kind of like interfaces, you could say in Java, for instance. I'm not sure the term in Kotlin, what that is, but you also have protocols as mixins in Dart, for instance. So what protocols are is that you create an interface, you create a set of rules that objects which conform to a protocol have to follow. So it is not a class, because if you have a class, for instance, if you have a superclass that has some functions, all subclasses do not have to re-implement that function. However, if you have a protocol that only creates some functions with no body, so the functions don't have logic in them, any object that conforms to those protocols have to implement those functions by themselves. All right. So it is actually a little bit difficult to explain what protocols are without having a look at how they work. So let's go in here and say that this is automatically running and create our first protocol. So we create a protocol called can breathe. Okay. And in here, we say any object that can breathe should have a function called breathe. So you can see this function is a special function. It has no body. You cannot create, for instance, a class person and just have this in it. This just won't work. You have to have a function body. And you can't do that either in structures. Your function has to have a body. So you can see that won't work in structures either. That's why protocols are a little bit special in that they can have just function declarations without any implementation. All right. And that's what is called interface in so many other languages. All right. So we have a protocol now, can breathe. Let's go ahead and create a structure called animal. And we saw when we were talking about structures that structures cannot have superclasses, so they cannot actually inherit from each other. Okay. So if you create, for instance, a structure of animal, and then you say struct cat, you cannot say that cat is an animal. It just won't work. Structures don't allow inheritance. However, they do allow inheritance from protocols. So you can say a structure of animal that inherits from can breathe. And this is completely fine Swift syntax. However, we're going to get an error because now you can see it says the animal type doesn't conform to protocol can breathe. And the reason behind that is that a protocol here called can breathe specifies that anyone conforming to this protocol has to implement this particular function. And we haven't done that. So as soon as we go and type breathing here, you can see then this error will go away because now animal structure conforms to can breathe protocol. Okay. And in here, we can just say animal breathing like this. Okay. And also then you can create another structure, struct person can breathe like this. And in here we say breathe as well. And then we say person breathing like that. All right. So then you can go ahead and create instances of these two structures. We say dog is an animal and we say dog breathe. And then we create a person called foo, an instance of person. We say foo breathe. All right. Now you can see both of these lines will then be invoked simply because we call them from here. So that's basically the essence of how protocols work. I mean, protocols can be a lot more complicated than that, actually. In that, I mean, we talked right now about having protocols that only have function declarations, but not implementations. But protocols in Swift are kind of like mixins in Dart in that they can't actually have their own implementations. So they're not just like objects that have dummy function headers, but they can indeed have function implementations. So let's have a look at that. Let's create a protocol called protocol can jump, and then we say a jump function. All right. Then in order to create implementation for this function, I mean, you may be thinking, okay, maybe I should do this jumping. And this will just give you an error because you cannot create your function body inside the protocol itself. The trick to do that is to go ahead and create an extension on canJump. Okay, and we haven't talked about extensions yet, but it is necessary that we just name it in here simply because that's the way to actually add implementation to this function. All right, then we go and say, okay, it's the same function, and then we just say jumping. So by this trick, I mean, it's not really a trick, this is the way to do it. By using this technique, I'm trying to avoid saying trick. By using this technique, you're adding a default implementation to this otherwise very dumb function. So you may be asking, okay, but what happened here? Can I just call this function now? So can I just say canJump is an instance of canJump? Can I do that? Well, you can't because you cannot instantiate a protocol. You need to instantiate an object that conforms to a protocol. Okay, such as a cat that can jump. So let's say struct cat can jump. And now since this jump function already has an implementation, you can see that we're not getting an error from Swift saying cat should implement this function. If you remove this implementation from here, all of a sudden, all objects that conform to canJump need to implement this jump function themselves. But if you bring it back into canJump, then all objects that conform to that protocol will get this implementation by default. But they can go ahead and change it if they want to, like this, okay? So that's also valid. However, if you leave it, it also works without problem. So let's create an instance of this cat. We say whiskers. Whiskers is an instance of cat, and we can just say whiskers.jump. All right, this is how we can invoke that function that is implemented on canJump, right? Now, protocols, apart from defining function headers that their conforming objects have to implement, they can also define variables. Let's go ahead in here and say we have a protocol in here. We say protocol has name, protocol has name, and then in here we say var name, a string, and then we have to say get in here or set or both like this. Now what this really means is that this protocol is asking Swift saying any object that conforms to me has to have a variable called name that has to at least have a getter. What does this mean? Well, this is really just a dumb way of saying this. So it basically says a variable that at least I can read from. But this syntax isn't valid in protocols. I wish it was, but you have to implement them like this. So you're basically saying some sort of a variable that I can read from, which is called name. All right. And then you can also have age. All right. And let's just say age should be getter and setter, meaning that it should actually be a variable that can be set. All right. Now we can go ahead in here and say we have a struct of dog and it has a name. You can now see that we will get an error now from Swift saying that this doesn't conform to has name, and we can ask it to fix it for us. And you can see by default, it creates these variables for us. However, what I really don't like about this is that what it did is that it created a variable for name, though it could actually be a let, since the protocol has name asks for this variable to be at least and at most actually read only. So we can just demote this to a let variable and you'll see that everything will work as expected. Okay, so let's go ahead in here and then create an instance of this dog. And we can call this instance woof. Let's say woof is an instance of dog. And we say name is woof. And age is a very graceful 10. Then we say woof.name. All right, and woof.age. Woof.age plus equal 1. So we just increase the age, but we cannot change the name. All right, so let's just woof age in here as well. So let's see what happens. Okay, and this, I mean, we're getting these errors right here because we can't modify woof because it's an instance of a structure, which by default becomes a let constant that cannot even have a mutation internally. So we have to change this to a var. So remember, structures are different from classes, all right? So this is basically a protocol that required all its classes or structures that conform to it to have a variable called name that can at least and at most be read from. So it can be a let and it can also be a var. But why does it have to be a var, a promotion of let, if we don't have to have it as a var, because the protocol says I should just be able to get from it. Now, you may be thinking, okay, but why do we do these things? Well, the reason is if you want to go ahead and add functionality to this protocol, then this protocol internally has access to name and age. Let's say extension has name, and then we can then create a function that says describe me. Then we can say your name is name, and you are age years old. Okay, so since this protocol expects a name variable and an age variable, it can then go ahead and read them. So it can access them, and it should also be able to set them. Okay, and then you can say func increase age, and in here then you can say self age plus equal 1, and we can fix this actually now. So you can basically go ahead and add functionality to your protocols. Let's say fix it, and we add a mutating function in here. So you can see this protocol, since it knows what it requires, all its classes and structures that conform to it have to have these values, then it can go ahead and take advantage of those variables or functions or whatever it has. Okay, so now all of a sudden, all objects that conform to has name protocol will get a describe me function. Let's go ahead in here and say woof. You can see it has a describe me function all of a sudden, and it will say, oops, okay, here. Your name is Woof and you are 11 years old. Okay, and maybe this should actually return a string. And it could just return that string instead of printing it here. And in here, then we get the result. You can see it says your name is Woof and you're 11 years old. And then since we have a var Woof pointing to a structure, we can go ahead and say Woof dot increase age, and then we say Woof age. All right, so the age by this point is 11, and then we invoke this increase age function, which is a mutating function, and then we get the age of 12. All right, so protocols can define kind of constraints or kind of like an interface on objects that conform to them, and therefore can, using extensions on those protocols, can access those variables and functions which are placed in here. So it's kind of like giving a blueprint. So it's kind of like any object that conforms to me has to have this blueprint, and then I can internally use that blueprint to my advantage. Okay. Now, just like we've seen this in here, protocols can have mutating functions, something that I wanted to mention next, but I think I just mentioned it a little bit too early perhaps, but at least you get the point. Let's now focus on that mutating function. So if you say protocol vehicle, I just want to show you another example. And let's say we have a variable speed, and we say it should be an integer, which is getter and setter. So we should be able to set it and read from it. Okay. Then we create a mutating func in here, increase speed, and we say by which value, like this. Okay. So we define this mutating func in here, and then we go ahead and extend this vehicle like this, and we implement this mutating func. All right, so what we did here was a little bit is not optimal, because we implemented the mutating func increase age inside the extension, so whoever looks at our protocol won't immediately understand that there is a mutating func available on it. So if you wanted to make this code a little bit more readable, we would place this function declaration here as well. Okay, so let's go in our code again, and we say in the implementation of our protocol, increase speed by value, we'll actually have an implementation that says self.speed is plus equal to value, like that. And we can bring this value down here to make the code a little bit more readable as well, and perhaps decrease the size of the preview as well. So let's then go ahead and create, for instance, a concrete implementation of this vehicle protocol. So we say struct bike, and then bike will have a speed. Oh, let's actually move this and say it is a vehicle. All right. Then we get an error from Swift saying that it doesn't conform to vehicle simply because it didn't have the speed variable. Then inside this bike, we create an init, and we say self.speed is 0. You could have also done it like this. That also works. It kind of depends on how you like to implement, do your implementations. I've seen both, and for me, both are fine. It's up to you and your team to actually make a decision on what convention you want to use for initializing your variables and structures, okay? But this is completely valid syntax as well. After doing that, let's create an instance of this bike. Let's say bike is an instance of bike like this. Then we get the current speed. It should be 0 because that's what the initializer did. Then we say bike, increase speed by 10, and then we say bike speed. All right, so because we are conforming to the vehicle protocol, we can have access to this increase speed function in here. Now, I can see we're getting an error simply because the bike cannot be mutated. You can see we're actually invoking a mutating function on an immutable let constant. And the solution to that is to change this to var. All right, now you can see our speed was 0 and then it was increased to 10 simply because we increased it using this mutating function defined and implemented on the vehicle protocol. All right, so that's one thing. I mean, that's not one thing, that's quite a lot of things about protocols, but at least you get the idea of protocols. Now, protocols can also be used as a conformance, how do you say it, blueprints kind of. So let me just explain how this would work. You can at any point in Swift use the is syntax or keyword in order to check whether an object conforms to a protocol or not, because any class or any structure can conform to at least one, actually not at least 0, and at most unlimited number of protocols. So a structure or a class doesn't have to conform to any protocol, or it can conform to one or more protocols. That's what I'm trying to say. And if you want to at any point check whether an object conforms to a protocol, you can use the is syntax. Let's have a look at that. Let's say we create a function called describe, and it takes an object of type any, and we haven't talked about this before, but any is pretty much, as its name indicates, any object. Okay, then we say if object is a vehicle, then we say object conforms to the vehicle protocol, else object does not conform to the vehicle protocol. All right, then we can go ahead and call this describe function and describe our object of bike. And then you can see, since bike conforms to the vehicle protocol, then we get this printed to the screen. However, if we had a structure of worm or a worm and it didn't conform to the vehicle protocol, and we set worm as an instance of worm, and then we just say describe worm, then you can see that we will get this message printed to the screen. Object does not conform. All right, so now that we've done that, let's just remove this worm. I don't like to have worms in my code. So at least you get the point now with that as well. Now there's one more thing that we have to talk about when it comes to protocols, and that is, I mean, we've talked about is, but we haven't talked about as, and as with a question mark. And they make more sense when we've already talked about optionals, and we haven't talked about optionals yet. We'll talk about optionals in like the next 3 sections of this video, but I just want to name it as well so you know that it exists in Swift. So using this as syntax, you can conditionally promote an object to a specific type. So in here, you can see object is vehicle, and if you say object dot, you don't have anything to do now with this. I mean, you cannot do anything with this object. Even though you actually said if object is a vehicle, then I kind of would expect us to be able to invoke these functions on that vehicle, because we actually asked Swift, is it a vehicle? Then we come here. But Swift doesn't understand the syntax as good as it understands as, like this. And the reason behind that is you're simply just doing an if statement in here, saying, is it that? Then do something. But you didn't actually promote this object to that type. All right, so any is like a very low object type. However, this is sitting a lot higher in the hierarchy, and that's the reason we say promote. So let me actually show you an example. Let's say that we have let's say a bike in here, and bike is a vehicle which has increased speed. All right, but we want to create a function that can allow any object to come in, and if that object is a vehicle, kind of like this, then it will increase its speed by 20. All right. So let's say func increase speed if vehicle, and then the parameter to this is an object of type any. All right. Then in here, say if, then we create a var, and the vehicle is equal to this object, and then we say, is it a vehicle? Like this with an as syntax. If it is, then we say vehicle speed. You see now we get access to all properties of that vehicle because we promoted this object to a vehicle. So it's not similar to is, because this won't allow us to access the vehicle objects in here or properties or functions. Then we say get the current speed, vehicle, increase the speed by 10, and then get the speed again in here, okay? Otherwise, we say this was not a vehicle. So let's then go ahead in here and see what happens. So let's say increase speed if vehicle, and then we pass our bike in here. All right, let's see what happens. Are we getting a lot of errors perhaps from Swift? It crashed? No, okay. So you can see we got the value of 10 in here, okay? And then we get the value of 20 right here, okay? Now, you may be thinking, okay, but what happened in here? Bike, let's have a look at bike. You can see its speed was 0 in here, and then 10, and then we called this function, which should have increased the speed to 20. But if in here we say bike speed, what happens? Do you think it's 20? Well, no, it is 10 actually. And the reason behind that is that bike is an instance, if you go back to it, is an instance of a structure called bike. So it's a structure. Structures are value types, meaning that when you call this function with an instance of your bike, you're not actually passing the memory consumed by this bike as a reference to this function. What you're in fact doing is that you're making a copy, actually not you directly, but Swift is doing that. Swift is making an entire copy of this, it's making a copy of this entire object and passing it in here. So in here, this var actually is pointing to not the same memory address that bike is consuming, but it's pointing to a completely new variable in the memory and is allowing it to basically be increased by a certain speed, which is not affecting this bike. However, if this bike was an instance of a class, so if we went in here and said bike is actually a class, so let's say class, now you can see calling this function, it will actually change the speed for you to 20. So calling this function, it affects the actual instance of bike itself. You see the speed is exactly the same, but if you go back to a struct, you can see the speed of your bike will be 10. All right, so keep that in mind when you're working with protocols. Protocols and classes and structures together go really hand in hand to create amazing object-oriented applications in Swift, but they can make things also a little bit complicated. So keep that in mind when you're working with these concepts. Good, that's quite enough about protocols. Now that we've talked enough about protocols, let's go ahead and talk about extensions. You've already seen examples of extensions and how they work in Swift, but we haven't really focused on them. So let's do that now. Let's go, oh, I don't have to do that. Let's create a new playground, and in here we say a blank playground and we say extensions, all right, like that. And here as well, then we say create. And just like usual, we say we just need foundation for now. All right. So extensions, as their name indicates, they can add functionality to existing types. They can extend existing types. So let's have a look at an example. Let's say that we have an extension on data type of integer. And then we say we have a function called +2, which returns an integer. And since this function is an extension of int, self in here refers to the current integer instance. Okay, then we say we return self +2. All right, then we can go ahead and say 2 is equal to value of 2, and then we say 2 + 2. And then you can see, then we get the value of 4 here in our playground. Okay, so self inside extensions refers to the current instance, meaning that this 2 in this case. All right, so self in here is actually 2. So if you just print self and then you say return self +2, you can see self is indeed the value of 2 in here, which is what you've specified in here. So if you change that, self will change to that as well. All right, so keep that in mind. That's one example of an extension. Now, using extensions, you can also add initializers to existing types, which is one of the most powerful features of extensions in Swift. Let's have a look at an example. Let's say that you create a structure called person in here, and you have a first name string, and then let last name as a string. Okay. Now, what you want to do is to create you want to hold on to this person's constructor or initializer that Swift already creates for you with a first name and last name. So you don't want to change that, but you also want a constructor that takes in a full name. However, if you go in here and say init full name string, then you can see all of a sudden your person doesn't have any other constructor with a first name and last name anymore. Your only constructor inside the structure itself replace the existing constructor. Okay, and that's not good. So what you want, if you want to, for instance, have a constructor or initializer on this person that doesn't replace the existing initializer that Swift creates for you, then you need to create an extension on person. And then you go ahead and add your initializer in here. Okay, now you can see if you try to initialize an instance of person, you have both of these constructors, the default one that Swift created for you, and also your own constructor, which is inside the extension. All right, so let's inside this constructor go ahead and grab the components out of this full name. So we say full name components is a function, and we separate the components by a space. All right, so we say let components, and then we want to pass these values that we extract from components. So we say self init into our constructor. Then we say the first name is actually components first, otherwise full name. And we say in here as last name is components last, otherwise full name, just like that. All right. So this is very dumb implementation, to be honest with you, but I mean, it's not too dumb either. It is literally taking the first part of a name and the last part of a name, assuming that this is the first name and this is the last name, and anything that is between them separated by space is the middle name, which we don't care about in this instance. Okay, then we can go and create an instance of person. So let person is a person. Then you can see we have both constructors or initializers, and we're going to use full name in here. We say foo and bar. You can see they're separated by space, and the first component is foo and last name, and last component is bar. Then we say person first name and person dot last name. All right, so that's another powerful feature of extensions in Swift, in that you can extend an existing structure, for instance, and add a new constructor or initializer to it. Okay, now apart from that, you can also extend existing types and add conformance to a protocol to an existing type. So that's also really cool. So let's create a protocol in here. We call it goes vroom. Okay, so that's our protocol name. And this protocol, what it does is that it has a var room value, and it's a string, and we should be able to read from it. Okay, and then we create a function. We say go vroom, and then this function returns a string. Now we go ahead and extend our goes vroom, and then we add the default implementation for this go vroom function, and then we say self dot vroom value goes vroom. So remember, this is just a variable that we know any instance conforming to our protocol should have access to. And then here we're just adding the default implementation for this go vroom function and returning this string as its return value. All right. Then we go and create a car instance. We say struct car, and this car conforms. Actually, we don't want to conform yet. And in here we say let manufacturer is a string, and we say let model is a string as well. I guess this is just a simple car structure. Then we can say let model X is an instance of car with the manufacturer of Tesla, and its model is going to be X. And after creating this instance, we can go ahead and actually extend this model X. So we can say model X extension of car. Then we say car now all of a sudden conforms to the goes vroom protocol. You will get an error in here telling you that you're not actually conforming to goes vroom. And the reason behind it is that if you go to goes vroom, you can see that we have two requirements. One is that we have any type conforming to goes vroom protocol has to have a variable called vroom value that's at most and at least readable. However, car doesn't have that, and that's the error that we're getting in here. So let's just get Swift to fix it, and you can see it creates a computer property in here called vroom value, which should return a string. Okay, and for our vroom value, we're going to say it is self manufacturer model and self.model. All right, and then all of a sudden this car instance conforms to the goes vroom protocol, meaning that this model X all of a sudden gets a function called go vroom. And if you do that, you can see it says Tesla Model X goes vroom. And that's because vroom value is a variable that is implemented on all types that conform to goes vroom. But goes vroom doesn't really know what this value actually is. It just extracts that value and adds it here and then says goes vroom. However, it is the conforming type's responsibility to return this value. And in this case, the case of car structure, we're just saying manufacturer and then model X. So it says Tesla Model X goes vroom. This part is provided by conforming types such as car, and this part is provided by the goes vroom protocol itself. Okay. So you can also have, now that we've talked about that, let's go to the next concept, and that is having extensions on classes with convenience initializers. So you can actually extend existing data types and add convenience initializers to classes. And not structures, because structures don't have convenience initializers, but classes can. So let's go ahead in here and create a class, and we call it myDouble. So like a class that holds onto a double variable. And we say var value double. And then we can say an initializer that takes a value of double. And we say self value is value in here, okay? Now you can go ahead then is actually this, I don't think this needs to be a var. It can just be a let perhaps, okay? And in here, then we're going to go ahead and create a convenience initializer, which always sets this value to 0 if anyone initializes an instance of myDouble. Because at the moment, if we say let's go ahead, foo is myDouble, you can see that you always have to have a value available and pass to myDouble initializer. But if you don't want to have that, you can extend your myDouble class in here and say you have a convenience init in here that takes no parameters and calls self init with a value of 0. So this is literally delegating its task to a designated initializer in the myDouble class, but it is a convenience initializer that is created inside an extension. So that's one of the powers of extensions. You can extend an existing class and add a new convenience initializer. Okay. So then you can go ahead and say myDouble, create an instance of it, and then you can just say value. All right, you can see now the value is 0. This is another fancy way of basically accessing the value. You could have said let myDouble is an instance of myDouble, and then you could have said myDouble.value. So that those two lines of code were pretty much, achieving the same thing. Okay. Now, apart from extending, not apart from, but I mentioned that extensions can extend structures and classes. But guess what? They can also extend existing protocols. So you can see in here we have a protocol called goes vroom, and it has this go vroom function. You can go ahead and extend it. You can say extension goes vroom, and then in here you can add a new function, say go vroom vroom even more. Okay, so this is just a ridiculous name. I'm completely aware of it, but you can. What I'm trying to say is that you can extend an existing protocol as well and add new functionality to it. And by doing this, every data type that conforms to that protocol will get your new function by default, so you don't have to do anything. Okay, then in here we just say self vroom value is vrooming even more, like that. Okay, then all of a sudden model X that we created in here, which conforms to, which is an instance of car which conforms to goes vroom, gets this new functionality by default. So then we can say model X go vroom vroom even more, and then you can see that value being printed to the screen as well, is vrooming even more. Okay, so extensions are, I would say, one of the most fun aspects of any programming language. And in Dart, for instance, they're called mixins as well, and they're available in some other languages such as Rust as well. So they're really fun because they allow you to make existing things and types better. They can kind of get out of hand sometimes if you're like misusing them, in that when you're extending generics types, for instance, you can just go crazy with generics. But as long as you're comfortable and you and your teammates are comfortable with those extensions, I would say go for it. Now, we've talked enough about extensions for now, at least. Let's go ahead and start talking about generics, which is a topic a lot of developers try to avoid, but I think you need to embrace it, because if you look at most modern toolkits and frameworks such as Swift UI, they could have not been made possible without generics. Swift UI is pretty much based entirely on generic types. So I'd say one of the best practices of becoming a better developer is to embrace generics, learn how to use them, learn how not to use them, and truly don't be scared of them. So practice, practice, practice until you get the concepts, and then use them wherever you think and your teammates think makes sense. So without further ado, let's start talking about generics. So I'm just going to press Command in here and say a playground, and we say generics like this, and ensure you're creating it inside your workspace. So Swift Crash Course, and we create this generics playground, import foundation, and we say automatically run this. All right, I'm going to get rid of the explorer to the left hand side. Now generics is, for me at least, is used to avoid writing the same function multiple times, or writing the same code multiple times. All right, now generics, they kind of look a little bit strange, but they really, at the end of the day, once you've written the code for generics, you can use them in so many different ways, and you will be amazed by how powerful they are. Okay, so what we're going to do as the first example of generics, I'm actually going to jump right in and write kind of like a scary looking function. All right, but what this function is trying to achieve is that, I mean, its mission statement is kind of like this. It wants to expect any numerical data, such as a floating value or a double value or an integer, two of those values. So it takes a left-hand side and a right-hand side, and it expects us to pass it a function that can perform an operation on those two values and return a new value in response, such as, let's say x is 10 and let y is 20, and then we say let's c is equal to x plus y. So this plus function takes a left hand side and a right hand side and returns a result which is the equivalent of adding those two values, right? Now you can have minus in here, you can have division in here, you can have multiplication in here. Oops, if I can write it. So all these functions take a left-hand side and a right-hand side, so they do some operations, and they're actually operators. We've talked about operators before, okay? So let's say then we create a function. We say a function that performs a task, and we say it's an operator that takes an integer and returns an integer, kind of like this, okay? And then, oops, and then we say it performs this operation on a value on left-hand side of type int and right-hand side of type int, and then in itself returns int. Okay, so you can see it's performing an operation that actually does the job. I think we actually did something like this when we were talking about operators, and we actually put this as a trailing closure, I remember, but it's similar to that at least. And internally what it does is calls that op function and passes the left-hand side and right-hand side to it and returns this value in return. Then you can go ahead and say perform plus on 10 and 20. And then you can see it will just say 30 as a result, because this is actually a function. All right. And you can say plus, and then you can say minus. Of course, you can say multiplication in here, and you could also say division in here. Okay. So maybe we could say 20 and 10 in here for the division so that we get proper values printed to the console. So this is an example of this function. Now, your teammate comes to you and says, could you make this function work with doubles as well? Then be like, okay, then I'm gonna change this to double, and this to double, and then this to double, and then you have to go and change this to double, and this to double, and this to double. Then your code kind of works. All right, but the result of these is actually now a double. So if you look at foo's data type is a double. What happened to your integers? Well, you changed the function signature from int to double, and you lost the ability to work with integers. Then you'd be like, okay, then I need two functions, one for integer and one for double. Then you call this perform int. So we say, let's see if I can change this name, perform int. And then you say, okay, I'm smart enough. I go ahead and create a perform double. And I make sure that this double works with doubles. Okay, so whoever wants to work with doubles calls perform double, and whoever wants to work with integers works with perform int. Then your third colleague comes and says, okay, but I want to work with CG float, and which is another data type, which is inside the core graphics framework, which we haven't worked with right now, but you can say core graphics, and then you can say let x is CG, CG float is equal to 1. It's kind of like a double actually. And then you say, oh, CG float, then I have to create another perform function, which is called perform CG float. However, as you can see, this is not a very maintainable way of working. So this will just increase the size of your code base, and you have to constantly go ahead and add new functions to your application. Wouldn't it be really good if we could create a function that works with any numerical type? And if you look at integer, let's go to int in here, and then we see signed integer and then signed numeric. You can see that this signed numeric protocol conforms to another protocol, which is called numeric. Okay. And if you have a double value, let's say x is a double, 1.1. If you go to double and let's say numeric, there should be an extension on double, extension double, which makes it conform to that numerical type as well. So let's say binary floating point, I think, and then expressible by oops, not that one perhaps, by integer, literal, hashable, stridable. It is one of these implementations which conforms double to that numerical type that we were just talking about. I'm not sure which one it is. We have to dig deep inside Swift source code basically. But what I'm trying to say is that both double and int conform to a protocol called numeric. Now, if we could somehow in here say that this function works with any numerical data type, that would be really good. So let's change this to numeric. And then we say numeric, numeric, and here, here, and here. Okay. Now you'll see what happens inside your Swift code, and Swift tells you, okay, I understand you want to work with numerics, but you can't just add them like that. You can't just say that this function expects numerics. Numeric is a protocol, and if you want to use it here, you have to use generics. So the way to use generics is that you go right after your function name and you just open these less than and equal signs, kind of like in here. Then you designate a letter, usually a letter, but sometimes people use words as well. But it is very, very common to use a letter. So you say, okay, I want to represent numeric with a letter. Okay, I can't just say numeric in here because that is an existing data type. Let's just say n, okay, as a numeric. Then you say n should conform to numeric data type or protocol. Then anywhere inside your function signature where you're using numeric, just type n. Okay, so in here, right there, and also here, and also for the return value of your function. All right, so now you see all of these errors are going to go away. So you can see all of them went away and your function still works. And if I say let x, and then I look at the data type for x, you can see x is understood to be an integer. But how? You didn't say anywhere that you're working with integers. And that's the power of generics. The compiler is basically inferring the data type based on the values you pass here. So if you say 10 and 20, then it knows that they both are integers and the result should be an integer. And let's change this actually. It's not perform int anymore. It is perform, okay? Now, if you go and do, let's say let x is perform on 10.1 and 20.2, all of a sudden x is a double because compiler understood that, oh, these both values are actually double. They're not integers anymore. So it substitutes the return value, which is indicated by this n generic value, to the actual values you pass to this function in here. Okay. And you can also go ahead in here and say 10.1 and 20. What do you think x is going to be now? Well, the compiler is also intelligent enough to promote the value, the return value, to the more complex or more complete data type. The more complete and precise data type in this case is not integer, but it is actually double. So if you look at the data type for x, is indeed double. All right. So that was the first example of using generics in Swift. And I know it could look a little bit complicated, but the more you work with generics, the more you will actually appreciate them. We've now seen this example, I would say actually quite a simple example of generics in Swift. Now, when you have functions that have multiple generic parameters, in this case, we have just one generic parameter that we've called n of type numeric. But in other functions, you might have generic parameters, maybe two or three of them, or even more. In that case, the function signature might be getting quite long. You would say R is something and D is something else. So looking at this function, you would probably just get a panic attack just looking at the function signature. And that is why Swift allows you to create function signatures or generic function signatures where the generic parameters are stated at the end of the function declaration itself and right after actually the return type. So to demonstrate how that works as well, let's just take this that we have in here, the code that we have in here, and let's go and paste it right there. Okay, and we will just name this function perform2 and change all these instances to perform2 just to ensure that everything is working as expected. So in order to create a function, a generic function where the generic parameters are defined at the end of the function signature, you have to remove this generic type right here, or as many as generic types as you have. You remove them from the beginning or attached to the function name, and you go right after the return value and then define them right there using a where clause. So in here, we then say where, for instance, n is numeric. So this is an alternative way of creating generic signatures for your functions. And in here, you would, of course, you would still have n in there, but you don't actually tag n as being of type numeric. So this is just an alternative way of doing it. And some developers prefer this way simply because in here, you could just say A, B, C, D are your generic types. And at the end, you could actually say what those A, B, and C, and D are in fact of type of. All right, so just keep it in mind. It's an alternative way of defining your generic functions, and it will just perform exactly the same way it did in the previous example. Okay, now any data types such as a class, actually I can't say any data type, but classes and structures in Swift can conform to multiple protocols. They don't necessarily have to conform only to one protocol. Okay, and using this, you can basically create generics that are conformant to multiple types. So let's have a look at that right now. Let's say that we create two protocols in here. We say protocol can jump, okay, and then in here we have a function that says jump. So any type that conforms to can jump should have a jump function, and then we create another protocol in here that we say can run, okay, and can run has to have a run function. Then we go ahead and create a structure in here we call person, and we say it can jump and it can run, like that. All right, so this is conforming a new structure to two different protocols. We can get Swift to fix these functions up for us. In here, you can see in run, we say running, and in jump, we say jumping. Okay, I think the indentation was a little bit wrong. All right, and then we have that. Now let's say that you want to create a function called jump and run. Okay, so let's say func jump and run, and you want to take in a value in here of some type. You want to say, okay, I want some value to be of any type, and in here I want to say value jump and value the run. But since this value at the moment is of type any, it cannot have the ability to invoke the function jump or the run function. So you could say, okay, I want value to be of type can jump. If you do this, then you can do the jump function, but you can't do the run function. All right. So in here, what you need to do is to go ahead and define a generic data type in here. Let's say T, and we say this data type can run, can jump, and can run, like this. And then inside the function signature itself, you say the value is of type T. Now you can see if you type value, you have access to jump and run functions. So this is a way of combining multiple protocols in order to create a generic function signature where you have access to not only one protocol data, but also multiple, as long as basically you can make this as long as you want to. All right. So then we can go ahead in here and create an instance of person. We say person is an instance of person. And then we can say jump and run with the value of person. And we can actually change this value's external parameter type to nothing. So we can just say jump and run person in here. Okay. Now you can also have extensions on generic types. And one generic type that is very useful is, actually we haven't talked about them so much, but they're arrays. And arrays, you define them like this. You could say let names, for instance, is foo and bar. Now, if you look at the data type for names, you can see it is an array of string. So it is denoted by these square brackets. Now you can actually look at, if you just type, this is a string in here. Let's see if we can find the data type for array. So if you say array of strings, so this is an alternate way of writing the same syntax. Instead of this, you can just do syntactic sugar here and say array of string. Now, if you go to array, you can see it is a structure, and it is a generic structure. Basically, it's working with a generic argument called element. Now you can also create extensions on generic types. So by simply saying extension of string, you're basically extending an array of string. And this is new format. Actually, this is new syntax in the latest Swift versions. Previously, you had to say extension array where element was equal to string. So this is the old syntax, but the new syntax, you can just simply extend an array of string, which is a lot more readable. Okay. Then what you can do in here, since you already have, you've told the Swift compiler that you're extending an array of string, if you create a function, let's say we want to create a function on any array of string that finds the longest string. Okay, so we say longest string, and we return an optional string. We haven't talked about optionals yet, so just for now, know that this means that we can either return, actually, have we talked about optionals? Structures, enumerations, protocols, extensions, closures. No, we haven't yet. We will talk about optional soon, okay? But just know that this means it can either be a value or it can be the lack of a value equal to nil, all right? So, and the reason behind it is that you can always have, and the reason, I mean, this is an optional string, is that any array, like final names, is an array of string in here. It can actually be empty. Okay, so if this array is empty, how can you find the longest string in this array? Well, you can't. There are no strings in here. Okay, final it should be a let, right? So the reason this is optional is because of that. And then what you can do in here is to say let dot. You say self sorted. And this is, I mean, to be honest with you, you don't have to know exactly how this is working. And this is just an example. Okay, so we say sorted, and then we say left-hand side string, and then we say right-hand side string, and we want to say left-hand side's count. The number of characters in the left-hand side should be more than the right-hand side's characters. And then we say take the first argument. You can see the first argument is then deduced to be of type string, simply because we are extending a generic type whose elements are of type string. And if you look at this property, you can see it is using the same generic type called element. All right. So that's also extending generic types. And then you can go ahead in here and say, let's say we create an array of strings. We say foo, bar, and baz in here as one string, and then cox in here. Then we say longest string. All right. Then we can get the value of bar and baz printed to the console or the playground console, whatever you want to call it. Okay. Then we have another topic to actually discuss, and this goes to a little bit more, I would say, advanced, but I think generics are advanced topics to start with, so we shouldn't be scared of having a look at some advanced topics in here. So let's go ahead and talk a little bit about associated types in protocols. Okay, so and this makes generic protocols. We've already talked about protocols before, but we haven't talked about generic protocols. So let me just show you an example and demonstrate how generic protocols work. In the beginning, it might not make so much sense, but as we go on and complete this example, it will make hopefully more and more sense to you. Okay, let's create a protocol in here. We call it view. All right, so anything that can be displayed to the user, and we call it just view. All right, we say any view should have a function on it that is called add subview, and it is basically using the same view. So it says anything that's a view should be able to add another view to itself. All right, then we go ahead and extend this view. We say we had the add subview as a default implementation in here, and we say by default it is empty. All right, so the default implementation of add subview doesn't do anything. Then we go ahead and create a structure in here, and we call it button, and we say it conforms to the view protocol. And at the moment we say its implementation is currently empty. Okay, if we didn't have this default implementation of the add subview function, then button structure would have had to implement the add subview function in here, as you can see suggested by the playground. All right. So let's remove these comments from here. We go back to how we had it before. Then what we're going to do in here is to create a protocol, and we say, and we want to basically represent every object in our system that can be turned into a view. Let's say you have a struct person, okay? And then you say it has a name. And then you want to say, I want to somehow present this person on my user interface. And then you say, okay, I want to make it presentable. All right. So you could define anything in your system that is presentable as a view using a protocol. Let's say protocol presentable as view. All right. And this is kind of like hypothetical at the moment, but later in this course, we will actually talk about MVVM in iOS and macOS and watchOS using, for instance, Combine and Swift UI plus RX Swift and RX Cocoa. But for now, this is a hypothetical protocol, but it is very real. Actually, I use this in production today. So, and I just want to give you an example of how this could look like. All right. Now, if you want to turn a protocol to a generic protocol, you'd use a syntax or a keyword called associated type. And using associated type is almost as if you say presentable as view has some sort of a generic parameter. But this syntax isn't accepted in Swift. You get an error. Okay, you can actually see it says an associated type name v must be declared. So let's go ahead and define this. We say associated type, and we say view type should be any data type that conforms to the view protocol. You see what we did in here? We didn't just leave it empty. We said if something is presentable as view, its view should actually be of type view. All right, so it can either be a button or it can perhaps be struct table is a view. All right, and maybe the struct person will conform to presentable as view and say that my view type is actually a table. All right, again, this is hypothetical at the moment, at least. Then we say any object that is presentable as view should be able to produce a view for us to display to the user. So we say produce view is a function, okay? And this guy should actually produce a view of type, not view, but view type, all right? So if your view type is, for instance, button, then this function should produce a button. If your view type is table, then this function should produce a table. Then we can go ahead and create the next function in this protocol. Let's just call it configure. So we say anytime we want to present an object as a view, we can allow it to configure itself using a super view as its reference. So super view, and we say this is a view as well, and we say this view is view type. So we say the super view could be any view, but this view, type, but this view is of type view type, which is a generic parameter to this protocol. Okay. And last but not least, then every object that is presentable as view should have a function on it that is called present. All right. And in here we say view is view type, and then we say on super view view. All right, so this view, we're already sure it is of type view type because this configure function, this produce view function actually produces a view type, and that same view will be passed to this present function, okay? And a super view should be anything that is a view. Okay, so that was the protocol definition itself. All right, let's go ahead and define basically do some default implementation for some of these functions inside this protocol. So we say extension, presentable as view, and now this is a generic protocol simply because it has an associated type. All right, then we go ahead and configure we write our configure function in here. So like that. Let's just paste it in here and we say its default implementation is empty by default. All right. Then we will have we will implement the present function. All right, like this. And upon presenting a view on a super view, we just go to super view and we say add subview view. All right, because we already know anything that is a view has this add subview function on it. So we just call it. All right, then what we can do to make this all very exciting, we say we create a button called my button, which is presentable as a view. All right, then we know that this function, this button has to have two function implementations, and they're the remaining two functions. Actually, we don't want to do that. So you can see presentable as view requires three functions. It has a produce view, and it has a configure and present. And these two functions at the moment have default implementations right here, but the produce view function doesn't have a default implementation. So you can go ahead in here and say that you want to define produce view, okay? And then we change this and we say this actually returns a button as we've defined it in here. Button is a view. All right, and according to our protocol implementation, the produce view has to produce a view type that conforms to the view protocol, and button does that. It conforms to the view protocol in here, okay? So inside produce view, we just say we return an instance of button, just like that. All right, now what's going to happen is that you don't have to implement anything else except for this, but if you want to go ahead and, for instance, do this configure function in here, so as soon as you start typing it, let's say configure, you can see then Swift understood that super view is a view. However, this view is a button. But how did it understand that it's a button? The reason is that we changed the implementation of produce view so that it produces a button. Then Swift went to this protocol implementation in here and said, oh, produce view is producing a button. So everywhere in this protocol where I see view type, I'm going to replace it by button. So it did this pretty much. Button, button, and button. You can actually go ahead and test that by adding, for instance, also the present function in here. You can say present, and you can see super view. Ooh, the view is a button. So that's how generics work basically in Swift protocols. Okay, so it's very, very simple when you look at the whole thing, but if you go into details, you can actually see there's lots of things to learn about how generics work with protocols, especially, and associated types. So just know that for now, that protocols can become generics using associated types. And sometimes in Swift, you need to know about them and you need to use them. But if you're not working so much with generics, you probably don't have to bother so much with associated types. But again, if you feel intimidated by generics in Swift, I think you need to tackle that fear and go ahead and actually play with generics so much that you become so comfortable with them that it becomes a part of your day-to-day tool and day-to-day way of working with Swift. Okay? Now, if you want to extend generic protocols, just like you have extension on, for instance, here, you can see we have extension on this generic protocol. You can go ahead and actually constrain your generic extensions to specific types. So let's say that you say extension presentable as view, and then you can say where view type is equal to a button. All right. This way, you're creating an extension on any object that conforms to presentable as view, as long as that object's view type is a button. If you did this, let's see what Swift says actually. So we're just creating a simple extension of presentable as view. If you add a function to this, any object that conforms to presentable as view's protocol is going to get your extension values or variables and functions. However, this way, only presentable as view conforming objects that have a view type of button will get your extension. All right. So let's say func do something with button. So we are adding a simple function in here and we say this is a button. All right. Then let's go ahead and create a button. We say button is an instance of my button, And since my button conforms to the presentable as view protocol, we can say button, do something with button, right? However, if we went ahead in here and set structure, table is also a view. Actually, let's go to my button and we will just say my button is, we copy that code and we go ahead in here and we say my table, okay? My table. And in here where we have button, we create another struct and we say table is a view and we say it's empty as well, all right? Then we go back in here inside our my table. We say that my table produces a table. And in here, we just create an instance of table and we change this as well to table, all right? So, and we can remove the configure function as well. We don't have to have it in there. Now, if we go ahead and say my table, table is an instance of my table. If you say my table dot, you can see that you don't have access to the do something with button function. If you want my table to have the same extension, do something with button, first of all, you'd have to change the name of this function. So you say do something with view, for instance, with view, and then you also have to remove this generic constraint from here, because my table doesn't produce a button. It actually produces a table. Then your table, my table, will have to do something with view function as well. All right. So I hope that this makes generics a little bit more clear to us at least by this point. Now, apart from all of this, you can also, as I mentioned, like when we saw this extension on array of strings, let's see where we did that, longest string. Okay, you can also create other extensions on arrays, even though they're generic types, such as, for instance, calculating the average value of an array of integers. So you can say extension int, so any array that contains integers, and then you can say a function that calculates the average values, and we say double. And then we say self reduce. This is a special generic function on any array. And you start with a seed value. And in here, you do your operation. You basically, what it does is that if you have values 1, 2, 3, 4, it says, okay, I start with the value of 0. Then I go to your first element. Then I say 0 and 1. So then we say, okay, plus them together. It says, okay, 0 and 1 plus together will be 1. Then I will take this one and I will go to the next element, which is 2. And I will do this operation between these two. 1 plus 2 is 3. It says, okay, then I have 3. Then I go to the next element and say 3 plus 3. Okay, 6. 6 is here. And this says I go to the next element, 6 plus 4, it will be 10. All right. So this is how reduce actually works. If you take so basically this, if you say let xxx, and then in here we say xxx, you can see it's an integer, but we want to grab the average, then we have to divide this with the count of this array. So self.count, and we have to convert all of these to doubles so that they can actually produce a double value in here. Okay. You can see now it is quite happy with the code that we're written. And then you can say 1, 2, 3, and 4, and you get its average. All right, and you can see then the value printed to the screen right here, 2.5. All right, so if you had an array that was just like 2 and 2 or 4 and 4 in here, then the average would actually be the same value as you've entered in here. 2 and 2 will produce 2, and 4 and 4 will produce 4. Okay, so that's how you can extend existing data types that are generic, such as arrays. Okay. I really hope that all of these examples made generics make a little bit more sense to you. If they didn't, I think it is important that you go back and practice generics yourself as well, because without practice, generics will probably never make sense. Good, we're done with generics. Let's go ahead to the next section, which is optionals. So I'm going to create a playground in here, playground, and we'll say blank, and we'll say optionals, which is also a very fun topic to talk about in Swift. So let's just do that. Good. And then in here we say import foundation, and let's just do this so that it runs automatically as well. And let's get rid of our project explorer to the left hand side. All right. So optionals indicate a value that might or might not be present. Okay. So let's say that you want to take a value and multiply it by 2. Okay, so let's create a function that takes a value and multiplies it by 2. So we say func multiply by 2 in here, and then we say value. And you could say it's an integer and it returns an integer as well. All right. Then in here, you just say value multiplied by 2. In order to turn this data to, actually before I say in order to, let me just explain what optionals then would do for this function and how they would make this function perhaps a little bit more fun to work with. If you call this function multiply by 2, you always have to produce a value in here. So you can't just call this function empty, thinking that it will just produce 0 if you don't pass anything to it. Okay, you can see that it says, okay, you have to pass a value to me in here. Then if you don't want to do that, if you just want to say, okay, if value isn't there, just assume it is 0. Okay, what you could do is to say, okay, value is optional. So you say it doesn't have to be passed in here. And furthermore, you can assign a default value to it. So you say value is an optional integer that by default is not present. Then what you can do in here, you say if let value. So this is a syntax of unwrapping an optional. So you say if the value is present, then return value multiplied by 2. Otherwise, return the value of 0 like this. All right. And also there are other ways of actually doing this in Swift. So you can see now this function works fine because it's hitting this point, since if let value syntax indicated that value is indeed nil. There are other ways of doing this. You could actually change this code to this and do it like this. You could say it's an integer which by default is 0. Then it will work exactly as it did, but I'm just trying to demonstrate how optionals work and how if let works. It's a little bit difficult to find hypothetical examples for using optionals, which is a little bit complicated topic to explain, and even more complicated to find very trivial examples of how to use them. All right, but let's just leave this example as it is. So now you can see that you can call that function with either no values, or you could say you pass a value of nil and it will produce also 0. Or you could say you pass a value of 4 or 8 or whatever you want in here, and this function will still work. So even it works even with the value of nil. I don't know why our playground isn't really running yet. There we go. So we got our values. Okay. Now you can compare optionals with nil. Nil is a special value, meaning that the absence of a value basically. So you could say let age is an optional integer and it is equal to nil. All right, so it is not present basically. Then you could say if age is not nil, age is there. How odd, because we expected it to not be there. Else, age is nil, correct. Okay, so we kind of expect this branch to be executed right now, and you can see that it is. Okay, so that's how you can compare a value not being nil, for instance. Okay, now if you want to take an optional value and check whether it actually exists or not, you should use, actually not, you don't have to use, but you can use the if let syntax. So you say if let age, if age is present, then inside this block after if let, age is not optional anymore. So you can see it is right here. Okay, so then you could say age is there. How odd. Its value is age. All right. Otherwise, no age is present as expected, because we know that age is actually nil and we should get this printed to the console. All right. Now, apart from if let way of unwrapping an optional, you can also use another syntax, which is called guard. And guard does the negation of age basically. So let's have a look at how guard works. So let's say we create a function in here. We say check age. All right. And in here, we want to read age. We say, we want age to be there. If it isn't, then we're just gonna return from this function with a message. But if it isn't there, we return with a message. But if it is there, then we print something to the console, for instance. So you could say if age is nil, then you could say age is nil as expected. All right. However, there's another way of writing this function, and the way to do that is you say, let's say that this entire function depends on this age variable, right? However, if you type a function, if you type your code like this, anyone reading this code might not fully understand that this age variable is very important to this function's signature or this function's functionality. And that is why Swift has an alternative way of doing this check. So if your function depends on some optional values and it can't really continue without those optional values actually being present, you need to perhaps use the guard mechanism. So in here you say guard age shouldn't be nil, else then you say age is nil as expected, and then you return. Okay, so you're basically saying make sure age isn't nil. If it is, so this else reads, if it is, then do this. And inside guard, you always have to return. So if you don't return, you actually get an error. So guards have this property that they need to return because that's the whole point. Okay. And also using guard, you can unwrap values as well, as we'll soon see. So let's put this guard in here. And then we say the rest is age is not nil here. Strange, because we don't expect that. And then we call the check age function in here. So we should now hit this branch because age is indeed nil. So we can't just guard that it isn't nil because it is nil and it will end up being here. Okay. Now using guard, you can also unwrap values because you can see in here, if I say let xxx is age, and in here I say xxx, it is still an optional. All right. So even in here, if I select xxx is age, you can see xxx is indeed optional integer. However, in here we said make sure that it isn't nil. So it shouldn't be integer. So I kind of expect xxx to be an integer. All right, but it isn't. And the reason behind it is that we're not actually unwrapping this age. We're just making sure that it isn't nil. But the rest of the function doesn't understand that. And the way to fix that is to actually use guard let. So let's say let age2 int optional, and we actually set a value for it. We set a value of 0. Okay. Then we create another function in here. We say check age2, and in here we say guard let age2 otherwise. So if we go in here and say let xxx in here, let's do a return, and we say xxx is equal to age2. You can now see xxx is an unwrapped integer, it's not optional anymore. And that is simply because we did a guard let. All right. And in here we say age is nil. How strange. And then we return. And then in here we say age2 is not nil as expected. Value is equal to age2. All right. So this age2 in here is not this value anymore, really. It is unwrapped within this function. All right, then we can call this function as normal. We say check age2, and we should then hit this line in here. And you can see the value of age is indeed printed to the console. Value is 0. You can change it to 10 if you want to, and you can see that value being printed to the console as well. All right, so that's another syntax for guard, using guard let for actually unwrapping an optional. Now, optionals are actually an instance of an enumeration. This enumeration is called optional, unsurprisingly. So just like you can switch on enumerations, you can switch on optionals. So you can in here go ahead and say switch age. All right, and you can get help from Swift to complete these for you. This switch statement, you can go in here and say fix it for me. You can see this optional enumeration actually has 2 cases. Let's see if we can find it. Enum optional, there we go. And it either is the value of none, meaning that it is nil, or it has some value inside it. All right. So in case of none, let's just say age has no value as expected. In case of some, we can unwrap it and say, let's say value, and we say age has the value of value like this, and we can break in here as well. Break. Okay, so age was nil if you remember, so we kind of expect to hit this case in here, which is none, and it says age has no value as expected. All right, so that's how you would switch basically on an optional value. You can also go ahead and do simple comparisons. So if you could say if age2, for instance, is equal 0, so you could do that, then you say age2 is 0 as expected and is not nil. And let's go to age2 and actually make sure that it is 0. So let's change it to 0. And in here we say else age2 is not 0. How strange. All right. And as you can see, the comparison is working. So you don't, so what I'm trying to say in here, you can actually compare an optional value with another value like this without having to say if case let or is it let case or caselet? I always forget that. So you don't have to unwrap it using a caselet or using a switch. You can just compare it with an unwrapped value like this as well. Okay, now you can also, just like we did this comparison, you can also compare with the none or some cases. So let's just copy and paste that code in here. Then we say if h2 is equal to some 0, then you say the same code in here. So these two are equal to each other. I mean, they're not equal, but they're identical to each other. So it is completely up to you how you want to do this code. For me, if I see this code, I don't assume that h2 is optional, but is indeed optional. But if you write your code, for me, I completely understand that, oh, h2 is optional. So this is a little bit more descriptive of the problem in hand. So I actually would probably prefer this, but it is up to you and your team to decide on a convention on which one makes more sense to you. Okay. Now you can also do optional, something called optional chaining. And that means you optionally access optional properties or methods of some classes or structures. So let's create an example for it. We say struct person, and we say let name is a string, and we say let address is, let's actually not do that at the moment. Let's inside this structure create another structure called address, okay? And in here we say let first line is a string and it's optional. All right, so if we have an address, then its first line might not be present. And also, additionally, we go into person in here, we say addresses itself is optional. So even if it is present, it doesn't have to have a first line. But if it's not present, it will be nil. All right, so it's like optional within optional. So this is optional within this optional. Actually, the other way around. Address is optional, and within it there is another optional property. Okay, let's create a person in here. We say foo is a person, and we say it is equal to an instance of person with the name of foo, and its address is nil. We just say we don't have an address. Okay, then if we say we want to get this person's first line of address, then we say if let foo first address line is equal to foo, then dot address, and optionally grab the first line. All right, so it means address is optional. We know about that, but go and grab its first line if it is present. Then we say if let, okay, is equal to that, then we print it out, foo first line. Otherwise, we say foo doesn't have an address with first line as expected. So since we didn't have an address for foo at all, then it shouldn't even have a first line. Okay, so this address, basically Swift stops right here. It says I can't go any further after address because address in itself nil. So I can't grab the first line of it. Even if first line did exist, the address itself doesn't exist. Okay, so then we get this message printed to the console. Now we can go ahead and do another, like an alternative way of grabbing this value is by first grabbing the address and then out of the address grabbing the first line. It is a little bit more code, and I don't actually think you win so much on it. So I just wanted to show you how you can do that as well. Let's say if let foo address is foo.address. So you first unwrap the address, okay? And then you say, okay, after that, get the first line as first line, like this, is equal to foo address dot first line. Then you can say foo address, and then you say first line. All right, but we know that we don't get in here because foo's address is in fact nil. So we don't even go inside this code in here, and not in here either. Okay. Now you can compare optionals using chaining as well. So let's go ahead in here and define a bar person. We say bar is an optional person actually, and it is equal to person whose name is bar and whose address is in fact an address instance with the first line equal to nil. All right, so it has an address, but its first line is nil. Then we say if bars, and you see we're accessing bar using an optional, like a question mark, simply because bar in itself is an optional value. If bar's name is equal to bar and bar's address first line is equal to nil, then we say bar's name is bar and has no first line of address. Okay, otherwise then we can say seems like something isn't working right. because we know that bar's name is indeed bar and has an address, but its first line is actually nil. Okay. But do you know this line of code actually isn't saying that it has to have an address, but its first line should be nil. It could actually work as well. It will work as well if the entire address is nil. So let's just change it to nil, and you can see still the same code will be executed. All right. So that's how optionality works. It just continues until it can't continue any further. Okay. Now you can also switch on optionals with where clauses. All right, using optional chaining. So let's create a Baz person in here. I'm just going to copy paste that code so we don't have to create many persons. In this time, it's an optional person with an address that is present and it has a first line as well. All right, then we can go ahead and say switch on the Baz address first line. All right, and in case we say in case of sum, we say let first line. And we just break in here and we say case and none. Actually, let's not do that. Let's just say case first line. And then we can go ahead in here and add a where clause. So this is pattern matching. And so we're saying, okay, if the first line is available and using this where clause is pretty much just saying and the first line starts with the string Baz. Okay, then we say Baz first address line is equal to first line, like that. Then we say case let sum, and then we say first line, and we don't have a where clause anymore. In this one, catches all. Then we say Baz first address line that didn't match the previous case. And then we print the first line. All right. And then last but not least, we also have to cover the none case where the optional value is indeed nil. We say Baz first address line is nil. Weird. Okay, because we already know that Baz's first address line is in fact Baz first line. And you can see this being printed to the console. It says Baz first address line is Baz first line, as it was in here. So you can have where clauses in your case statements for switching on optional enumeration or enum values. Okay. Now you also can choose to if you're using if-let or guard-let, and you should do that as long as it makes sense to you. All right. So let's create a function in here. Let's say we say func get full name, and then we say we have first name as a string, and then we have a last name as an optional string, and we produce an optional string as well. All right. Then we say that you have to have a last name. All right. Even though the function signature says optional, we say that, okay, you should have one. We said if let last name. If we can unwrap it, then we return first name and name and space. Then we say last name. All right. Otherwise we return nil. All right. Now that's one way of doing it. So you can just in here say get full name, and for first name we say foo, and for last name we say nil. Then we call the same function with foo and bar as names like this. So this one has a last name of nil, so it should end up being here, and you can see it's actually producing the value of nil. And this one has both first name and last name, therefore it is returning foo bar as its result. So that's one way of doing it, but you can also go ahead and use guard-let. So if you copy this code from here, and then we go and paste it right here, and we say get full name too, and in here you could say guard-let last name, otherwise return nil. And then you switch these statements basically. All right. So basically the way I usually read this is like this. Make sure last name is present. Otherwise return. And then do this. Otherwise, basically saying if last name is present. Okay. So after doing a guard-let, all statements after that guard-let, if we hit them in those statements, the value that you unwrapped in here will be present as a non-optional. All right. So that was also short and sweet
about optionals. And there's lots more to actually explain about optionals, and they pop up pretty much everywhere in Swift, and especially Swift UI, as actually we'll talk about Swift UI later in this course as well. But just know that they're there. You need to learn them if you're working with Swift, and it is very advantageous if you can really master optionals in Swift, because they're pretty much everywhere. I hope you enjoyed this section of the course as well. And in the next section, we're going to talk about error handling in Swift.
Now that we've talked enough about optionals, let's first do some cleanup here in our workspace. So I'm just going to press Command W and close all these tabs that we have opening here. There are quite many, and they're not really contributing to so much right now. Rather, they're just like making our workspace look a little bit dirty. So I'm just gonna do Command W in here, and if you're in Visual Studio Code, for instance, on Linux, and or even actually replace build. Oh, okay. I don't know what happened really. And even if you're on Linux and you're, for instance, having Visual Studio Code open with your Swift files, you can also close them if you're not really interested in having them all open at the same time. So as mentioned, we're going to go and talk about error handling right now. So I'm just going to press Command N and say blank in here, playground, and let's say error dash handling. And I'm going to create it in the main workspace in here, as you can see, okay? Let's press create in here and say import foundation. And like usual, we're going to go in here and say that it should automatically run all our code, okay? So error handling is one of the most important concepts in any programming language that supports errors and exceptions. And really the point of errors and exceptions are to tell the caller to our code, or whoever's using our code, that something has gone wrong. It's either the failure of the code that we've written, such as an error, or it's the failure of the person calling this function or code, such as an exception. So there is a little bit of a difference between actually errors and exceptions in different programming languages, but in Swift, usually we only talk about errors. So meaning that the code found out that something hasn't gone according to the plans, and then it throws an error. And actually the word for it is actually throw in Swift indeed. So there's a keyword for it called throw, okay? And it is the same thing in many other programming languages. Actually, it is called throw in Dart, for instance, as well. So let's have a look at an example of throwing an error in Swift and catching it. So we're going to create a person in here. Let's see if I can spell struct person. And let's say we have a first name, it's an optional, and we say last name optional string as well, okay? Then we want to create a function in here called get full name, and this function should ideally return a string, okay? So we're gonna say func get full name, and we say it returns a string, right? However, how can it return a string if first name and last name are both optional, meaning that they could at any point both be nil, or one of them could be nil, and in those cases we cannot produce a full name. So the goal of this function is to return a string. It shouldn't really return an optional string, because a full name shouldn't be optional. Then what we're going to do in here, we're going to say, okay, it is going to try to produce a string, but it may actually throw. So we say throws. Okay, so the function throws, but inside it will throw. All right, so that's how the verb and the noun basically work. Actually, I think it is a noun. Yeah. So the function is marked as throws, meaning that internally it can throw an error. Now we're going to go ahead and define our errors inside this structure. Then you don't have to define them inside the structure or the class that throws them, but it is usually good practice to define them within their enclosing structure or class, so to associate the error objects with that structure or class. Okay, so we're gonna go and say enum errors, for instance. It doesn't have to be called errors. You could call it my errors or person errors, whatever. Okay, person errors also works, but in here we're just going to call it errors, and we need to ensure that this enum conforms to this error protocol. Okay, you can see it is a public protocol. Okay, so you cannot throw errors that are not actually your enum. If you're actually going to throw its cases, the entire enum needs to conform to the error protocol. So that's the rule basically. Then we're going to say the first case of the error is, for instance, first name is nil. We're going to say then last name is nil, and we're going to say case both names are nil. So these are the available errors that this function can throw. So these are the three things that can go wrong. Either the first name is nil, or the last name, or both. In any other case means that name and the first name and last name are not nil, and we can calculate the full name successfully. All right. So as we've actually learned in the optionals section of this video, optional data type is it is an enumeration, meaning that we can do switch on them. So if we want to basically learn whether these two are both not nil, you could either do it like this: if let first name and let last name, then you can produce the first name like this, first name and then last name like this. Then you should say else if first name is nil and last name is not nil, then you should say throw, and you say errors first name is nil. Then you have to do a lot of else statements in here to understand, okay, first name wasn't nil, last name was nil, and then throw last name is nil, and if both of them are nil, then do this. So it's a lot of if and else statements. Instead of all of that, we can just do a simple switch statement in here. Okay, so let's just say we switch, and we say we switch on the first name and the last name. All right, so this is the first time we're doing a switch on two enums at the same time. All right, so the first case we want to handle when they're both nil. So we say case, the first one is none and the second one is none. Okay, in this case both names are nil, so we say throw errors both names are nil. The next case, we want to make sure that we want to basically see if the first name is nil but the last name is not nil. So we say first name is nil and the last name is not nil. Remember, some and none, they're the cases of optional. So if you go in here, do you remember these? None and some. Some meaning that there is a value. So we're saying that there is no value for first name, but there is some value for last name. In the case of not having a first name, then we throw an error and we say first name is nil. Then we reverse these. So we say in here, we take this none, we say the first name is some value, but the last name is no values. And then we say last name is nil. And in the other case, then we say in the case of actually having a first name and last name, so we say case let some first name and some last name in here, then we can calculate, we say return, and we return a string with the first name and last name in here, just like that. Okay, so this is like some sort of pattern matching, you could say, in Swift. And pattern matching in Swift is very powerful. I mean, I would say it's even more powerful than pattern matching, for instance, in Rust, which is also in its own very powerful. But Swift has some really neat features when it comes to pattern matching with switch statements, for instance. Okay, so let's go ahead now and create an instance of this person structure. We say let, oops, can I spell? Let foo, and we say person. And for the first name, we're going to say foo, and for the last name, we're going to say nil. All right. So now we want to go ahead and grab the full name of this person, and knowing full well that the last name is nil, meaning that we're going to get into this case. Actually, no, sorry, this case, last name is nil. All right. So how do we do that? Because if you go ahead and say let full name is foo, get full name, you can see that we're going to get an error from Swift saying that actually it's very important that we see this error. It says call can throw, but is not marked with try. It says, well, it can throw, basically. It can throw an error, but you're not trying to resolve that error. So the keyword for trying to resolve an error, or trying to actually call a function, for instance, that can throw, the keyword for it is try. Okay, so you say try. However, we're going to probably get another error now, and it says, well, it crashed. So the entire playground pretty much crashed. And the reason is that this function threw, but we tried this inside a context that doesn't have error handling. So if you're using try, then you need to be inside a context in which you're handling your errors. And that type of context is created with the do keyword. So you say do, and then you place this code in here, okay? And in here, then you can go ahead and say catch, and then you say got an error. And there is an internal error object in here, which is just called error, okay? And you can see now we are getting this in here, and it says got error, and it says last name is nil. So this is according to what we basically expected. Okay, so just remember do and catch, and inside the catch block, if you don't specify anything in here, like let's E or something, because then we're gonna get E in here. If you don't specify how you want to catch into which variable, there is an internal hidden variable called error inside every catch statement. Okay, good. Now, if you also want to, I mean, this just catches every error, any error pretty much. Okay, so if you go in here and say foo, the first name and last name for it is nil. Now you see you catch another error that's called both names are nil. Okay, but what if you want to catch specific errors? You don't want to catch every error. You want to catch, for instance, specific errors. You can say I just want to catch person errors. Okay, and any other error that happens in here, I don't want to catch it, because remember, inside the do statement you can actually have a lot of code. You can have a lot of code in here, and you can say let blah is try something else. Okay, and any of these statements that have try before them, they can throw, and then those errors that are thrown could be of different types. So within the do statement, you can have multiple lines of code, each of which can also throw different types of errors. If that is the case, how can you catch specific errors? And the way to do that is using the is keyword after catch. I'll show you. So let's copy this in here that we have and paste it, and then we put the full name in here just so that we get the full name printed to the screen, if any, but we already know that there will be no full name. And in here we're going to say catch is person.errors, like this. Okay, and you can see in here this statement still, I mean, let's see, error. Okay, we're going to get rid of this one because we already know that is a person error. Okay, so we have pattern matching basically on our catch, and we can't actually grab the variable out of it anymore. So we detected that it's a person error, and then the error variable isn't available to us anymore after doing this pattern matching. Okay, so this is how you would look for specific types of errors in your catch statements. All right, now you can also catch specific errors. I mean, here you're basically matching the error against a type. But then you would be asking yourself, well, but how do I know which one of these errors it is? Okay, and you can actually catch specific errors just by typing catch which error. Okay, so let's copy this code. Actually, maybe let's create another variable in here. We say let bar equal to person, and in this case we say both first name and last name are nil. All right, like this. Then we're going to copy this code that we have in here, and right after bar, we're going to paste that, and we say full name is bar get full name. All right. And then in here, inside catch, we're going to change this code that we have, and instead we say catch person errors, and first name is nil. Then we say first name is nil, like that. And then I'll copy this, and I say we also want to catch last name is nil. And we say last name is nil. Then we say, okay, we also want to catch person dot errors. Both names are nil. And we say both names are nil. And otherwise, at the end, we have a catch all block in here. And we say some other error was thrown. Okay. So now you see, we're basically getting this error in here. Both names are nil as expected. First name and last name are basically nil. Okay, so this is how you can catch specific errors as well. This is how you can catch error types, like errors of this type. But inside this, we already know that we have 3 specific errors. And if you want to catch any of those specific errors, you can do just catch and that specific error. Okay, so that's another way of handling errors. Now, we've had a look just at one function at the moment that can throw, but you can also you can basically throw errors inside constructors as well of structures or classes, meaning that you try to construct an object, but the parameters that you're passing to that object are somehow not valid. So as you know, the constructor or initializer of classes and structures have complete right to do some validation on the data that you're passing to them. If those data for some reason are not correct according to the validation of that structure or class, then the class or structure should be able to throw. Okay, and I'll show you now how you can define throwing initializers or constructors for structures and classes. So let's create a struct car in here, okay? And then we say let manufacturer, and this manufacturer is a string. Then what we want to do is to create a constructor or initializer for this car that looks at the manufacturer that you pass to us, and if it is empty, then it's going to throw an error, because at the moment you can say my car is a car with a manufacturer of empty string, and this is not valid according, to our rules. You shouldn't have a car that doesn't have a manufacturer, okay? So we want to basically catch this case. We want to see, okay, when you pass the manufacturer to the structure, is it empty? If it is, then we want to throw an error. So let's go ahead and define that error first. So we say enum errors, and of course we have to conform to the error protocol, and we say case invalid manufacturer. It is a very complicated word to type, in my opinion. Then we go ahead and we say, okay, we have an initializer in here which takes in the manufacturer. Okay, so I'm just going to copy this so I don't have to type it anymore. And then in here we say this init function or initializer actually throws. And then we say if the manufacturer is empty, then throw errors dot invalid manufacturer. Otherwise, self manufacturer is equal to that manufacturer. Okay, so you can see then we don't have a problem in here. The only problem actually we have is that we're now calling this, now Swift understands that this call to the initializer of car is throwing, but we're not trying it. Okay, so let's go ahead and do a try on this. So we say do, and then we say we catch car errors, invalid manufacturer, and we just have a catch-all case in here as well. So we go into the do, and we say try this code, and in here then we say invalid manufacturer, and we say some other error, just like this. Okay, now you should be able to see that we get this invalid manufacturer pass in here. So now the important thing is also that if you're inside this do clause, and after this try statement, you can definitely use my car. So you can say my car.manufacturer, do whatever you want with it, but you already know that none of this code is going to be executed, because the way we're calling this car, or the initializer of the car structure, is that it's going to throw. So it's never going to reach this code in here. So Swift reads this code, goes and calls the constructor, and it gets to this throw and just immediately jumps out of this into its catch statements and says, okay, do I have any catch that matches the error that was just thrown? Yes. And it then comes here, and it doesn't even go here. Okay, so you need to kind of follow the path of the program to understand what is happening really. Now, you sometimes may not really care about the errors that are being thrown from functions or initializers, for instance. And the way to do that is that you want to grab the value of a function optionally. So you say, if this function is successful, get me the value for it. So you don't actually care about the errors. Okay, so let's go ahead and have a look at the syntax for it. And the syntax for it is using if let. Okay, so you said if let your car is equal to try with a question mark. So this is simply try with a question mark, simply means that you don't have to have a do and catch statement. It says optionally try to call this function, and if it is successful, then give me the value back. Okay, so we say Tesla, and then we have access to, we say success, your car is your car, like this. Otherwise, we say failed to construct, and error is not accessible now. So if you do this statement in here, so you can see we're passing Tesla actually to the constructor for our initializer for car. Therefore, this logic is not going to be called, and a proper instance of car will indeed be created, meaning that we will indeed come in here inside the success block. All right, so we optionally try to call this function. If it was successful, if it didn't throw, then we come here and then we have full access to this variable. All right, otherwise we get to this clause, and as you can see, I've typed in here we lose access to the error that was actually thrown. So we don't have access to the error object really in here. Okay, so that's how you can optionally try to call a function that throws and grab its value. Now, you can also, in some very rare cases, very angrily try to unwrap the value of a function that can throw. But please know that in all my years of working with Swift, I haven't done this. I know that it is available, but you should, as a Swift programmer, know that it exists, but you should almost never ever use it. But, and the reason behind it is that this code, as I said, angrily unwraps a function that can throw, meaning that your program or your application or your iOS app or watchOS app or macOS app will indeed crash completely and completely close should the function that you're invoking actually throw an error. And the syntax for it is not with an optional try, it is indeed with how do you call this actually? Exclamation mark. Okay, so let's go ahead and have a look at this. We say let their car is equal to try, and we say car with the manufacturer of Ford. And you can see now this will indeed be a valid car instance, and I can say their car dot manufacturer. Nothing really happened, and you think, okay, but why did he say that you should never use this syntax? And the reason is that should this manufacturer be empty, this whole playground will crash, and it will just, you can see in here, and encountered a crash and could not finish executing. And this same thing will happen to your app, whether it's a macOS or iOS or watchOS app. Your app will completely crash. It won't look as pretty as it did in the playground, because the playground, it still was open, but it just told you that it crashed. If it is in a real application, the application will just completely close and the user will be baffled by what just happened. So please don't use this syntax. Try to always do, I mean, ideally you should do and catch. If you can't do that, please do try, and please never try this. Never try this way of unwrapping values unless there is a very compelling reason for it that you and your teammates, for instance, are completely comfortable with. Okay, now we've already looked at throwing errors from functions, but just know that you don't necessarily have to throw a specific type of error. In here we have just one enum, and in here we also had just one enum that define our errors. But any function that is marked as throws can throw any error. It doesn't necessarily have to throw errors from just one enumeration. So let me just show you how that will look like. Let's create a struct in here, and we call it dog. All right, like this. And inside this, let me actually create some empty spaces so we can do this. So inside the dog structure, we're going to create two variables. One is called is injured and is sleeping. Okay, so is injured bool, and let is sleeping in here, boolean. All right, and then we go ahead and we want to create two functions, a bark function and a run function. So let's say func bark and func, and we say run. Now inside the logic of this dog structure, we're going to say, okay, we're going to bark like this, but we're only going to bark if we're not sleeping. All right, so we're saying if is sleeping like this, then we want to throw an error. So let's go ahead and define the error for that. So we say enum barking errors, and we say error, and in here we say cannot bark is sleeping. All right, then we say if you're asked to bark and you're sleeping, then we say throw barking errors, cannot bark is sleeping. All right, otherwise we bark. And then we do something similar for this. Actually, let's see what error we're getting in here. Throw. Okay, because this function is not marked with throws, so let's just change that to throws, and we're also going to change this function to throws. Okay, now we're going to go ahead and create another enumeration in here, and we're going to call it running errors, I think. Let's just say enum running errors, error, and then we say case cannot run is injured, and we do the same thing in here. So let me just copy this code and put it inside run, and we say if is injured. Okay, so we cannot run if we're injured, then we say running errors, cannot run is injured, otherwise we say running or run, something like that. Okay, so I think you get the point. So you cannot bark if you're sleeping, or actually not you and not me either, it's the dog. So the dog cannot bark if it is sleeping, and it cannot run if it is injured, unfortunately. Okay, so now that we have those, we will also go ahead and create another function, and we say func bark and run, which combines those two functions. Then we say try bark and try run. Now what happened in here? We just said try without having a do and catch. What happened is that we're inside a function that can throw. And if you mark your function as throws, you can simply just try things. You don't have to wrap them inside do and catch. What happens is that if any of these functions that we have inside bark and run throws, then this function itself will throw. So if you call this function and you call bark, then Swift goes in here and it says, oh, is it sleeping? Yes. Then it throws this error from this function, and since that function was invoked from this function, then it will throw the error essentially from this function out to the caller. Okay, so if you have a function marked as throws, inside it you can try statements without having to wrap them inside do and catch. In some rare cases, you actually want to wrap them inside do and catch because perhaps, let's say that your backend developers tell you that, hey, if someone calls this function and this particular function throws an error, then I want you to actually send an API request to the backend to log that error, because that should never happen, for instance. Okay, so then you can say do, okay, try, and then you say catch, and in here you'll do your API. Okay, you do your API call. All right, and then you can actually rethrow this error as well. So, and we probably will talk about that soon as well. But just know that inside a throwing function, you can try your statements without having to wrap them within do and catch. Okay, so let's go ahead and create a little dog in here that unfortunately is both sleeping and injured. So we say dog is an instance of dog which is injured and is also sleeping. All right, then we go ahead and we create a do and catch block in here. We say do and we say catch dog barking errors, cannot bark. And also we want to catch dog sleeping errors. Actually, what did we have? Running errors, sorry, running errors, and cannot run is injured. Okay, so you can see how we're catching both of these errors at the same time just using a comma. And we'll also have a catch all in here. So we say cannot bark is sleeping, or cannot run is injured. All right, and in catch we say some other error. And inside do, we're going to say try dog bark and run. All right, so you can see now when we do that, we get this catch statement in here that says cannot bark is sleeping or cannot run is injured, because we've basically caught both of these errors in the same clause. All right, you can separate them if you want to, just using separate try statements. Now if you go and change these to false, you will see that none of those errors will be thrown, meaning that we will just not see anything in here basically. So we can say dog just to confirm that this try statement actually ran its course and went to the next line 115 here. Okay, let's revert them back in here so we have this example as well. Now in case you're catching errors in separate catch statements, just know that only the first thrown error will be caught. All right, so in here we caught both of them. But again, Swift called this block not because both these errors happened, but it called this block because at least one of these happened. Because remember, when a function throws, the execution of that function completely stops. So barking throws an error. Swift doesn't even go to running, meaning that this error will never be thrown. Therefore, only the bark function will throw its error, which is right here. Swift just completely stops the execution of this function and I will basically run its course out of it, step out of that function. This error will be thrown and then we will come in here. Okay, and we can actually test that. Let's copy this code and paste it in here, and then we're going to go ahead and separate these catch statements, and we go in here and we say catch first, cannot bark is sleeping, and we say cannot bark is sleeping. Then we will say catch dog dot running errors, cannot run is injured, and we say cannot run is injured, like this. And you'll see now only the first error that was thrown will be caught, which is cannot bark is sleeping, even though this dog is both injured and is sleeping. But the run function will never be called inside the bark and run function, simply because bark threw an error, breaking the entire function call basically in here. Okay, so that's how you can actually understand how you can catch various errors. And I hope now you know basically the flow of when errors are caught, and that you shouldn't really expect to be able to catch multiple errors at the in the same do statement basically. All right, Now let's talk about rethrows. I said that we're probably going to talk about rethrows, but I think it is time now to talk about it. So when we talk about rethrows, we're talking about a function that internally calls another function, which can also throw. So let me just show you an example. Let's create a function here called full name, okay? And we take in a first name, which is an optional string, and then we say a last name, which is also an optional string. And we say, okay, we ourselves cannot calculate the full name. We actually need a function that can do that for us inside this function. So this poor little function can't really do anything. It just takes the first name and last name and calculates the full name. Now, this error is really stupid. I mean, it is really not how you probably want to do your write your Swift code, but it is just here for the purpose of demonstration. Because if we didn't do a simple function like this, which looks dumb, we would have to go ahead and create a very complicated function, which indeed is production ready, and you would probably use it in production code. But this is a little bit easier, at least, to get into what rethrows keyword means in Swift. So please just bear with me. So we say we have a function that actually does the calculation. We call it calculator. It takes in a string. It takes two string optional parameters, and it is a throwing function. So we say it actually throws and it returns a string in return. Okay. And then we just do this. Then we create our own function body in here. So all these errors are going to go away. Now, since this function is going to call this function, it has to do a try, right? Because this function throws. Therefore, this function should also throw. So then we say throws. All right. And also produces an optional string. Then, okay, we say try calculator. And in here, we have to pass the first name and last name. So we say first name and last name. All right. So if you look at this code, you will now see, okay, we're trying something in here. Okay. And our function is called, is marked as throws. Anyone looking at this function will think that somewhere inside this function, we're probably throwing a specific error, like we're actually have some errors that we know what they are and we're throwing them perhaps, okay? However, there's another syntax for this, and it is called rethrows. And how this really works is that this tells Swift that this function in itself doesn't throw anything. It is gonna basically invoke some other functions that throw. All right. So we could have gone in here inside the bark and run function and say this rethrows. Okay, and you can see that our code will, let's actually see what happened, must take a throwing function argument. And this is really good. We're seeing this. I mean, this is an example why we actually didn't mark this as rethrows. So in order, I mean, the error is a little bit cryptic, but what it is telling us really is that if for a function to be able to be marked as a rethrows, it has to have an argument that is a closure which throws, and it should call that argument. And since this bark and run function doesn't have any argument that is a closure, it doesn't even have any arguments, then it cannot be marked as rethrows. Again, that's what that error was telling us. However, this new function that we have in here has an argument that throws, and we're actually calling it using try. And therefore, we can mark our function as rethrows. And this tells Swift that this function in itself is just calling an argument, which is a closure, which in itself throws an error. Okay, so it's just a way of telling Swift that, hey, we have a throwing function in here, and we're just calling it, and just we rethrow the errors that this function might eventually produce. Okay, so let's then go ahead and create an enum in here. And then we say enum, enum and name errors, and it conforms to the error protocol in here. And we say case first name is invalid and case last name is invalid. All right, then we create a function that can produce a full name based on a first name and last name. So we say func plus, so it's an operator. Then we say first name is optional string in here. Then we say last name as well as an optional string, and we produce an optional string in return, okay, like this. And we also can throw. All right, good. And you can see we created this function with first name optional, last name optional, and result optional as well, and throws. And this function signature matches this. You see optional string throws and returns an optional string. And the reason we created this function is simply because we want to call this function, and instead of the calculator, we're going to pass a reference to this plus operator in here, okay? So let's say we want to ensure that both first name and last name are presented. So we say guard let first name, so we ensure that first name is available, and we say in case the first name is empty, okay? So the way you should read this statement is that we say make sure first name is available and make sure first name is not empty. Otherwise, this is how I usually read my guard statements, okay? Make sure something and something, otherwise, which is this else, do this. Throw name errors, first name is invalid. All right, so if first name is nil or that it is empty, then we throw this error. Then we're going to do something similar like this. Then we say guard let last name, ensure last name is present and that it is not empty. Otherwise, say last name is invalid. So you throw that error. And if everything then goes fine, then we say return the first name and last name. And you see these variables in here are not optional anymore. And that is simply because we're doing a guard let. Okay. After guard let is executed, if last name is nil, then you never get here. And that's why Swift knows that if you did get here, it means that you've already checked that last name was not nil. Therefore, the data type for last name is not an optional string anymore. It is actually a string. Same thing with first name. It is string and not an optional string. Okay. Now that we have those, we can go ahead and try to invoke this function right here, which is full name. So we go ahead and say we create a do block in here, and we say let foobar is try get the full name, and we say first name, let's say first name, we say nil, last name is nil, and for the calculator we pass a reference to our plus operator in here. Okay, and then we say we have to catch some errors in here. So let's say catch, and we say name errors, first name is invalid, then we say first name is invalid, then we say catch also name errors, last name is invalid, last name is invalid, like that. And then we'll also have a catch-all block in here. We say catch let ERR, for instance, and we say some other error, and that is equal to ERR. Okay, and you can also put parentheses around this as well, but this is completely optional. I think actually this is a little bit cleaner to read. So now you can see that we're getting first name is invalid thrown in here. Okay, and that is simply because our code just came in here and was like, can I unwrap first name? Is there a value in it? Nope. Then it throws this error. So it doesn't even go here, and it definitely doesn't go in these cases either. Okay, so let's change this. Let's change the first name to foo, and you will see that your error will be the other one, which is last name is invalid. And then you say last name is bar, then all of a sudden your function is going to produce foobar for you. Okay, so let's go ahead and do one more test. In here, you can see that our function, which is this operator, is marked as throws, but it is still returning an optional string. However, internally, it never returns nil. It either throws, which is caught by this guy, or not caught by, it is covered by this guy, or it actually returns a valid string. So why is it marked with returning an optional string? And this is actually a really good question. It doesn't necessarily have to be an optional string. It is better that it is not. And it still matches inside this function signature. So because this is a promotion, a string that is not optional is a promotion of an optional string. So it can always match it, but a demotion will never match inside a function signature. Okay, so you can, if this requires a string, you can never use a function that returns an optional string. You will actually get an error now, or we should get an error. There we go. Okay, so just remember, a promotion will work, but a demotion won't. And this is a promotion. We're saying that although you need an optional string, which is at a lower level, meaning that it can be nil, but we will always produce a string, which is at a higher level, meaning that it's never optional. So it is a promotion. A promotion in function signatures in Swift always works. Okay, good. We've now talked about that. Now let's also talk about results. And results are also very important to understand. They're kind of related to error handling. So that's why I wanted to name them. And they're usually useful when you're writing API calls, okay? So what we want to achieve in here is to create a function that is called getPreviousPositiveInteger. And you will pass an integer to this function, and the responsibility of this function we're going to develop is to find the positive integer right before the integer that you pass to it as an argument. So if you pass 2, this function is going to have to return the value of 1. If you pass 1, this function has to return 0. But what happens if you pass 0? There is no more positive integer before 0, because the next number, if you do a -1 to basically say 0 minus 1, you are going to end up with -1, and that's not a positive integer. So you could say, well, let's just throw an error. And you'd be right. You could just mark your function as throws, but there's another way of doing that. There's another way of saying that a function fails, but it fails perhaps a little bit more gracefully. It doesn't actually throw an error, but it carries an error with it, okay? And this concept is also available in many other programming languages. You have it in Dart, you have it in Python, you have it in Rust. So many other programming languages have this concept. And in some languages it's called either, but in in Swift, it is called result. So let's first go ahead and define our error. So we say enum, integer errors. It is an error, and then we say case, no positive integer before this value, okay? Enum error case, did I do something incorrectly in here? It doesn't look like it formatted it right, but this is fine, okay? Then we create our function, we say func, and we say get previous positive integer, and we say from int, all right? And in here, what we need to do, we are not going to say that this function throws, but instead we're going to say that this returns a result that is either an integer or an integer error, like in here, okay? So now all of a sudden, instead of this function just saying, I throw anything, you're saying it either gives you the result or it gives you an error of this specific type, which is a little bit cleaner, to be honest with you, because a throwing function doesn't necessarily specify, or it can't really specify the type of errors that it throws. So the call side to that function always has to have a catch-all block in order to understand, okay, what error is actually being thrown by this function. But by using a result, you specifically say which errors you're gonna throw. Not really throw, but which errors you're gonna carry with you, if any, all right? So let's guard that this integer is more than 0. Otherwise, we say return a result that is a failure, and its failure is indeed an integer error. You can see in here that is no positive integer before this value, and the value is this integer right here, okay? So we're guarding that the int is more than 0, basically, because otherwise we can't -1 it, all right? Then after this, we say, okay, in that case, we want to, in any other case where the integer is more than 0, then we have to return a successful result. Then we say return a result with success, and the value is integer -1. All right, so you see how this function is structured at the moment, okay? Then we go ahead and create another function, which internally calls this function. So we call it func perform get, and this is just to add another layer of complexity really to our code, so that we don't go ahead and directly call this function. I just want to show you how you can call this function within another function, okay? So we say perform a get for a value, and we say value is an int, and inside this function we're going to call the other one get previous positive integer from value. And then since this guy returns a result, and if you look at result, you can see just like optional, result is an enumeration, meaning that you can switch on it. So let's switch on this guy, and we say in case if we get a success, and we say previous value, all right, actually success previous value, maybe not previous value, previous positive, yeah, previous value. Then we say previous value is previous value. But in case we get an error, we say case failure, and we say error. Then you can say, okay, but this error, it is in itself an enum. It is an integer errors enum. We already know that. So since it's an enum, you can have another switch within your switch. The first switch is switching on this result. And since it gets the error, which is of type integer errors, which itself is an enum. Then you can have another switch in here. Then you say switch error. In the case of no positive integer, you put a let in here and you say this value. Then you say no positive integer before this value. All right. So now that we have this extra logic in here, we can go ahead and call our perform get function. So I'm just going to copy paste some code in here. You can see first we pass 0 to this function. And let me comment this line out. First we pass 0 and 0 then comes, so that 0 comes in here. It's then passed into this function. Then it comes in here and says make sure int is more than 0. Oops, it's not. Return the failure. And then it comes in here into failure, gets the error. We switch the error. Is it no positive integer before? Yes, it is indeed. Then you get this line printed to the console, no positive integer before 0, and that's correct, okay? Then we bring this code back. You can see now it will hit this block and it says previous value is 1. All right, because the previous value before 2 is indeed 1. So that's short and sweet about error handling in Swift. You can either use throwing functions and throwing constructors, for instance, and then do and catch. And you also looked at try with a question mark, which optionally tries a function, or try with an exclamation mark, which you try to always avoid actually, because it can crash your application. And then at the end, we looked at how result also works in Swift and how it goes hand in hand with error handling in Swift as well. Okay. Now that we're done with error handling in Swift, let's talk about collections. And collections is something we've talked about up to this point a good maybe 5 or 10 times, 5 to 10 times, I would say, but we haven't really gone into details about them. So I'm going to close this playground in here. I'm going to press Command N and say blank in here. And let's create a new playground, and we're going to call it collections. All right, and ensure that it's created in your main workspace. And then we say create. And just like normal, we say import foundation and run this playground also automatically. We get rid of our Explorer here, and then we can start talking about collections. So collections, as their name indicates, there are a collection of stuff. All right, so for instance, let numbers. And if you're, I mean, not if, but since you're already familiar with other programming languages, collections are also called arrays or dictionaries, or even JSON objects. For instance, if you're working with simple JavaScript, you can just say const something is equal to, and then you add your values in here, value blah. Okay, so this is a simple JSON JavaScript and is some sort of a collection. And in Swift, you also have different types of collections. One of them is an array. So you say let numbers is 1, 2, 3, 4, for instance. And then you can do different things with this collection. You can say, give me the first value, give me the last value, give me the count of objects in here. Or you can say numbers, map every element to its minus counterpart. So you can see in here, then let me just bring this over. So you can see we have 1, 2, 3, 4. Then the first element is 1, last element is 4. There are 4 elements total. And in here, we mapped every element inside this numbers array to its minus counterpart. Okay, so this is an operator in here. Now, if you have an array in Swift, you can also mutate it as long as it is a variable. So let's say var mutating numbers, and we say 0, 1, and 2. And then you can say mutating numbers, append the value of 3, and then mutating numbers, insert the value of -1 at the index of 0. Okay, so index of 0 is right here. Not that the 0 is actually, let's just say 4, 5, and 6 instead, okay? And then we append the value of 7, and we then insert the value of 3 at the index of 0, meaning that the array was 4, 5, 6, but at the end, it will be 3, 4, 5, 6, 7. You see what happened in here? The index of 0 is right here. And in the index of 1 is right here, index of 2 is right here, because indexes in arrays and any collection in pretty much every programming language that I know about, they start at the index of 0. They're called zero-based indexes, okay? So apart from doing appends and inserts, you can also insert a whole array inside an array. So you can say mutating numbers, insert, and then you can say insert the contents of, for instance, 1 and 2 at the index of 0. So let's see what happens in here. And then, right, it's not insert, it is actually insert contents of. So this API call is called insert contents of. And you can see the resulting array will be 1, 2, 3, 4, 5, 6, and 7 in here, okay? You can enumerate over the elements inside an array by just using a for statement for value in numbers. So then you can say a value and print it to the console. And now, Playgrounds have an interesting way of showing values over time. Since we're enumerating over these values and there are 4 of them, it can't print them all in the same line. So you have to click here, I believe, and it gives you like a little graph, and then you have to right click on it and you say value history. Then you get the values 1, 2, 3, 4. Otherwise it shows you a graph for some reason, okay? And let's somehow remove this. Okay, there we go. So that's how you would go through values inside an array, okay? You can also enumerate through items inside an array with pattern matching using the where clause. So if you want to, for instance, grab all the even numbers inside this array. So because you saw this printed 1, 2, 3, and 4, and 1 and 3 are not even numbers. But if you want to grab only the even numbers, you could say for value in numbers, where value, and basically the result of dividing the value by 2 should be equal to 0. Okay, so this is how you would do your pattern matching. And if you say value in here, we can do the same thing that we did earlier and say value history, and then you only get the values of 2 and 4 in here. Okay, so that's how you can have a where clause right after your for statement. Now you can also map objects inside an array, and mapping is also very important because it's one of the most useful functionalities of collections. Mapping means that you take the values inside that collection and you turn them into something completely different if you want to. Okay, so let's say numbers, you map them, you see, and it says, okay, I give you the number. So let's say value, and in here you can say I return anything. In this case, we've decided to return an integer, and we say value multiplied by 2. Now you can all of a sudden see that numbers are 2, 4, 6, and 8, whereas they were originally 1, 2, 3, and 4. So here you multiplied them by 2. However, inside map, you can return anything. You can say, I actually return a string, okay? And then you turn these into a string. You can string first multiply them by 2, but then turn them into a string. Now you can see they're strings. So map allows you to map it to anything. All right. And now that we're talking about mapping it to anything, you can guess that this map is indeed a generic function because it allows you to change the result value. And if you look at its signature, you can see it is indeed giving you the elements inside the array, but it allows you to return anything, and the result would be the array of that anything. Okay. So if I go and say let values, you can see values is an array of, not in this case, but in this case, values will be an array of string, okay, like this. So values is an array of string right now. And just a note about this, maps don't necessarily have to be this complicated. I mean, to me, this, and I actually can recommend this syntax more than I can recommend the next syntax I'm going to show you. And simply because the more information you give to the Swift compiler, the faster your code compiles in larger applications. But if you have very simple applications, you don't have to do this much syntax work in Swift. You could literally just say, okay, first of all, I don't want to tell you what return value I have. And Swift still is happy with that. You can also remove this in here because Swift already knows the value is an integer. Okay, and this works as well. And you can completely remove that, and instead of value, use $0, and that works as well. So your code could pretty much just look like this. But again, I mean, this does work, but it has very little information about what that code is actually doing internally. So a newbie software developer may be quite confused by it. And also, as I said, this is more information to the compiler, which allows it to compile your complicated codes in the future a little bit faster as well, okay? Apart from mapping arrays, you can also filter them, meaning that you want to grab specific values out of this array. You could say numbers, then you filter, and you say you get the value, and you return a boolean for all the objects that have to be included in the result of this filter function. So you say if the value is greater than or equal to 3, then it should be returned from the result, and you can see the result is 3 and 4. Okay,
So that's how filter works. You can also do compact mapping, and compact mapping is similar to map, but it returns an optional, and the values that are returned from this compact map, which are nil, will not be included in the result. So it's a compact map is a combination of map and filter. Okay, so let's have a look at that. We say numbers compact map, and we say we get the value as an integer, and we return a string. Okay, an optional string. Remember, it should be optional. Optionality indicates filtering. So if it is nil, it won't be included in the resulting array. Then we say if a value is divisible by 2, then return the string of that value. Otherwise, return nil. So let's break it down into separate lines so it's a little bit more readable. Okay, so you can now see the result is an array of strings that only includes 2 and 4, but it doesn't include 3 and 1, or 1 and 3 basically. Okay, so compact map, when you see it, just know that is a combination of map and filter at the same times. Now, arrays in Swift can also contain the value of nil. So let's say numbers 2, and it is an array of optional integers. So meaning that it can contain not just integers, but also nil. Then you can say 1, 2, and then nil, 4, and 5. So this is completely fine. All right. And then if you say numbers 2.count, you will actually see it is 5, because nil is one of the elements, one of the valid elements inside this array. And if you want to grab all the values inside this numbers array and that are not nil, then you would say let not nils is equal to numbers 2 filter. So you basically say, here's my integer, and I return a boolean for all the values that are not nil. Then you could say, let's say its name is value. Then we say value shouldn't be nil, like this. All right. And you can see the result of this is just 1, 2, 4, and 5. All right. However, this you will be like, okay, we've checked that the values are not nil, and we've placed them inside this array. So this array should now be an array of integers, but that's not correct, because if you look at this, is still an array of optional integers. So what happened in here is that though we checked for nil values, but we didn't tell this, so basically filter doesn't allow you to change the data type. All right, you can see it always returns the same array of the same element type. So if our elements is optional integer, the result of this function will indeed be optional integers as well. In order to grab the non-null or not nil values out of this array and also change the data type, you have to use compact map. All right, so so you could say in here, not nils is numbers 2, and we say compact map, and we say we take the integer, which is value, and we actually return an optional integer as well, and just return the same value. All right, if this value is nil, it won't be included in the result, and also it won't basically change the data type. So not nils is now not an array of optional integers. Okay, I know it's complicated and it's a lot of generic code, but it really requires that you work with these functions yourself for it to basically click. Now, arrays can also include instances of the same object multiple times. So if you say numbers 3 and we say 1, 2, 1, 2, you can see that numbers 3.count is indeed 4. So it contains 4 objects. It doesn't check whether they are unique or not. Okay. Arrays can also, they don't necessarily have to include homogeneous objects, so they can be heterogeneous, meaning that you can have integers and strings mixed up and blended up in the same array. So let's say let's stuff 1, and we say it is an array of, it has an integer of 1, then it has hello, then it has an integer of 2, and has a string of world. But this will give us an error, or it should, because it says it is not a homogeneous array. All right, and it says it's heterogeneous. So in order to fix this, you can see Swift is telling you to actually add as any to the end of this array. And a collection literal could only be, what is it saying? As an array of any. And I mean, this to me looks fine. But I'm not sure really what is it saying. Collection literal could only be inferred to any, add explicit type annotation. I believe we've already done that, so not really sure what it is complaining about. Let's just say stuff1 and see if Swift has understood what this code is actually doing. Expected separator. Did I miss a separator somewhere? Let's stuff1. To me, this looks fine, but not sure really what it is complaining about. Let me just bring it in here, and then we say hello. Let's put all of these in. Oh, because I've missed a comma in here, I can see. Okay, sorry about that. So I'd missed a comma in there. So now you can see our array looks fine. And if I say stuff1 count, it should include the count of 4 in here. Okay, there are 4 objects. So this is a trick to get your array to include heterogeneous objects as well. All right, so we can also go ahead and change the syntax for this. So if I copy this and paste it in here and changes the stuff2 and then stuff2 count. If you don't want to have this as in here, you can also tell Swift that this is in fact an array of any by doing this colon in here, just specifying the data type right there. Okay, so that's another way of achieving the same result. Now that we've talked enough about arrays, let's talk about sets. A set is a special object. It's a special collection that only contains unique values. All right, and the way it calculates uniqueness is based on hash values and equality. All right, and this is a little bit complicated. A lot of people think it's just hash value, but it is not. It's also equality, which is very important to understand with sets. So let's create a set. We say unique numbers, and then we say it is a set of the values 1, 2, 1, 2, and 3. All right, and then we say unique numbers count, and then unique numbers map them to their minus values. Let's just see what values we get in here. You see, after the creation of this set, the set only includes the values of 3, 1, and 2. So 2 things are quite interesting about this is that it removed the duplicates. So both 2's were not included, only 1 instance was included, and the same thing with the value of 1, only 1 instance was included. So that's one thing that's interesting about creation of this set, or and one of the properties that's important about sets, it only includes unique numbers. And the other one is that this array that we just passed to it, its ordering was completely changed within the set. So sets in Swift cannot guarantee ordering as you pass the ordering to it. So the ordering could just be mishmashed, and the set will order the items as it pleases. All right. So sets can also contain nils. So we can go ahead in here just like arrays. So let's say my numbers is a set of 1, 2, 3, and nil and 5. And then we say let not nil numbers. If we want to get the not nil numbers, then we say it is a set of my numbers. And then we compact map this guy, compact map, and we grab only the current value. You can see it here, compact mapping. Let's actually break it down into separate lines, so it is more readable, like this and like this. All right, so we're just taking the same values which are inside my numbers, returning them from compact map. Compact map, what it does is if the values are nil, it removes them from the result, and you can see the result of compact map inside a set. It is an array of the values, and that is the reason we're putting it inside another set, because we want the return value to be a set as well. All right, and then we say not nil numbers in here. You can see in here we have 5. Where is it? 2, 3, nil, 1, 5. But in there we have only 3, 2, 1, and 5. So nil was removed essentially by calling compact map on that set. Okay. Now you can also create heterogeneous sets, just like you can create heterogeneous arrays. So a set doesn't necessarily have to only have integers, for instance. So the trick to do that is to create a set of a protocol called AnyHashable. All right, so you say stuff3, for instance, and we say this is a set of AnyHashable, and you can look at the code for AnyHashable. Sorry, it's not a protocol, it's a structure. And we say it is equal to 1, 2, 3, and then bounded. All right, then we can say stuff3 count. You will see that includes 4 values. All right, so this is the trick to create heterogeneous sets as well. Now, if you want to extract specific items, like of specific types out of any of these sets or arrays, let's just focus on the sets right now. Actually, let's have a look at our stuff1. You can see our stuff1 is an array at the moment. that is an array of any. But if you want to grab specific objects out of this array, which are of specific types, for instance, only the strings or only the integers, you can use a keyword which is called as. So let's say let ints in stuff1, and again, remember stuff1 is this array. It has integers and strings, and you only want to grab the integers out of them. So then you could say ints in stuff1 is stuff1, and then you compact map. All right, remember compact map does map and filter at the same time. Then you get your value, which is any, and you want to optionally return an integer. Then you say value as int. So you compare the values type to an integer and optionally return it if it is integer. Okay. And then you can see in here that the result of this is only your integers. And you can do the same thing with strings. So you can say, okay, let's copy this. And then we say strings in stuff1, and then you get the value and you optionally return a string. And then you say, as long as the data type is a string, I return it. Okay, then you get the hello world printed in here. Okay, so if you are comfortable doing this with arrays, then you're probably also comfortable doing that with sets. And it is very similar. It's actually compact map on sets as well. So let's copy this code, ints in stuff1, and then we say ints in stuff3. And remember, stuff3 is a set. Then we go in here and we say stuff3, and we compact map, and the value is any hashable, and then we optionally return an int, and then we get the result printed to the screen, which is 231. You can see 1, 2, 3 van. So van was essentially removed from this set. But one thing to note about this is that, as I mentioned before, compact mapping on a set doesn't return a set. It actually returns an array. So if you go in here and call type of, which is an internal function in Swift, and say, give me the type of ints in stuff3, it will tell you that this hopefully is, did it crash? It will tell you it's an array. It's not a set anymore. Though stuff3 was a set. You can see in here is a set, but the result of compact mapping a set is an array. Okay, so just keep that in mind. Now that we talked about sets a little bit, and we talked about that they can contain that they only contain unique objects, then the question is, how does it calculate uniqueness? And the way it does it is using a protocol called Hashable. Now, Hashable, a lot of people think that only thing it does, it contains some sort of a hash value, is some sort of an integer value that uniquely identifies every object. But Hashable protocol in itself also includes equality. All right. So without actually me talking too much about that, let's have a look at an example. So let's just say we create a person struct in here, struct person. And then we say we have an ID. So every person has an identifier. We have a name of string, and then we have an age of integer as well. Okay. And then we want this person to be able to, instances of this person to be able to be included inside sets. Okay. So without making this person hashable, let me show you what will happen if it is not hashable and you try to create a set out of it. So let's say that we have a foo ID in here. And we say it is a UUID. Then we say let foo is a person with the ID of foo ID. Its name is foo and its age is 20. All right. Then we create a bar person in here, and we say bar is pretty much similar to foo, and we say bar, but we forget to change the ID, and bar is also using the foo ID. Its name is bar and its age is 30. All right. Now we want to go ahead and create a set of foo and bar. So let's say we have people, and we say it is a set of person, and it is equal to foo and bar. Now we should get an error ideally from Swift telling us that these objects are not hashable. You can see it says does not conform to protocol hashable. All right. So how do we do that? How do we ensure that they conform to hashable? So let's go ahead and say that they conform to hashable, and everything will just go fine. Nothing will happen in here. You won't get any errors. Okay. And if you go in here and say people that count, let's go in here. Okay. You will see, unfortunately, it is still 2. So what happened in here? We said that, well, we are making this person hashable, and it should ideally not be placed twice in this set because it is pretty much the same. But if you look, I mean, same data, but what happens in here is two things. When you create a structure and you just say it is hashable without having any custom logic in it, meaning that you didn't actually tell Swift how to calculate the uniqueness of this object. What Swift does is that it looks at all the properties of that object and says, okay, are all these properties unique themselves? Like, are they hashable? And if you look at UUID, is indeed hashable. If you look at string, it is hashable. Let's see, extension string hashable. Somewhere it should have been made hashable. I'm not sure if it is exactly. There we go, extension string hashable. And also if you look at the code for int, it should also be extension int hashable. There we go. So since all these three are hashable, then Swift says, okay, I'm going to calculate the hash value myself. Then it says, okay, you created a person. It has the ID. Let's just say its hash value is 1, let's say. Then it says, oh, the name is Foo. The hash value is, for instance, 10. I'm just making this up, okay? And the hash value for this guy, let's say, is 20. All right. Then it comes to bar and says, oh, it has the same ID as the other ones, which has a hash value of 1, but its name is bar, so its hash value is, let's just say, 30, and the age is also 30 with a hash value of 40, for instance. Okay, so it says, okay, then you put both of these inside a set, and I'm gonna calculate these hashes 20 plus 10 plus 1, for instance. Okay, this is not how hashes are actually calculated, but we're just gonna plus them together. So 20, 10, and 1 are gonna be 31, and then we have 40, 30, and 1, which is gonna be 71. So 31 and 71 are not the same, meaning that they're basically not the same object and should both be placed inside this set. Okay, so that's how hashing basically works within Swift. Okay. But what we may want to do is to tell Swift that, hey, we actually don't want people with the same ID to be recognized as different people. So what we want to tell Swift is that if two people have the same ID, then they're essentially the same person, okay? And in order to give Swift more information about how it should do our hashing, we should go ahead and basically implement the hash functionality somehow ourselves, or at least inject our own logic within it. So let's create a person2 object in here. So a person2 structure. So now that we've seen that example, let's say a struct person2, okay? And we're gonna let's actually grab this struct from here, but instead we're just gonna call it person2. So person2 in here, we said that it is hashable. Now, if you make an object hashable, you also have the ability to override a function in here, and not really override, but also implement actually a function called hash_into. All right. And this function comes in here because we've conformed to the hashable protocol. All right. Then in here, what you can do is to say hasher, and then you call the combine function on it, and then you basically hash the fields that you want to be taken into account while Swift does its hashing. So what this really did in here is that it jumped over hashing name and age, and instead only hashed ID within the hashing mechanism of Swift. All right. So now that you've done that, you also need to tell Swift whether two objects are equitable, because you've just implemented your own hashing functionality. And when you say something is hashable, by default, it's also equitable. And what happens in here is that right now you set that take ID only into hashing mechanism. But in terms of equation, because hashing is also doing equality, Swift, if you don't intervene, Swift goes and it says, okay, the hash values are the same, but these two objects are not really equal, because by default, Swift is going to also equate all three properties. So in here, what we're going to do is to say static func equality. So we're going to override equality as well. On the left-hand side, we say self, and the right-hand side is self. Then we say Boolean, and we say as long as the left-hand side's ID is equal to the right hand side's ID, then these two objects are equal. So not only have we changed the way hashing works, but we also need to change the way equality works. Otherwise, they won't really come to an agreement with each other. Okay. Now that we have that, let's go ahead and create a Baz ID in here, and we say it's a UUID. All right. And then we say we create a Baz person in here, which is person2. Remember, create an object of type person2, not person. Then we say Baz ID. Its name is Baz. And then we say it has, or he has the age of 20, or she has the age of 20. Then we create a Cox value in here, and we say QUX, and we say person2, and then we say Baz ID, and the name is Cox, and the age is 30. All right, so you can see now the ID is the same, but all the other values are different. However, the way we've done our hashing and equality is that we only take into account the ID. So even if their names are different, but they're using the same ID, then we consider them to be the same person. And that's why you can go in here, if Baz equal to Cox, they are equal. So this basically is invoking our equality, and you can see it comes in here. Okay. But that's not the point. That's not what we're trying to do in here. We actually want to add them to a set. So let's say let people 2, and we create a set of Baz and Cox in here. And if you look at the values inside people 2, it should just be one value, people2.count. All right, simply because our hashing intervened in here, and both these objects were considered to be the same object. All right, and if you take the first item out of this, you can get a person2, and then you can say the first object's name, give us the name. All right, and you can see it is Baz. All right, so Cox was not inserted into our set simply because Baz was already there, and Cox was considered to be the same object, therefore it was not inserted into the set. All right, so that's how you can go ahead and implement your own hashing value or hash value and equality. All right, that's enough about sets. Let's talk now about dictionaries. Now, dictionaries, they're also called JSON objects in many other programming languages, such as not really JSON objects. Yeah, well, kind of JSON objects. Yeah, they're keys and values basically. Okay, and you define them using a square bracket in Swift. So you say user info, and you can create your dictionary, and then you say keys are in this case string, for instance, with a column, and you separate the keys from the values using a column, and you can say the key is name, the value is foo. This key is age, and oops, if we can spell age, and its value is 20. Then you can say I have an address field in here whose value is indeed another dictionary, and you can say the address has a line 1 and is address line 1. Then we have a postcode, for instance. Its key is postcode, and its value is 1, 2, 3, 4, 5, let's say. All right, and this is completely valid Swift object if I haven't messed anything up. Let's see, foo, age, address. All right, and we also have to tell Swift that you can see it is heterogeneous values, because some values are strings and some values are integers. Then we have to tell Swift that it's a dictionary with keys equal to string and values of any type. All right, without that, it won't work. However, if we didn't have this age in here and we didn't have this address in here, we could have just gone away by defining our dictionary like this, and Swift would have understood the data type to be of keys, strings, and values of strings as well. But since we have keys of string and value of integer and a key of string and a value of a dictionary, then we have to tell Swift that keys are string and values could be anything basically. Now, you can grab values out of your dictionaries using subscripting. So you say user info, grab the name, and you can see it will give you the value of foo in here. You can say give me the age, user info, give me the age. So you're basically giving it the keys and you're extracting the values for those keys. Now you can say user info and then give me the address. Let's go in here, address. All right. And since this is an address dictionary coming back from here, you may be hoping that, okay, since this is an entire dictionary, maybe I can type a key in here as well and get the postcode. All right, and if you do this, then you get an error because you've told Swift that the values that come out of this dictionary are of type any, meaning that Swift just believes that this is any. And now you're trying to tell Swift that this is not any and is in fact a dictionary, and it should go into that dictionary and extract a value with a specific key, and Swift just rejects that. Okay, there's a dangerous way of doing that, forcing Swift to believe that this in itself is a dictionary, and that is using the as syntax. But please don't ever do this in production applications. There are better ways of doing this. So I just want to show you how it works. You can say get the address,
and force cast it to a dictionary of type string and string. You can see it because this has keys of string and values of type string as well. Okay, so after doing that, then you can go ahead and say, give me the postcode on it. All right, and this should work, but in production applications, really is not a good idea to do this. So let's see what happened. I accidentally found nil1 unwrapping optional value, and I think it's because I misspelled address basically. So it works, but you should never do this because this will crash your application should this key either not exist or that its value shouldn't be of type string or string. Your application will crash. So please don't do this. I'm just showing you so that you know this syntax also exists, okay? If you want to extract the keys and values out of a dictionary, you can say userinfo.keys, and also you can say userinfo.values, and this will give you the keys only. You can see in here. Let's go in here. The keys are age, address, and name, and the values are 20. Let's go here, 20. Foo, which is, let's see where it is. It is 20, foo, and then this dictionary. So you grab basically only the keys or only the values out of your dictionary using that syntax. However, it is more common that instead of just saying keys and values, you want to enumerate over the keys and values and their associated values. Because you can see in here, we're only saying keys and only values, but what if you want to grab every key and its associated value? The syntax for it is for key and value in user info. Then you can print them out, key and value, like this, okay? Let's see if the playground can help us extract these values. So the key says name, value, history. You can see age, address, and name are the keys. And the values, we can also perhaps get their history. Let's see, value. The playground isn't so smart in being able to print the values. So let's instead print the values and see if we can get them in the console. Like this. So here are the values basically, okay? And you can also print the keys as well. So let's say we print the keys and we print the values. So the key of address has this value, the key of name has this foo value, and the key of age has the value of 20. All right, so we can do that as well. Let's just revert them back to how they were. Okay, now you can also have a where clause in your enumeration over keys and values. So let's say for key and value in user info where the value is an integer, okay? And then you can say key and value. So you see the only value that was an integer had the key of age, and the value was of course the value of 20. All right, then you can also have multiple where clauses, so you're not limited to only one where clause. So you can say for key and value in user info where the value is an int and key that count. So the key is a string and we're saying it should contain only more than two characters. Then we say give us the key and the value. All right, so the count is pretty much the length of the key. And then you can see that we got the same result because age is 3 letters long and our condition said it should be more than 2. But if in here we said more than 3, then this will never be called. So we won't get any results in here. Okay, so I think that's actually quite enough right now about collections. We talked about arrays, we talked about sets, and we talked about also dictionaries and some new formats and pattern matchings that you can do with these collections. They're very, very useful. And I think you need to really get quite handy with these objects yourselves in order to get a good grasp of how they work. I can just sit here and explain these for ages, but without practice, probably it will never really click. So my advice is to go ahead and create some sets, arrays, and dictionaries yourselves to get a good grasp of how they work. Now that we talked about collections, it is good time that we start talking about equality and hashing as well. I mean, we did touch upon this topic a little bit right now, but we haven't fully covered them. Equality and hashing, they're like their own whole world of understanding how they truly work. And basically understanding them is the key to understanding how sets, for instance, work, and how equation generally in Swift works. So I think it's very important that we dedicate a whole
section just to equality and hashing. So that's what we're going to do right now. So I'll see you there. Let's then go ahead and create a separate playground for this. So we say blank and foreground, playground, and we say equality and hashing like this, and ensure that you're creating it in the root folder like this. And then we just say create, and we import foundation, and we can get rid of the Explorer to the left hand side. Now, equality in Swift is provided using a protocol called equatable. Any object that conforms to the equatable protocol has to have a function, a static function, which is an equality function like this, which is pretty much an operator. And this function has to have two arguments, one at left-hand side and right-hand side, both of the same exact type as the current structure or class implementing it. Now, if you go ahead and create a person structure in here and say that this person is conforming to the equatable protocol, and you say let ID is a string, and then you say let name is a string, then we create two instances of this. We say let foo1 is a person with the ID of 1. All right, and then we say name here is foo. Then we create foo2 right here, and we say the name is actually bar. Then if you say if foo1 is equal to foo2, then we say they are equal with an exclamation mark in here, because they shouldn't be. They are not equal otherwise. Okay, so what happens in here is that by ensuring that this person is equatable, right, let's also make sure that this is running automatically. By conforming the struct person to equatable, Swift goes in through all the properties of the structure and ensures that they are indeed themselves equatable. String by default conforms to the equatable protocol, and so does this one. So then Swift says, okay, then I understand that it should be equatable. However, if you go in here and say struct dog and don't make it equatable, and in here you say this person should also have a dog, all of a sudden Swift will throw an error in here saying that, oh, I can't give you equatable by default because dog, which is one of the properties of this person structure, does not conform to equatable. If you want to get rid of this, just ensure that this dog is also equatable, which then gets rid of the problem in here. But the only problem we have in here is that we need to pass a dog instance in here. But we're going to remove all this dog reference in here. Just wanted to show you how default implementation of equatable basically works. It looks at all the properties and then makes sure that they're equatable, and then goes through all of them one by one, compares the properties between these two objects that we're comparing. Okay. Now, you can also override equality, and you can basically say, let's say that you in your person structure, you want to say any two persons that have the same identifier should be considered equal. So then you can say extension person, and you can see at the moment, these two objects right now, before our extension, they're marked as not equal. All right, simply because their names are not equal. But if you go to extension person and then define this static func equal like this, and you say left hand side is self like this, and right hand side is self as well, and this function should return a boolean indicating whether the two objects are equal or not, then we say if the left hand side's ID is equal to right hand side's ID, then these two should be considered equal. Now all of a sudden you see that this will be flipped to they are equal. Previously, before this extension, this branch of code was being executed because by default they were not equal since they had different names. However, with our extension in place, since we're only comparing the IDs, then they're marked as equal. So if you comment your code out, you can see all of a sudden that this branch will stop being executed, and instead this branch will get executed. All right. So that's how you can create your own equality on custom objects. So we can comment this guy out. Apart from structures, you can also implement custom equality on enumerations. Let's say that we have an enum in here we call animal type, and we have a case for a dog, and we ask for the breed, and also we have a cat, and we ask for the breed. Okay, now let's say that you want to compare these with each other. If you go ahead and say let dog and say is an animal with a type of dog, with its breed is a Labradoodle, and then you say let Whiskers is an animal type, another dog basically exactly of the same type, then if you go ahead and say if dog equal to Whiskers, let's just change this to maybe dog 2, dog1 and dog2, and then we say if dog1 equal to dog2, like this, you can see that you get an error from Swift because by default animal type is not equatable. You can go ahead in here and say, okay, well, I'll make it equatable. Does this work? You'll be surprised to see that actually by default what Swift does is it looks at these values and says, let's put some values in here and say they are equal, like this. Otherwise we say else they are not equal. All right, so since dog1 and dog2 we actually are giving them the same values in here, then Swift by default says, oh, they're equal. But if you change the value inside this breed, for instance, then Swift says they're not equal. So Swift does the same thing that it does with structures as it does with enums. It goes through all the properties of those enum cases and then make sure that they're equatable. If they are, it will just call the equation function on those parameters as well and compares them with each other. If all those they're equal to each other and the case is equal to the other case as well, then the enum cases are marked as equal. However, you can go ahead and change this implementation. So you can say extension animal type, and let's just remove the equatable from here, and we say animal type becomes equatable in this extension. All right. And then we go ahead and implement an extension, the static func, left hand side is self and right hand side is self as well. And then in here we say bool. All right. So now what we want to do in here is to compare the breeds with each other. So we say we switch the left hand side and the right hand side. Then we say in case we have a dog with the left hand side breed and another dog with the right hand side breed, then they're considered equal as long as the left-hand side breed is equal to right-hand side breed. We do the same thing for cats. So we say if we get a cat in here and a cat in here, then they're equal to each other as long as their breeds are equal. And since this pattern matching is the exact same thing between dog and cat, you can see they're getting left-hand side breed, right-hand side breed, and the same thing in here. You can remove this code in here and just put a comma and remove this case as well. All right, so they're basically doing the same thing. And then you can go ahead and say anything else, they're considered not equal to each other. Okay, so as long as it's a dog and their breeds are the same, then it's considered to be the same. And if it's a cat and a cat, then they're considered to be the same as well. So let's see what we got. We got this. Oh, we have to return this, of course. We can't just write that statement in the playground. Good. Then we can go ahead and basically, we've now created an animal type. Let's go ahead and create an animal now. So we say struct, and we say animal in here, animal, and we said let name is a string, and then we say let type is an animal type. Okay, and since both string and animal type by this point are equatable, you can make this animal also conform to equatable. All right. However, what we want to do is to say, okay, the animal equality has to only look at the animal type. We don't want it to look at the animal name. That is the default behavior that Swift looks at all the properties. But in this case, we just want to look at the animal type. All right. So let's say that then we override the static func equal, and we say left hand side is self and right hand side is self as well. And we return a Boolean. Okay. And we only look at the types. So we say left hand side type should be equal to right hand side type. Otherwise, they're not equal. Okay. Then we can go ahead and say let cat1 is an animal and its name is Whiskers, like this. All right. And its animal type is actually a cat. Then we say it is a cat of type street cat, of the breed street cat. Okay. Let's put that in here. And this is also a shorthand of writing the animal type. So instead of saying animal type in here, you can just say .cat. So instead of doing this, you can just do the shorthand and Swift will understand the code anyways. Let's copy this code. And then we say cat number 2 and its name is Whoosh. Okay, just like that. And it's also a street cat. So looking at our equality functionality in here, we only look at types on animal in order to determine if they're equal to each other or not. So then we should be able to go and say if cat1 is equal to cat2, they are equal because of their breed, actually type because of their type, else they are not equal. All right, and you can see that this branch of the code is being executed simply because our equality, custom equality on animal only compares the animal types. And since they have the exact same type of cat and street cat, then our code works. And you can actually go and remove this implementation on animal type, because this pretty much is the same thing that Swift provides, equatable, and you can see the code will be executed just like before. So no difference really. So it's up to you if you want to do custom implementation of equatable, or you want to let Swift deduce this on its own. If Swift can already deduce this on its own, which it can, you shouldn't really go and write an exact same implementation. So this is pretty much just redundant. But if your custom implementation of equatable adds some functionality to how Swift does it by default, then please go ahead and add your own equatable to your custom types. Okay, so we can now, we've had a look at equatable. Let's look at hashable. We've already talked about this a little bit before, but let's just talk a little bit more in details about it. Just like equatable, hashable also looks at all properties of a struct or class to make that struct or class hashable. So if you say struct house and we make it hashable, then we say let number is int, and we say let number of bedrooms is an int. Then we say let house1 is house with the number of 1, 2, 3, and number of bedrooms is, let's say, 2. All right. And then we say house1, and you can see now you have a property in here called hash value, and that is coming from the hashable protocol in here. Then we go ahead and create another house. We call it house number 2 in here. Okay, house 2. And its number is 1, 2, 3, but its number of bedrooms is 3. And then we print out its hash value in here as well. Now you can see these hash values are different. Simply means that they basically, if you create a set with house 1 and house 2, they can occupy their own space and not overwrite each other. However, if you go in here and say number of bedrooms is 2, then you should ideally in here see the exact same hash value, meaning that you cannot put both houses inside the same set and expect them both to basically appear in the set. One is going to overwrite the other one. Okay, so if we go ahead and create a set in here, we say let houses is a set of house 1 and house 2, and please note that I changed this back, so it's now number of bedrooms 2 and this one is 3. Then if we say houses.count, then you can see we get 2 in here because none is overwriting the other one. Let's see if the playground is going to be able to update soon, hopefully. Even if it doesn't show the count, we can still see in here that we have one house in here and another one here, and now the count is also being displayed right there. Okay, really good. You can overwrite the how hashing of course works. We've already had a look at this when we talked about collections, but let's have a look at another example. So we say a struct numbered house, okay, and we say it is hashable like this, and we say let number is int, and then we say let number of bedrooms is an int, and this is pretty much the copy of the house structure, but we had to give it another name because you can't have two structures with the same name in the same code scope in Swift. Okay, then in here we're going to go and overwrite this hashing mechanism. So we say hash into, and we say we only want to combine the number into the hasher. So we say combine the number, and this simply means that as long as two houses have the same number, then they're the same house pretty much when it comes to their hash values. Okay, however, this doesn't mean that they're equal. You have to overwrite equality as well. So say static func equal, and we say on the left hand side we get self, and the right hand side we get self as well. Then we say this returns a boolean, and then we say as long as the numbers, so we say left hand side number should be equal to right hand side number, and then both houses are considered to be equal to each other in that case. Okay, so let's create let house 3, and please make sure you create a numbered house in here, not a house. Its house number we say 1, 2, 3, and number of bedrooms is 2. Okay, so as a house number 1, 2, 3, then we create another house. We call it house 4 in here. Okay, like that. And then we say it is a numbered house at the exact same number as this house. However, it has 3 bedrooms. Okay, then we create a set of these. We say houses at 3 and 4. It is a set of house 3 and house 4. And then if you look at houses 3 and 4 count, you can see there's only one object inside this set, simply because house 3 and 4, they can only consume the same space in our sets, and simply because their hash value is the same. You can see in here. Let's see if Playground is going to be able to update our codes, hopefully soon. If I close this one, maybe it's just gone crazy a little bit. Let's see automatically run. hopefully it can run the code. So you can see there's only one value in here. And if you say houses 3 and 4, get the first item, then it gives us a numbered house, and then we can say get its house number of bedrooms, and it says the number of bedrooms is 2. And the reason behind this is that house 4 could not be placed in the set simply because there was a house already in the set with the same hash value. And you can also look at the house 3 hash value and house 4 hash values, and they should pretty much be the same, simply because the hashing algorithm is only taking the house number into account. So you can say house 3 number dot hash value, and it should pretty much be unique as well. And you can see they're exactly the same thing, okay? And house 4 dot number hash value, they're the same as the entire hash value of the house, okay? So that was another example. Now, enums are by default hashable even without raw values. So I'll show you in here. We say enum car part like this, and we say case roof, case tire, and case trunk. Then in here we say let unique parts is a set of car part, okay, and it's equal to a set that contains roof, it contains tire, it contains another roof, and then a trunk. So since this is a set of car parts and it doesn't have any raw values, like we're not doing like this, so they don't have raw values. If you in here say unique part, oh, actually we can see the value already here. You can see it only contains trunk, roof, and tire. So it doesn't contain 2 roofs. That's what I'm trying to get to. So if you create a simple enum in Swift without any raw values or any associated values, it's by default hashable and equatable. All right, that is the whole point. Now, if you have an enum with associated values, then you can basically go ahead and change the hashing mechanism yourself. So let's say that we have an enum in here. We call it house type, and it has a big house, and we say its associated value is a numbered house, and we say case small house, it is a numbered house, like this. And then you can go ahead in here and say this is hashable. All right. So as you do that, Swift looks at the properties that are inside this enum, and it understands that, oh, this big house is of course hashable because it's an enum case. However, it has an associated value. Then it looks at the associated value and says, is this value hashable? Then it goes to numbered house and it says, yep, it is hashable. Then it implements hashable by default for you on this house type. Okay, so then you can go ahead and basically add these into some sort of a set. So let's go ahead and we say we create 2 big houses. We say big house number 1 is a house type, big house, like this, and it has a numbered house inside it, like this. All right, and this numbered house has a few properties. It has a number, and we say number 1, and it is number of bedrooms is 1 as well. So we have a big house at number 1 in that street, for instance, and it has 1 bedroom for some reason, a big house with 1 bedroom only. Then we say a big house number 2 in here. Okay, let's get rid of this bottom bar. Then we say it is also a big house at number 1, and total number of bedrooms is 1 on that one as well. Then we create a small house. So we say small house 1. Like this, small house 1. It is a small house, and we say it is at number 1 as well, and its number of bedrooms is 1. All right, so now we have 3 houses with the same number, and 2 of them are actually the same house type as well. So what's going to happen if we go and put these inside a set? So we say all houses is a set of house type, and is equal to a set with a big house 1, big house 2, and small house 1. All right. So if you say all houses that count in here, then let's see if the playground can resolve this. You can see there's only 2 objects in here. The reason is that big house 1 and big house 2 are considered to have the same hash value, simply because that their numbered houses have the same hash value and their cases have the same hash value. However, small house 1 is of type small house, not big house, though its numbered house has the same hash value as the other numbered houses. However, the enum case itself also has a hash value. Therefore, in here, you can see if I say all houses first and all houses actually, let's see if we can get the values inside the sets like this. You can see we have a, let's see. Oh, you can see the first one is a big house at number 1. And if we say all houses last, let's see if you can get the first. Does it have a last item? No, it doesn't. We can get the first, unfortunately. And let's just say for value in all houses. And then we type the value out in here. Let's maybe even print the value like this. So you will see then the first element inside all houses is a numbered house, is a small house with that numbered house. And the second one is a big house, meaning that the 2 big houses couldn't actually occupy 2 separate spaces in the set simply because their hash values are the same. Okay, so I think that's actually enough right now about equality and hashing. We've talked quite a lot about them right now, and I think you get basically the idea. So there's 2 different things you have to implement or think about when it comes to equality hashing. One is the hash value, which determines whether 2 objects should consume the same space inside a set, but also you have to implement equality, which determines whether 2 objects are actually equal to each other. Okay, and also you may sometimes just need objects to be equitable, not hashable, in which case you can just implement equitable protocol or conform to the equitable protocol. As long as all the properties inside your structure or class are equitable, then you don't have to implement a custom equality static function. However, you can always go ahead and change the default implementation of both hashable and equitable as well. All right, now we're done with equality and hashing, so let's start talking about custom operators. I'm going to close this playground in here, so let's create a new one, a blank playground. Oops, like this, and then we call this one custom operators. All right, and we create the playground. Then we say import foundation like that, and then we can get rid of the explorer to the left hand side like this, and we can run our playground automatically. Now we've talked about operators to this point quite a bit actually, but we haven't talked about creating so many custom operators, and that's what we're going to do in this section of the code. So let's say that you have a first name, which is a string, optional string, and you say it is actually equal to foo, though it is set as being an optional string. And then you create a last name in here, and then you say bar. Now, if you want to get the full name and you say it should be equal to first name plus last name, you'll see that you get an error from Swift saying that this operator, it is not defined between. You can see there is no operator that exists that matches this particular signature, left hand side optional string and right hand side optional string. If these were not optional strings, then you would have this operator. You can see then the error goes away. Let's see if we can get the definition actually for this one, plus operator. I don't think we can, unfortunately. Let's see, static func plus. Here we go. There is that function signature. All right. However, the Swift Foundation framework hasn't defined the same operator for optional strings. So we can actually go ahead and do that ourselves. So let's say we have a func plus, and its left-hand side is an optional string, and its right-hand side is an optional string as well, and it returns an optional string. Okay, then we go inside the function implementation and we switch the left hand side and the right hand side. If they are both none, meaning that they're both null, then we return nil, or actually not null, but nil. Swift is one language that has chosen to use nil instead of null. Then we say, okay, if then we get the left hand side, so if we say case let, we have some value on the left hand side, but no values to the right hand side, then we return the value to the left hand side. So if you only have the first name but not the last name, then we return the first name as the full name. We do the opposite of this for last name as well. So if the first name is nil but the right hand side has the value, meaning that there is a family name, then we say return that value. All right, and we can join these two together like this because they have the same pattern. Okay, and then we say if both of them have a value, so we say some left hand side and some, if I can spell, some right hand side, then we say return the left hand side plus the right hand side. Okay, as soon as you're done writing this function, you can see all of a sudden the errors go away and all of a sudden full name is indeed equal to foo bar. All right, so We can also add a space in here perhaps, or add a space before bar, so it becomes foo plus bar right here. Okay, so that's how you can create a simple custom operator in Swift. Okay, and I think we've actually looked at something similar to this before, maybe even something more complicated. All right, now we haven't yet created our own unary prefix operator. This one was a binary infix operator because it works with two or binary things, two things, therefore binary. So this is a binary infix. It is binary because it works with two operators, with two parameters, and is an infix operator because it sits in between two values. Okay. However, we haven't looked at unary prefix operators. So let's create a unary prefix operator. Let's have a look at an example. Let's say that we have a lowercase name in here, which is equal to foo bar, and we want to turn it into uppercase name by saying lowercase name, uppercase, like this. And this operator doesn't exist at the moment. So you can see it is, we want to say unary prefix. It is unary because it only works with one argument to its left hand side, and that's why it is called prefix, because it basically works with some, actually no, that is a suffix. I would say that we need to move this here. Okay, so this is a unary prefix because it uppercases whatever comes to its right hand side. So prefix because it is previous to the argument to its right hand side. Okay, so what we can do then is to go ahead and implement this operator. But before doing that, since it is not an infix operator, you actually have to tell Swift that it is a prefix operator. So you do that by saying prefix operator, like this. So you first tell Swift that this is a prefix operator. Then you go ahead and define a function for it. So you say prefix func, like this. Oopsie daisy. All right. And then we work with a value of type string, and we return a value of type string. Then we take the value and we say uppercased. Oopsie daisy, uppercased, like that. Now all of a sudden you can see that this error will go away and our foobar value will turn into foobar as uppercase. Okay, so that is how you do a prefix operator in Swift. You have to first define it as a prefix operator, then you create the function for it. Similar to this, we can also create unary postfix operators. So let's say that we have, for instance, a name here, which is foobar, and we want to turn it into star 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 foobar star star star, like that. Okay, so whatever string we give our operator, we want it to prefix it with 3 stars and a space, and then a space and 3 stars after it. Okay, so we say let with stars is equal to lowercase name, and then make sure you star it out. So we want a unary postfix operator. It is unary because it works only with one object, so it's left hand side, and therefore it's called postfix because it comes after the element that it works with. So let's define it. We say postfix operator star, and then we say postfix func star. It takes a value of type string and it returns a string as well. And what it does is that it just says star 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 space value star star star. Okay, and then you can see the value printed here will then be star 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 foobar space star star star. Okay, so you can also define your own custom binary infix operators on completely unrelated types. So what we've looked at so far is that every time we worked with a binary infix operators, both left hand side and right hand side were of the same type. However, what happens if you have, for instance, a struct in here? Let's say we have a struct of person, and we say let name is a string, and then you have a struct family, and then you say let members is an array of persons. Okay, then you go ahead and you say that you, for instance, have a mom. Let mom is person with the name of mom. Then we create a dad in here, dad. We say dad, and then we say son. Son is son, like that. Then we create daughters. So we say daughter 1, and it is daughter 1 and daughter 2. All right. Now what we want to do in here is to say we want to create a family. We say family like this is mom plus dad. So mom and dad create a family together. However, this operator at the moment is not defined. Swift doesn't understand what plus between two persons means. So we can go ahead and actually define that. So we say we have a function in here. We say func plus on the left hand side, we take a person, you see person, and right hand side another person. So we say a left hand side person, and we say right hand side person. I completely understand that we said left hand side and right hand side are probably going to be different types, and we've so far created binary infix operators with the same types for both parameters, and we're going to do something different now. So you're probably asking yourself, so why aren't we doing something different? But before we do that different thing that we're going to do, we have to first implement this function. You'll see soon. Okay, so we first say if you add two persons together, we create a family. All right, then in here we say we create a family with members equal to this. Let's create these in separate lines like that. The members are at the left hand side and the right hand side. Okay, now all of a sudden you can see this error will go away, and then you get a family in here. Okay, so that's one thing. Now what happens if you then go ahead and say for instance family with son is equal to family plus son? Does this work? No, it won't, because the left hand side of this operator is a family and the right hand side is a person. And what we've defined is plus between two persons, not a family and a person. So what we're going to do is to go ahead and say func plus. On the left hand side, we're going to take in a family. All right, so we're going to say on the left hand side we have family, and the right hand side we have a person, and this returns also a new family. Then we go ahead and we say we take the current family's family members, then we append to it the current person to the right hand side. Then we create a new family and return it with the given members like this. All right, and then you can then see that this error will also go away. So you can say family.members.count, and then in here you say family with son members.count, which should be one more than this family. You can see it's 3. Okay, now what if you want to say family with daughters? So let's say family with daughters, and then you say, okay, take the family with the son and then add a whole array of daughters to this. So you say daughter 1 and daughter 2, or sorry, not an array of daughters, but an array of person. You'll get an error now because we still don't have an operator that can work on an object on the left hand side of type family and an object on the right hand side of type an array of person. But we can go ahead and define that. Okay, so we can say func plus. On the left hand side we take a family, and the right hand side we take an array of persons, and this guy returns a family. All right, so the way to do it is to say var members, again members equal to left hand side members, then we say members append contents of the right hand side. Okay, and then we return a new family with the new members like this. All right, so now you can see this error will also go away, and if you say family with daughters dot members dot count, then you should get the value of 5 printed to the console in here. Okay, so you can see how easy it is to rationalize about how operators should work in Swift. They're just simple functions, except for unary infix and unary postfix, which you have to also create these operator tags kind of or declarations. So this is the implementation of the operator, and this is the declaration of the operator. Okay, so I think that is actually quite enough right now about custom operators. In the next section, we're going to talk about some of the new features inside Swift for basically concurrency and asynchronous Swift. And that is going to be the last section for this course. So without further ado, let's just get started with it. I'm going to close this tab in here, and then I'm going to create a new playground. And then let's say playground, and we call it async Swift. All right. And we just say we want to import foundation. And here is one of the exceptions where we have to import 3 things. We say import also playground support, and then we import concurrency like this. And we're doing this playground support here simply because asynchronous code requires that our playground is active all the time, and it doesn't just start from the beginning and ends when it encounters the end of the file. We just need the playground to stay alive simply because concurrent code and and asynchronous code requires that kind of behavior, because if you make an API call that takes 3 seconds to finish, maybe before that API call is done, your playground has already reached its end and it just terminates, and you don't want that. So let's go and say playground playground page dot current page, and then we say needs indefinite execution equal to true. So if you're running your code on a Macintosh in Xcode, then you have to do this. But if you're on Windows or Linux and you're in Visual Studio Code and just running your code using simple Swift, then you shouldn't really do this. You should perhaps just create a simple project that can have a main loop, and then you can then execute your code inside that main loop that never ends. Okay. However, if you're in a playground, then you will need to do this on Mac OS. All right. Now, let's say that we want to create a simple asynchronous function in Swift. If you're already familiar with Dart, for instance, for Flutter, or Python or Rust, you probably have already used Tokio perhaps in Rust, or in Dart you also have futures and stream controllers. You're probably already familiar with asynchronous code. But if you're not, I'll just quickly brief you on what it means. It means if you have an asynchronous function, it will not immediately return its result. It can take any number of seconds or milliseconds to complete its work and return some value. And perhaps it won't even return a value. Some asynchronous functions don't return a value, okay? So let's go ahead and create a simple dummy function in here, which we call calculate full name. So we say func calculate full name. All right, then we say we have a first name is string, and then we have a last name, which is a string. Then we say it is an async function, which returns a string. Okay, so by creating this asynchronous function in here, you'll have the ability to basically delay the return of your results. So you can in here just say return hello. You could definitely do that, but that's not the point of async functions. This is a synchronous function, not an asynchronous function. A synchronous function returns its value immediately. An asynchronous function might take some time before it returns its value. So let's go ahead and say we try to await on a task by sleeping for the duration of 1 second. So this is how you would create a delay, a fake delay in your function. All right. And we're using the try with question mark syntax in here because we're not throwing. Okay. If this function throws, then we didn't have to do that. However, we're saying that our function is an async function that doesn't throw. Let's also mark our playground as automatically running. So we say try and we say await, and let's say cannot convert return expression. Okay. And in here, then we can say return after waiting 1 second, return the first name with a space and the last name as the result of this function. All right. That error is now going to go away. Now inside your playground, if you want to call this asynchronous function, you have to create a task, and then you can say let result 1 is equal to await on the result of calculating the full name. The full name comes from the values of foo and bar in here. Okay. And you can see the result is actually foo bar. All right. It waited before it calculated the value for us. Then we can also go ahead. I mean, you can see in here we have let result equal to await, but there is another syntax word in Swift which is called async let, and you can say async let result 2 is calculate. So you can see how async is before the let, and then we say take foo bar again as the values. And in here, if you wanna wait for the result of this, you have to await on it. So you say await result 2. Now async let is a little bit more special because it creates a child task as part of this task. You can read about it in Swift Evolution on GitHub, and so I won't go too much into it, but it is kind of similar to this guy, but it has a little bit difference in like how you await on it, because some developers think maybe that, oh, this by default awaits on this, but it doesn't. Okay, you have to await on the result yourself manually. Okay, so that's how you can create a simple task, an asynchronous task, and then do some async and await code inside it in Swift. Now we can go ahead and put together maybe an example that talks about async and async let and task all together, just to make it stick a little bit more. Okay, so let's say we create a cloth enum in here, and we say we have case socks, we have shirt and trousers. All right, then let's create some asynchronous functions in here. So we say the first function that we have is called buy socks. All right, and it is an async function that throws, and we say it returns a cloth. And what it does is it says try await on a task by sleeping for a duration of 1 second. And the reason this function throws is that we're not doing try like this. If we did try with a question mark, we didn't have to throw, okay? But we're doing just normal try, therefore the function has to throw or it has to be inside a do. But what we're indicating to the outside world by writing this function is saying that this function is an asynchronous function that can internally actually throw an error. So be careful while consuming its value. All right. Then we return a cloth of type socks. So after 1 second, we produce an item of clothing. After doing this one, we can go ahead and create another function, which is called buy shirt, like this, and it produces an item of clothing, and in here we just say shirt. All right, and we can create another one that produces an item of trousers, so we say trousers, and it says dot trousers. All right, so they're very similar to each other, they just return a different result of them. Now you want to create a structure in here that is an ensemble. An ensemble is a, you can say it is a collection of clothes items, and you can say struct ensemble, all right? And then we say this guy has clothes in it, and we say it is an array of clothes, and it has a total price of type double. All right, doesn't really matter what the currency for the price is. We also want this ensemble to be printable to the console in a very nice format. So we conform it to custom debug string convertible protocol. And therefore we have to implement a new variable here called debug description, like this. We make it a computed property, and then we say clothes equal to clothes, and we say price is equal to total price. So the value that you produce in here will then be printed to the debug console whenever you try to debug an instance of this ensemble structure. Okay. Now we create a function in here called buy whole ensemble, like this, and we say it's an async function that throws and it produces an ensemble in here. Okay. Then we should go ahead and buy all our parts. So we say async let socks is buy socks, async let shirt is buy shirt, and async let trousers is buy trousers. All right, so since all of these are async lets, then we need to await on them, and also we should also sorry, not also twice, now became 4 times. So what we want to do is to go and create an ensemble. So we say let ensemble is an instance of ensemble, and it says, okay, give me the clothes. And you probably think, okay, I'm just going to give it socks, shirt, and trousers. But you can't do that because these are async let items. You have to await on them. So just type await, and then we go ahead in here, we say socks, shirt, trousers. But since these guys are also throwing functions, you have to try them. Okay, so you say try. And then for the total price, we're going to say the total price is 200. Okay. There we go, and then we can return the ensemble like this. Now all these errors are hopefully gonna go away soon. There we go. Now you can, to test this, you create a task in your playground, and then you can say if let ensemble is equal to try await on buy whole ensemble. Then you can say ensemble is this, otherwise something went wrong, like that. All right, and then you can see our ensemble debug description will be printed to the screen. It says clothes are this. Let's see if you can get the entire clothes. Maybe we could print it even. So print, it's a little bit easier perhaps to read it here. There we go. So it says is a shirt, is a socks, trousers, and also the price is $200, let's say. Okay. Now, async let can only be used within asynchronous closures and asynchronous functions, or wherever there is a task being run. So you cannot use asynchronous async let within anything that is not one of the ones that I just described. So it should be an asynchronous closure, an asynchronous function, or wherever there is a task that you have, such as in here. Okay, so let's have a look at a few examples. We go in here and we just say func get full name, and we ask for a delay, a fake delay, and we say it's of type duration, and we say we have a calculator for what we calculate, like how we calculate the full name, and it is an async function that returns a string in here, and then we say it is async function, and it in itself returns a string. So our job is just to try to await on this task sleep for this delay, and then we return, we want to return the result of this function, but it is an async function, so we have to await on it. So we say await on the calculator like this. All right, and then you can see all these errors are then gonna go away. And then we have our print statement in here. Let's just remove it so that we don't get this print in the console. All right, now that we have that, we can go ahead and actually say we have a func, we call it full name, and we say it's an async function, which is an arrow function. We just for now, we say foobar. All right, so it is an async function, but right now it just returns a synchronous result back to us, full name like this. Then we can create a task and we can say await on get full name, and we say let's break these down, and then we say the delay is delay in seconds 1, and its calculator is indeed let's actually see, for the calculator let's create a trailing closure in here. Then we say async let name is full name, and then we can say return await name. All right, so let's see if we get the results printed to the screen now. You can see foobar then being printed to the screen. So we could use async let simply because we're in an async trailing closure. Okay, and also we've been able to use async let in other contexts, such as here, which we're in an async function. All right, so I mean, there's a lot more actually to talk about when it comes to asynchronous programming with Swift, but this just gives you an idea of the basics of asynchronous programming. It's very similar to JavaScript and TypeScript, and you could also say it's very similar to actually Dart, for instance, for those of you who do Flutter development. It's a little bit more complicated because, well, it is Swift. It has a long history of its own code base, and there are a lot of people contributing to Swift as a programming language, not even just people just inside Apple. So it is somehow a mishmash of everything the community thought was a good idea to add to Swift. I personally don't like, for instance, async let. I think it makes things more complicated. Almost every other programming language that has asynchronous programming, such as JavaScript, TypeScript, and Dart, don't need async let. They just do async and await, and everything works as expected. I think async let adds a new layer of complexity to your code, which is unnecessary. Some people may argue that it is actually nice, but I personally don't like it so much. But that's just my opinion. And I think although I don't like it so much, I learn it, and I think it is important that we all learn how to use these syntaxes that are available in modern Swift. So with that said, I think we can then conclude this particular video of the Full Stack with Swift course. And we've talked a lot about, you can see we have so many playgrounds in here, I can't even count them. We talk about variables, operators, classes, extensions, generics, pretty much everything that you can think of in Swift. So now what we're going to do in the course is to go ahead and start talking about client development and also backend development with Swift. I really hope that you enjoyed this video. If you found it helpful, please press the thanks button at the bottom of the screen, or you can just alternatively join my YouTube channel. So see you in the next video.